day 3, which is kind of like mile 20 in a marathon. Your brain is possibly a bit tired, but the end is in sight, and we've saved some of the best for last, including for this morning. So I will not be on this stage until 11:20 because we have a hat trick of speakers, 1, 2, 3 in a row, who are going to show you some stuff that I think you're going to love. So I will be introducing them in the order that they'll appear on stage, and then the first one's going to come on, and I will disappear. You're going to be in excellent hands. The first talk is called The Deep Future, Implementing Science Fiction. That is with Pablos Holman. He is a hacker, an inventor, and a technology futurist. His biography is truly out of this world, so I'd recommend looking it up. He's then going to introduce John Bucknell, who's going to be talking about space solar power, solving the future of energy forever. An optimistic talk, very nice in the morning. And then we're going to move on to Leo Howden, as our last speaker, reimagining metal recovery. A new class of chemistry creates a greener, cleaner world. So, without further ado, please join me in welcoming Pablos Holman to the stage.
Hi, you guys. All right, I have so many things that my plan is to just talk even faster than yesterday. So, what are we here for? Well, we're here because what we want to do is understand what does deep tech mean and what's possible. And when we talk about deep tech, I think it's important to sort of separate it from what are we not talking about, which doesn't really have a name, so I made one up. And I call it shallow tech. And shallow tech is all this other dumb shit that people think of as technology, but is really just software. So what we want to do is look at what is the cool shit that we can do in the world is not exclusively software, because we think we live in a world full of technology, but we really just live in a world full of software. And there are a lot of things that you can't do with software, and some of those are things that we should do. So I want to pick that apart a little bit. I'm going to give you some examples. Years ago, I worked on this project. It's called MakerBot, and it was the first consumer 3D printer that you could sort of have at home. And before MakerBot, no one had ever seen a 3D printer. It was like an exotic machine that only existed in labs. And what we were able to do is make something that kids could have. You know, my daughter was 5 or 6 years old, and we had one of these on the table at our house, and she would print high-heeled shoes for herself. Kids grow up with these things. This is how they think of making things. And what's different about 3D printers is they're programmable. So if you look at how we make stuff in the world, in factory automation, we're often you make a machine that makes one thing and then amortize the cost of it over thousands of units. But then when you want to make version 2, you throw it out and make a new machine. And that's not how we want to make things in the future. We imagine that we're going to be able to make factories of 3D printers where you can just draw something in Minecraft and click print and it's going to go make it for you, right? Because that's how kids think. And that's how our engineers are being trained. They're growing up with these programmable machines that never have to make the same thing twice. And that hasn't worked out very well. You know, we don't have these kinds of factories working. The things you buy don't come from 3D printers. And a lot of the reason for that is that, well, there's 2 big reasons. One, they're slow, because they're like 1-pixel printers, right? They put down a pixel at a time. And that's too slow. But the second big reason is that the input materials have to be very high quality, and they're very expensive. And at the end of the day, you're competing with injection molding, which would be the cheapest possible way in the world of making anything. Injection molding in China. So if we want to automate our factories and make them programmable, reshore them to Europe and the US and the places that are closer to the actual customer, we have to be able to make these things cost effective. Well, I met these guys who figured out how to adapt the powder bed style of 3D printers. Those are used for metal. And that's kind of the one thing that has worked in manufacturing, because metal parts are more high value, right? And the printers are faster because they put down a layer of metal powder and then they bind it together. And they print like a layer at a time instead of a pixel at a time. But these guys figured out how to adapt the metal style of printer to print with used coffee grounds from Starbucks. And what's interesting about that is that now the input material costs less than zero. They get paid to haul this stuff away from Starbucks. They throw it in the printer binds it together, and they're printing all kinds of durable goods. They print these coffee mugs, they powder coat them or metalize them. You can't tell the products are made of coffee. They're making sinks this way. They're making, all kinds of, durable goods, light fixtures. They just metalize them. You can't tell it's made of coffee. And it costs less than making the stuff in Asia. And it's fully automated, right? And of course, along the way, you're sequestering carbon. You're keeping biomass out of landfills. There's really nothing not to like about this. I mean, they're also doing it with seaweed and sawdust. They figured out how to print with biomass. And I think these kinds of things are important because they are possible and they're better. And when we're talking about deep tech, a lot of times what we're talking about is really modern industrials. Like, how do we go back and look at the industries that humans have built and grown over the last century or two, take the new technology superpowers that we've got and reinvent them so that they can be 10 times better, 100 times better, 1,000 times better, right? That's what's possible in a lot of cases. Most industries are busy trying to make themselves 1 or 2% better. But if you can get a new technology that allows you to reinvent how you do something, sometimes you can get those 10x multipliers. And that's really where the potential is to solve a lot of the big problems we have in the world. A lot of people don't realize this. A cargo ship spits out really nasty smoke. You don't see that smoke because it has a second gas tank where it burns refined fuel like your car. So when it's in view of people, they normally don't do this. They burn the clean stuff. It's not clean, it's just cleaner. And then when it gets out of sight, they switch to the nasty stuff, right? But why do that at all? We could make cargo ships that sail themselves. It's like easier than self-driving cars. The sailing's been working for, 400 or 500 years, crossing oceans with sails. We know that works. Why would we do that? These things are unquestionably better. The technology's not that hard. We know we could do it. This is an industry that's probably twice the emissions of air travel, cargo. We build almost everything in the world out of cement. It's the single most used construction material in the world. I think it's the single most used material in the world. It is also the material most responsible for carbon emissions. And that's because cement, there's a couple parts to that. One is you're throwing a lot of coal or gas or something to fire up a furnace to heat it up. So a lot of emissions there. But the other reason, you could maybe get rid of that by electrifying the furnace. But the truth is, most of the emissions comes from the chemical process of making the cement. And that you can't get rid of. And this is an interesting one because the cement only lasts for like 50 or 100 years. All of it cracks. Water seeps into the cracks, kind of destroys it from the inside out, and it crumbles, which is frustrating. We try to partially ameliorate that by putting steel rebar in it. So we reinforce the cement with steel. Well, it still crumbles. But look at this. You recognize that? It's called the Pantheon. It's a building the Romans built 2,000 years ago in a seismic zone out of cement with no steel reinforcement. Right? Yet it stands. And somehow the Romans were able to build these things, and then we just sort of forgot how to make cement the way they did. Their cement lasts 2,000 years, ours lasts 50. What's going on? Well, it turns out the Roman cement has extra lime trapped in it. And so what happens is when it cracks, water seeps into the crack and then activates that lime, fills the crack. It's kind of amazing. This just gets stronger over time. But nobody's been able to figure out how they did that. I found a team at MIT that just figured it out. And so now we know how to make cement the way the Romans did, and it's unequivocally better. It doesn't cost more. You can do it in any cement factory. You can use less of it, use less steel, and the kicker, 20% less CO2 out of the box. Like, we can do better on these things now. Years ago, many years ago in my childhood, I grew up with this thing. It's like the first home computer that you could have in the world. But I grew up in Alaska, so nobody for like 1,000 miles in any direction had a computer. And so I had to learn everything the hard way. And it was pretty useless. In those days, computers were super slow. The spreadsheet hadn't been invented yet, so people were pretty conflicted about whether it was actually a waste of time or not. And I thought, someday it'll get faster, someday it'll have more memory, and someday it'll be useful. And really nobody believed me. In fact, I had this thing and I also had a skateboard. And most people weren't sure which was a bigger waste of time. But revenge of the nerds, I was right. Eventually computers got fast. This is the one I was fantasizing about. It's called a Cray XMP, 400 megaflops. Just imagine what you could do with all that computational ability. Well, now every one of you is hauling around something like 2 teraflops in your pocket. It's insane in a way. We're no longer computationally constrained. We're imagination constrained. We don't even know what to do with all this computational ability. This is a totally fake slide that I made up. But you guys have all spent plenty of time in Excel, making a spreadsheet, spitting out charts and graphs like this. This is not what computers are for, okay? Nothing interesting will ever be done this way again. You can just take Excel, drag it into the trash, empty the trash, right? Because this is what I call small data, right? Now, we use these giant supercomputers, and mine has 5,000 cores and a lot of blinking blue lights, and it's super cool, but there is no reason you need one of these. You can just rent them by the minute from Amazon. Anybody can get access to a massive amount of computational ability, right? But what we use them for is to make these kinds of computational models. I think it's really important to understand that's what we're talking about. We're making computational models. SimCity is a computational model of a little city. And you get to try destroying it in different ways. It might be a really wise thing for the people running actual cities to spend some time in SimCity first, right? Because models are how we test our ideas, right? My daughter grew up making models. She would just, these driving little cars around her fake little city. In her mind, she's creating a model in her brain. All of you have done this. You all have a model in your mind that you created over your life. You can close your eyes and picture your bedroom. You can close your eyes and picture how to get out of this room. Your mind is creating models, but it's only making one. And the cool thing about the computers is they can make a lot of models, and they can run a lot of simulations. So when we talk about artificial intelligence, I think it's a little bit of an exaggeration. What we're really talking about is we've created big models, right? You've been using Google Maps for 15 years every day. It's a model of the streets in the world. When you ask it, how do I get home? It says, here's a simulation. Right? Follow the blue line. But it also gives you a couple of gray lines. Oh, here's other options. Right? It's showing you your possible futures. And you can choose from that which one you want to go for. We use this type of technology to make models of the spread of disease, infectious disease, largely in the developing world. So we collect data on climate, rainfall, the travel of humans, all the kinds of things that can affect the spread of a disease. In this case, we're modeling malaria. And what it allows us to do is see over years into the future how the disease will spread. So this is a model of Madagascar. And incidentally, if you go to Madagascar, you should probably go to the middle. That's kind of where the people still are. In the rainy season, malaria covers almost the entire island, but in the dry season, it'll go away almost entirely. And because we have these models, we can test our interventions thousands of times in software before we do it in the real world. This is not science fiction. We've been doing this for 15 years. We're advising 75 different countries on how to optimize deploying their vaccination resources. This is how we save millions of lives a year, right? In the first Ebola outbreak, 12,000 lives were lost. In the second Ebola outbreak, only 12 lives were lost, just a couple years later, right? In part because using computational models like this, we're able to optimize the ring vaccination campaign, optimize how we deploy those resources, contain the disease before it spread. That's what would have been possible with COVID. But we weren't paying attention, right? These technologies are new superpowers for humans to help us see what are our possible futures and choose the one that we think sounds the best. And I think you guys can all understand this. And probably in this audience, we have people who understand these technologies pretty well. But if you think about a picture in Instagram, that is a computational model. It's a data structure, right? A picture in Instagram is the same thing as a spreadsheet in Excel, right? In Excel, you got a cell with a number in it. In a spreadsheet, you got a pixel. The number is what color is this pixel. Same thing, right? Basically, everything works that way in computers, right? So what happens? Well, when you're going to run a filter in Instagram, that's another way of saying an algorithm, which is another way of saying a formula in a spreadsheet, right? It's the same thing, except that a formula in a spreadsheet is typically small enough that you could sort of read it and figure out, you know, A2 plus B2 equals, right? But here, what's happening is I'm going to change the color of a pixel, and then I got to compute what happens to the 8 pixels around it. Well, shit, now I got to compute what happens to the 8 pixels around each of them, and I have this giant cascading exponential amount of computation. That's why it's hard. But computers love to do math. So we can do it. And that's how, and it's so fast now, you're not even waiting. It happens in real time. The progress bar, anybody remember progress? Gone. Like, we don't have that anymore. Computers are so fast. So the point is, when we use all these fancy terms, artificial intelligence, machine learning, transformers, neural nets, whatever, we're just trying to sound smart. You can totally understand this stuff. It's the same thing. Neural nets, basically the same thing. We just have the computer randomize a bunch of algorithms, test them all, throw out the ones that suck. That's it, right? So when you're talking about these machine learning algorithms, the difference is just that it's so much data no human could ever ingest it all. And the algorithms are so complicated and long that no human could ever understand one, right? But they're good at giving us better answers if we learn to wield these tools. So that's going to start to affect everything. And the reason I'm dragging you through all this in the deep tech context is that a lot of times people will say to me, well, you know, you're trying to do these super technical things, isn't that hard? And I'm like, yeah, all the easy shit's been done. So yeah, we're going to go do the hard things now. But also, it's easier than it was. And it's easier than it was because what made software so powerful was the rapid iteration, the ability to just, for very low cost in time and effort, try a lot of experiments and A/B test your way to success. That's why software works so well. And it's not because it's software, it's because of the rapid iteration. Well, guess what? Now we can model almost everything in the world. If I'm building a hypersonic jet or a rocket or a Tesla or whatever, I design it in software, I test it in software, I crash it in software, and then I figure out which design is the best and I go build one. Right? Iterating in hardware, yeah, that is hard and expensive and slow. But iterating in software, we can apply that to almost everything else in the world, and that's why we're making advancements in synthetic biology. That's why we're making advancements in physics for applying it to all these kinds of problems, right? And so we're at this moment in time when the toolkit we have to go do the hard stuff is helping us accelerate that. And it's exciting because now we get to go take on all these big problems and the things that we've been ignoring. So I think this is important. We are all made of stars. And I said this yesterday, but this is our sun. This is the star that we are made of. Like all the energy that you need to survive, to exist, comes from that sun. And that includes the solar power, but it also includes the coal and the gas and even the photosynthesis that makes plants for everything you ever ate. Even if you don't eat plants, you know, they feed the things that you do eat, right? And it even includes like the uranium in the ground, right? And we need to make enough energy to power you. And the average person on Earth gets as much energy as a single toaster running 24/7, right? That's all the energy you need to survive, to power your cooling and heating. It's the energy you need for transport, for your food, everything, one toaster. I like to make fun of Americans who get 8 bonus toasters, right? We get about 9 or 10 times as much energy as the average person on Earth. Europeans, in general, were kind of running at about 5 to 6 toasters until recently, and now they're down to like 4 to 5. Not because they want to, just because they can't get any more energy. But to get these averages, 3 billion people have to live on less than 1 toaster, right? And again, not because they want to, but because we haven't provided enough energy for them. So the true demand for energy in the world is 10x global energy production. And I don't think we're being honest with ourselves about that. It sounds unfathomable. It's the true demand for energy. How do you give every human on Earth the living standard that we get? Right? That maps to energy. And if you want to solve all these other problems, you kind of got to solve energy first. But here's the thing. 10x global energy production sounds insane, but we have done it before. In the last century, we 10x global energy production on this planet. Now, we did it by burning more coal, burning more oil, burning more gas. Probably we don't want to 10x using that stuff, right? We have learned our lesson. At some point, there's only so much shit you can put in the toilet before it doesn't flush anymore. That's what we're dealing with. So we want to 10x using what we call renewables, right? Let me show you a couple things. This is all of the metals mined in the world last year. Aluminum, copper. This gives you a visual sense, but check this out. They all pale in comparison to that one, right? We mine so much iron that those don't even register. But look at this one, this tiny little pile here, uranium. In that one pile, there's enough energy to power the entire planet, everyone, just from that amount of uranium we mine in 1 year. We could get rid of all the coal, all the oil, all the gas, everything, just with the energy we already mine from uranium. It's so energy dense that if you had a single can of uranium the size of a soup can, You could power you and your family for your entire lives with just that one can, right? But it's radioactive and dangerous and messy, and we don't know what to do with the waste, so we've been saving it for our grandkids in these stockpiles. We invented a new type of nuclear reactor that's powered by nuclear waste. You literally take the waste left over from making bombs and put it in this thing. It enriches it and burns it. What a lot of people don't realize is today's reactors are only 0.7% efficient. 99.3% of the energy is still in the nuclear waste. These modern reactors can get the rest of that energy out. All right? This is a stockpile in the US in Kentucky. 700,000 metric tons of depleted uranium, saving it for our grandkids. Left over from making bombs, left over from making reactors, right? With this one stockpile, we could power the entire planet, including growth, for the next 1,000 years. We don't even need to mine uranium. Like, we have this miraculous energy source, but what happened is humans told ourselves the wrong story, right? We started to conflate nuclear reactors with nuclear bombs. We got mushroom clouds in our heads. We outlawed nuclear reactors before we understood them. And we are living with the consequences. If we had built nuclear reactors since the 80s, you never would have heard of global warming. That's what's possible. But we made the wrong choice, and now we're living with the consequences, and we have to course correct. That's one way we could do it. Build a lot of nuclear reactors, and we should. There's another way that people are looking towards, which is fusion. Fusion is exciting because you don't even need to mine uranium, and you could potentially make a machine that emits more energy than it takes to operate it. Everything we do now, you just put fuel in, whatever the fuel is, you put it in and burn it until it's gone. But a fusion reactor, if we get it going properly, it can actually produce more energy than you put in. And we know this is possible because of the sun. The sun does that all day, every day. It's fusion. We're just trying to figure out how do you do it on Earth without, melting everything. And this used to be the kind of thing that was fantasy for scientists, but just in the last few years, we got the last breakthrough we needed to be able to do it. So there's no new science necessary to accomplish this, but there's a lot of hard engineering work, and it's going to take some time. And I don't think we should be sitting on our thumbs waiting. But if it works, maybe 10 years, 20 years from now, you'll be able to power you and your entire family for your entire lives off of one glass of seawater. That's what fusion can do. So look, I invited a couple of my favorite founders to come up here with me today. First one that's coming out is John Bucknell. He's the founder of Virtus Solis. And this is a company that has another way of solving energy in our lifetime. And I'm so excited to share this with you. It's one of my favorite things in the entire world. And so we're going to get John out here, and then he's going to show you what he's doing, and then we can take some questions about it after that. So thanks for listening. Yeah. Hey.
Yeah. Good morning. So I titled my presentation, Solving Energy Forever for Everyone. And really, that is our goal at Virtus Solis. Our goal is to provide clean, firm, sustainable energy forever. And the sun, 4.5 billion years from now, may not be able to provide that energy anymore, but might as well be forever. But we can do that. We can do that today. The technology is here, and I'm going to tell you how that is important. Now, if we talk about renewable energy, the things that we're not digging out of the ground, they have challenges. This chart shows the history of Germany installing solar power. That's the orange line, installed capacity. And the blue line on the bottom is how much of that installed capacity is being used on a daily basis for the last 20 years. And if anyone is paying attention, about the time that chart goes by, January and February, there isn't very much of that column being generated. That is wintertime. All of us that live in the northern latitudes, it gets cold in the wintertime. And worse yet, it gets cloudy. And that means that you can have solar power that you've installed only generating like 1% to 3% of what you installed. And in fact, the same patterns hold true for natural gas usage in Western Europe. For 10 months of the year, we store all the natural gas that's available and burn it all in just 2 months to stay warm. So we need a solution that is able to provide the energy that we need all the time. Well, that energy is already up there in the sky. We just need to figure a way to get it to the ground. And we call that space-based solar power. It's very simple. You put solar panels in space where there's no weather, there's no day-night cycle, and you get that to the ground. And we'll talk about how we get that to the ground in a little bit, but space solar power as a concept is very straightforward. You just need to get a way to get those solar panels in space. And if you've been paying attention, commercial space launch has been evolving a lot in the last 20 years. In fact, a decade ago, I was at SpaceX developing the Raptor rocket engine that powers the Starship vehicle, which is a new heavy lift launch vehicle. Maybe you've heard about it. It should fly any day now. They're waiting for the FAA to give permission to try again. But that vehicle is designed to be fully reusable and go all the way into orbit and come all the way back and do it a few hundred times before needing to be recycled. Today, SpaceX flies about 16 times the rocket, which is 16 times more than anyone else. And this new rocket, maybe 200, maybe 300, we don't know. But you can get to space very cheaply now. The Falcon Heavy has been around since 2018, and it's very low cost. It's thousands of times lower cost than prior solutions. So you can get things up into space. And what should you do up there? Well, there's going to be 10 billion of us in about 20 years' time, and we all need energy. Pablo's described the fact that most of us are in energy poverty globally. The global GDP last year was about $104 trillion, and about 15% of that was primary energy use. That includes all kinds. But the true demand is probably 10x that. And we don't have 10x of the global GDP, so really the only thing you can do is to bring those costs down. Now, the good news is that space solar power as a topic is a generation, it makes the power, and a transmission technology in one. That means that once you can get at it, you can bring it to the ground. And I'm going to tell you about the history of this, because you're going to be amazed at how long we've been talking about this. So this guy is Konstantin Tiaski. He's a Russian school teacher, prolific inventor. He wrote the rocket equation in 1897. And those of us who develop rockets learned that it's very hard to get off this planet, but it's possible. You need to build a very big rocket that's mostly rocket propellant, fuel and oxidizer, to get off the planet. But he kept going. He described space solar power as a topic, as a technology to power all of us in 1921. So it's 102-year-old as an idea alone. And then another guy, you might have heard of Isaac Asimov, popularized space solar power as a topic in a story called Reason in 1941. And in fact, that became part of the iRobot series, which was the very first science fiction, kind of, sort of, that was very popular. So it's been around in popular media for a very, very long time. In fact, there's been engineering solutions since 1968. Dr. Peter Glauser, an Englishman working for NASA in the late 60s, actually went through all the engineering necessary to figure out how to build space solar power plants, and he has a patent in the early 70s. So the engineering solutions have been around longer than I have. The problem has been that it was too expensive to do back then. A lot of the underlying technology you needed, commercial space launch, modern manufacturing, automated manufacturing, and especially the power electronics and what Moore's law has done to a semiconductor manufacturer weren't there yet. But that was a long time ago. This solution is the first one that NASA worked on in the late 70s, and this is called the NASA Reference System. It was a bunch of ex-Apollo engineers. I'm lucky enough to have a father that worked in the Apollo program, so I've been around space for a very long time. But these guys said, hey, you know what? We can do this. We have the technology. We know how to build it. And they spent like on the order of $600 million studying this in the late 70s. So this blue square in the background is the power satellite. It's about 2 gigawatts, about 2 nuclear power plants. But the long axis is 7 kilometers long. It's enormous. It covers all of central London up in space. And they were going to put up 60 of them in a geosynchronous orbit, which means it's sitting over a spot on the ground and beaming power. But in order to make it, they needed to put mines on the moon. They needed to dig materials out of the ground, put them up into space, and put factories up there to turn those raw materials into finished goods and start putting all this together. In fact, they needed space habitats in the lower right, rotating space habitat to put astronauts in to put it all together. And then, worse yet, we needed the space shuttle and its derivatives to get down 1,000 times less cost to orbit than they were operating. And the space shuttle hadn't even flown at this point in time. So NASA went to the US Congress in 1980 and asked for $1 trillion in today's money and said, hey, we'll have the first one operational in 2006. And do you think they got told, go ahead, let's do it? They didn't. They didn't, in fact. And the funny thing is, being an American and talking to my colleagues at NASA, they remember being told no. They remember it so much so that they don't want to see another dime spent on this technology, at least until relatively recently. And it took a friend of a friend who had a conversation with a British business called Reaction Engines, who is developing aerospace planes. A friend of mine named Keith Henson, who is part of what I'll show you on the next slide, asked, hey, what does it take to put up millions of tons into orbit? And he talked to his friends at Reaction Engines, and they said, well, we know we need to build about 20,000 rockets to fly it up there. And we can do that, and we can reuse them, and it'll be low cost. And that was in the early 2000s. And then when the UK decided that they needed to fix their energy, there was something called the Net Zero Initiative. And they went and looked at offshore wind, onshore wind, terrestrial solar, new nuclear power plants, and space solar, which no one had been talking about for about 40 years. And it was because Martin Soltau, who runs another business based here in the UK called Space Solar, which is doing the same thing as we are, had known about this study at Reaction Engines. So all that snowballed into an effort to develop this. And so the Europeans actually are moving faster than us in the US on this topic because they didn't get told no. So I'm going to tell you a little bit more about that. But more importantly, in-space infrastructure is the key to making the cislunar economy and everything off this planet work. And right now, the communication infrastructure is the only thing we have in orbit today. You might recognize some of this artwork. This was Gerard O'Neill at Princeton in the late 70s. He and his students were trying to imagine what should humanity do? I mean, where should we live? Where should we operate? And they came to the conclusion that we should live and operate off the planet. And there's a lot of us who believe in that vision. We should be able to live on this planet. It's great, but we should also be able to live anywhere else. And we need to figure out how to live up there. And these are renderings of habitats. And the one on the lower left is actually made by a guy named Jeff Bezos. He wants to do the same thing. He's very big a fan of it, but the way these things were going to be built and paid for is building solar power satellites. And in the late 70s, early 80s, it just wasn't commercially viable yet. And one of the big challenges was not only the economics, because the underlying technology wasn't there, but it was in a way. And I'm going to tell you about that in a moment. So my company, Vertisolis, we have solved the last little remaining element, and that is how to get the energy from orbit to the ground. We're using low-intensity microwaves. In fact, we did a study for NASA to do this on the moon for their very first lunar base a year ago. And this is the winning proposal. They needed to figure out a way, because there's no infrastructure on the moon, to put power plants on the ground and then distribute that energy to all the different end users. So with that, I think we are going to run a video telling you basically at a high level how my system works.
Moore's law and modern manufacture enables in-space infrastructure. Space-based solar power satellites are the key infrastructure for expanding into space. Low Earth orbit is not suitable for solar power satellites, but on-orbit propellant transfer allows access to higher orbits at low marginal cost. Virtus Solis's power satellite constellation is planned for a 12-hour medium Earth orbit called Molnia, which is uncrowded and highly elliptical, spending 11.5 hours of every 12 at 35,000 kilometers above the northern or southern hemisphere. This orbit allows 2 ground stations on opposing sides of the planet to be served sequentially, providing baseload capabilities. The arrays of thin tile satellites are assembled in the final orbit, transported flat-packed in racks for maximum usage of the rocket's payload bays. The assembly robots extract 25,000 satellites and then assemble them into arrays of 100,000 or more. Each autonomous satellite delivers about 1 kilowatt to the ground, and the arrays can scale up to over 20 gigawatts each. As the satellites are interchangeable and cost less than a laptop, servicing amounts to removing and replacing elements of the array. The assembly process is simple. Extract the satellites from the racks and click together like Legos into large circular transmitters of 0.5 to 3 kilometers in diameter. Once a sufficient size, the arrays can transmit power to 1 or more ground stations, and a constellation of 2 or more can provide baseload power to multiple ground stations simultaneously. You can see this constellation of 3 power satellites provides redundant coverage to nearly the entire northern hemisphere. The ground stations are 2 kilometers in diameter and can absorb up to 1.5 gigawatts each, powering 150,000 people, and can be sited and built like conventional solar farms near end users. The launch vehicle can return to the launch site and be reused with only small propellant use. Virtus Solis is Latin for the power of the sun. Virtus is the root of virtue, and as the Romans didn't have a concept of energy as we do, it is better translated as power or kingly authority. This power to change the world aligns with our vision of clean, firm, low-cost, globally available energy. Low-cost energy is the greatest lever for universal prosperity.
So that's all really nice renderings, right? How far away are we from reality to doing all this? Well, the good news, I've already built it. The key element is the proof of concept that we've done is a wireless power transfer system that can operate from orbit, 35,000 kilometers above us, all the way to the ground. And at that altitude, about half the Earth's surface is visible in line of sight. And if you build a transmitter big enough, you can move power wirelessly at very high efficiencies. We're talking high 90s. In fact, we've chosen 10 gigahertz microwaves because it penetrates the atmosphere and weather with almost no loss. We account for about 1.5 to 2% of the total energy that we transmit will be lost in that area. So in order to prove it works, we had to build a demonstrator. In fact, this March of this year, we built the largest wireless power transfer system, the first one to do end-to-end wireless power transfer. We did it over 100 meters on a football pitch. And this is the system that I'm going to show you part of today, and I'll show you that in a few minutes. But can we roll the next video, and I'll talk a little bit about what we did. So this is at a football pitch in Indiana. We put a transmitter about 100 meters apart, and we have 3 receivers on the other end. One is Rectana that's receiving energy and turning it into light so you can see it, because as an invisible technology, it's very hard to prove that you're doing anything. And this is my co-founder, Dr. Tate, but we have a number of other receivers. But one of the key things they're asking, hey, what happens when a plane flies through it? Well, we put this drone right in the middle of that power beam, and it's carrying a receiving antenna that lights up LEDs. And that's some of my team, but that's the transmitter there on the left. It's 2 meters high, 2 meters wide, about 6,400 elements. we transmitted about 60 watts to the far end in DC power. So that system is the first one anyone's ever done, and that is an actual fractional space solar power system. That is one satellite and one receiver at full scale of what we're going to do. But when you get to the other end, you need to turn it back in electricity. This is my senior scientist, this is Lin Qing, and this is the very system we got operational in January. These receivers that turn microwaves back in electricity are the most efficient ones ever built, at 81% efficient. That's our first attempt, and we think we can get that to high 90s. So the key to making this work is we can use existing launch vehicles. The Falcon 9 series here has transporter missions that fly about once a month, and they put a bunch of small satellites up, in maybe 15 to 20 of them. You can rent a spot on the front of the ESPA ring and their payload fairing for about $5 million. That's really cheap compared to the $60 to $66 million that the current launch costs cost, and you can put up experiments. And we intend to fly a fully operational pilot plant in 3 years by end of 2026 so that we can build the full scale system, which is just many more of the same satellites, which are about 1.5 meters across, by the end of this decade. And so if I can have Pablos come back out, we're going to show you how all of this works. So you can see on my left here, this is a transmitter. This is 1% of what I demonstrated in March of this year. And this, just no funny business. You can see there's a power supply on the ground. And so there's an LED powering this guy. I don't know if you can see it from this angle, but at scaled physics distance, so orbit to the ground, 2.5 meters is how far 35,000 kilometers is. So we talk about scaled orbital distance, the aperture size, in this case 192 millimeters squared divided by the wavelength, which is 30 millimeters, is only 2.5 meters. And we're moving power from here to here. But the fun thing is Pablos can walk all the way across the stage.
We should have made the light aim that way.
Yeah. That is actually all the way to the moon. And we're moving power the same way. So
It's actually cool because you can see, like, it's, hopefully you guys can see, it's lit up.
yeah,
If I'm here, but if I get out of the beam, then it goes off and comes on.
yeah,
If I'm aligned, and I guess if I got to aim it in the right direction.
yeah, yeah. And if you hold still, this piece of paper is opaque to light, right? So if I put it in front, a little bit attenuation here. But if you put a conductor, like my tinfoil here, it blocks it completely. So if you're in a satellite or in a plane, or you're working on the ground, working on one of these microwave receiving systems, you're not exposed at all. Even though we're running fractions of
Just wear a
the intensity
tinfoil
of
hat.
sunlight, these systems are completely safe. I've spent 60 or 70 hours standing in a power beam that's floor to ceiling. So this one's, yeah, it's fine. I mean, I would argue, I mean, you can barely tell it's on. It's like if you stand in front of your oven from across the room after taking cookies out, you're like, I can feel a little bit of the heat. And it's photons. It's the same photons that sunlight's bringing down from the sky, and we're just using a different wavelength. And it turns into heat when it intersects with your body. And one of the reasons we've built it this way is because it's safe. None of the plants or animals that are going to, I mean, we're mostly worried about birds sitting on our transmitters as they're going from north to south during their migration periods and getting in the way of us receiving power, but it's not going to hurt them. It's just one of those things that we want to make sure that if our goal is prosperity, really we want to make sure that everyone is going to have a good time and not have to worry about us installing big orbital death rays, which is the other option. But having said all that, hopefully you guys got a feel for what space solar power is all about. And as a commercial business, I intend to have this all done in a very short period of time because investors want to see things happen. And the technology is really ready. It's actually been possible since 2018 to do this economically. And one of the key things that you may not realize is that because all of this can be mass manufactured, and one of the key points of our architecture is we're making millions of the same thing, the same satellite over and over and over again, and they're about the cost of a laptop, a few $100s. You can build that and pay it back in just 2 years, roughly, from the investment. And that makes the levelized cost of energy, which is what you pay. I don't know if you look at your electricity bill, but I pay about $220 a megawatt hour living in a a place in Michigan where the power plants have been there for 60 years. They should be paid for. So most of the cost is actually the transmission cost, but our system, by the time we build the first gigawatt, is about $30 a megawatt hour, which undercuts energy costs across the board. That's not just electricity, that is fossil fuels, the petroleum you put in your car, the aviation fuel you use to fly an aircraft. All those energy sources are more expensive than what this technology makes possible. So that is what I want to communicate, is that it's possible now, and I'm the first commercial entity pursuing this, but there's at least a half dozen others, and we hope there are more because we think the time is now.
Well, thanks. That's amazing. I have a few questions for you, and I think I don't know if we have someone with a mic, but we can also take questions from the audience. I think you covered this, but just to make it clear, like if the antenna is beaming power down to a receiver on the ground, and I decide to have a picnic on the receiver, what's going to happen?
Well, you're going to decide that you had to climb that fence to get in the middle of the receiver, but absolutely nothing. The human thermoregulatory response, and in my case it's called sweat, is able to reject a whole lot of energy, and it's only coming down as heat.
Yeah.
And this system is maximum about half the intensity of sunlight. So if you can stand to go outside on a day like today, you can stand there and maybe sweat a little bit, but that's it. That's all that's going to happen to you.
Yeah, amazing. And so birds can fly through it, planes can fly through it, all that. We know that's working.
Yeah.
And then what about, when you talk about the launch cost coming down, if I remember right, the space shuttle was kind of $20,000 to $40,000 a kilogram to get things into space. And then SpaceX is at about $2,700 a kilogram right now, which is an extraordinary improvement. Mm-hmm. And then where's the target for this to make it sort of cost effective? Yeah,
so the Falcon 9, the earlier rocket that started in 2011, is about $2,700 a kilo to low Earth orbit. Oh. A Falcon Heavy that came out in 2018, which is about 3 times the payload, but only 50% more cost, gets you down to about $1,800 a kilo.
Okay.
At that price point, I can sell electricity for about $100 a megawatt hour. So not as cheap as all forms of energy, but these forthcoming heavy launch vehicles like Starship, its stated price point, and this is not me saying it, this is Elon saying it, is $200 a kilo. At $200 a kilo, my price is $30 a megawatt hour. And that's assuming very modest reuses of these launch vehicles. So that, again, that system, that Starship vehicle is designed for 200 launches. I'm only accounting for like 15. So amortizing the purchase of a new vehicle, reusing it 15 times. So if we get to 200, I am much lower than that.
So at 200, you basically become the lowest cost base load energy anywhere on Earth.
Anywhere ever, yeah.
And I think to me, one of the most exciting things about it is you don't need storage. Like that chart that John showed at the beginning showing how like in the winter the solar doesn't really work. That's the people working on terrestrial solar are fantasizing about having giant batteries to store energy until winter. And we don't have a technology that can do that, not at a grid scale. So it's exciting. What I think is amazing about this is it eliminates the need for storage. And you solve transmission for free too, because the other big problem we have is we're putting solar farms out in the desert and then trying to move the energy through power transmission lines to where the people are. And there's a huge amount of losses in that. And so you solve that problem too. It's just very exciting, elegant solutions. So.
Yeah. And it's all enabled by modern software as well. These systems are vast distributed networks. They're all operating a lot like your cell phones are. In fact, the antennas that you have in your cell phone are microwaves as well, and they just happen to have a much smaller number of antennas than I've shown you here. This is 64 antennas, so 1% of the 6,400 that we showed earlier, but the underlying technology, the software to control all of it is all here today. So cool. We have, these systems are software defined, right? You can tell a transmitter to send power to 5 or 6 or 10 places at once. But hey, there's questions.
Yeah, we'll take those.
Many questions. That's fantastic.
Hi, I'm David Wood, Chair of London Futurists. Great talk.
Thank you.
Back in June, one of the cabinet ministers in the UK, Grant Shapps, announced that the UK government was going to put £4 million into support for space-based solar. Are you welcoming that? Are you part of that initiative?
Yeah,
or are you separate?
actually, we are part of the Space Energy Initiative here in the UK. We are operating under a government contract through the Net Zero and Energy Security Bureau, which was formed earlier this year. We are developing open source software tools so academia, industry, governments can model what these things look like through the University of Bristol. So yeah, we're already involved in that. We have a subsidiary based here in London so that we can leverage all the interest. So yeah, we're already taking part in that. So
Awesome.
Thank you for that. Thank you for asking.
Congratulations, John. Very interesting presentation. I have been following space-based solar power for over 20 years with Keith Henson that you mentioned. And now China and Japan are also pushing for this, and these are the governments of China and the government of Japan. So how do you see them? Because you are not a government, you are a startup, and China is big, and Japan is big, and they want this technology too. So how do you see these two markets, Japan and China?
Well, I would argue that the reason startups exist is because the existing systems aren't delivering, and delivering at the cost that we like to. So as a commercial entity, I'm very motivated, and I think our timescales, even compared to all the other research organizations that have been working on this for the last 40 years, they've been saying 2040, maybe 2050, they'll get the first one up. I'm saying 2030. So not super worried about those other organizations because they just don't act like startups, and startups have an impetus to get these things delivered quickly and serving the customer's needs. So if we were to somehow run afoul of these governments, I still think the world's free enough that organizations like mine can operate and deliver what customers want. Because we make the world a better place. One of the things that we talk about, I told you we have a 12-hour orbit in that video. So that means for every asset that's in orbit, there's a ground station in the Western Hemisphere and a ground station in the Eastern Hemisphere, and they're sharing. So if you don't like the person in the Western Hemisphere, you're tied to them. It's a force for peace because your neighbor or someone else is actually sharing the energy, from someone else on the other side of the planet. So in that way, I hope that everyone would agree that this is the thing to do.
A fantastic talk, very interesting. From a practical point of view, how big would a ground station have to be to power London, for example?
Well, that is a very good question. I don't know off the top of my head how many gigawatts you use, but generally a gigawatt is 150,000 people's energy, and that's every bit of it, whether you're using petrol or diesel or what have you. I would probably guess somewhere in the 5 to 6 gigawatt range would be three ground stations, 3 2-kilometer ground stations would be necessary to power the metropolitan London area. And you can use the existing distribution infrastructure, but a lot of our initial power stations are going to be adjacent to existing solar farms, and we can use their transmission distribution equipment at night, so that you'll build up a power line, and it's only used during the day for a conventional solar, so we can build adjacent and use that at night to power. So it's a good question. Thank you.
Good morning.
Morning.
First of all, I love the idea. Congratulations.
Thank you.
Incredible. I just have a question about what is going to be a potential question that you're going to be asked. So they're talking about putting things in space to block out the rays of the sun to slow down global warming and to slow down the heating of the atmosphere. What is the danger, since you've described that this feels like heat, of having these all around in space and coming down onto receivers, of actually warming the atmosphere?
Good question. So just in terms of blocking sunlight, these orbits are mostly above and below the path from sunlight to the ground. So we're intercepting energy above the orbit of the Earth, and we're delivering it to the ground. But the key is that I don't have the number off the top of my head, but I think it's in the terms of terawatts, the number of watts that sun projects onto the ground. And our systems are small enough that they're about 1,000th of a degree arc width above us, so you can't see it, and it's not blocking the sun because it's out of the path. So these systems are only adding fractions, small fractions, 1,000ths of a percent of additional energy to the ground compared to what the sun is already doing. And one of the key things about the sunlight that comes into the ground and warms the planet, is that most of it is re-radiated away at nighttime. So if you look at your temperature profiles over the course of the evening, just before the sun rises is generally when it's coolest, and that's infrared radiation. You're rejecting all that heat that comes in. But the key element is, even if we were to increase our consumption of energy by bringing additional sunlight down, it's way less than the heat energy that's being released by fossil fuels today. So we're net dropping the energy being introduced into our atmosphere by a lot. So
Awesome.
yeah.
Last
one.
question.
Very good.
Yeah.
All right. It's incredible. Really, really cool. So you talked a little bit about the size of like a solar array to receive the energy that would be required to power a city like London. And you talked about utilizing the infrastructure that's already built into solar farms in order to try to power that. But you talked earlier about transmission costs being much lower utilizing this kind of wireless transmission. If you're utilizing the transmission infrastructure that's already being utilized by solar energy, don't you sort of lose some of that and end up taking on those same transmission costs that's suffered by those institutions?
No. And the short answer is that you'll read about the cost to add the distribution networks, the transmission networks, to integrate intermittent renewables into our power grid. And I think globally it's a $21 trillion bill to add the infrastructure, just the transmission infrastructure, to move the energy from where it's generated to where it's being used. So that's cross-country, high-voltage DC networks, and all those other things. So the key element is like there is a project you might have heard of. They're going to use put a solar farm in Morocco and run an undersea cable 3,800 kilometers here to England. And that was a $4 billion project just to build a cable. That cable is unnecessary in a situation where you're using space-based solar, because you're redirecting the energy from orbit to wherever the local use case is. And in America, most of the sun and wind is on the coasts and in the southern parts. And in order to get that to where the consumers are, you have to build a huge distribution network. And those are the costs that we're avoiding. Yeah. So that is really what we're talking about. It's not the local distribution costs, but the long-distance distribution costs. Okay, that was it, I think.
Yeah. Thanks, you guys. Thanks so much, Sean. This
Yeah.
is exciting. I'm really glad we get to share it with everyone.
So let's bring on Leo.
Yeah, great.
All right, thank you. Thank you very much.
So I'll just introduce Leo real quick. Leo, this is for you. Leo is the founder of another company that I really wanted to share with you guys. It's based here in the UK. I won't spoil anything. I'll let him tell you, but it's one of the most exciting things coming. So thanks.
Thank you. Great. So my name's Leo Howden. I'm a co-founder and managing director of DesCycle. And I'm here to talk to you today about how we're changing an industry that's really central to some of the things that you've been hearing about over the last few days. So when I was putting my presentation together, I really wanted to make it as relevant to the audience as possible. So I'm going to tell you a few things that you probably already know, but then I'm going to tell you why they're relevant to what we're doing at DesCycle. So we are a global community, connected together through a web of technology. And that technology 30 years ago would have sounded like science fiction, but now is science fact. The internet revolution has ushered in a new world, one that has empowered and connected people to an extent that it's scarcely believable how we ever lived without it. But as we're moving forward, we're breaking new ground and moving away from a physical world to a virtual world. Dropbox, OneDrive, Google Cloud have all replaced the physical with the virtual. And web-based apps, SaaS-based products, have given us everything at our fingertips in a virtual cloud. But the tether that connects that cloud to the earth is very real, and it's called a data center. Data centers are the physical manifestation of our virtual world. There are over 8,000 of these centers spread across the globe, and they have become a truly indispensable part of our infrastructure. They are so intrinsic that they're almost forgotten by the public. But as we take another leap forward in computing with generative AI and machine learning, their importance is only going to grow. Imagine adding 500,000 servers a year for AI training. Double that when adoption really takes off. The number of data centers is going to grow massively. But what makes this new wave different from the previous one is that those earlier waves were built on incremental cloud computing, and it was broadly used. It's called commodity hardware. But that model is drifting, moving in the other direction. The hardware for AI and machine learning is going to be very different. Compared to the basic cloud hardware, the equipment for AI is going to be far more complex. We're moving from what's at the top to what's at the bottom. 3 times the circuit area, 5 times the processors, 6 times the volume, and 10 times the power consumption. And these data centers must deliver higher power, more bandwidth, and expanded cooling. And the physical servers themselves have to have more connection points to create the compute environment needed to train large models. But what underpins all of this amazing technology is a simple thing: metal. Miles of copper wire and plating for electricity and heat transfer, gold for high-speed connection, and palladium for power delivery. And this growth in data centers comes as manufacturers and cloud service providers are adopting circular supply chains and negative carbon goals as climate issues impact business practices. So as the use of these data centers continues to grow, it's going to create a problem. AI is going to be relying on technology that has a major environmental impact. Now, consumption of resources is something that is generating a lot of attention. Already, the energy cost of data centers is immense. They consume between 2 and 3% of worldwide power, and that's expected to climb to 10%. There are even predictions that the demand from data centers is going to outstrip the electricity production globally. In fact, power consumption is such a concern that the European Union is even considering placing data centers into space to be powered directly from the sun. And it's not just power consumption. Water consumption is an issue too. A large data center can consume anywhere between 1 million to 5 million gallons of water a day, enough for a small town of 10 to 50,000 people. But it's not just the consumption of resources that's going to be problematic. All of the new server boards are going to be replaced at a faster rate than they have been before. We're going to go from a refresh rate of every 5 to 7 years to every 2 years, which means increasing demand for things like AI is going to be contributing to the world's fastest growing waste stream, electronic waste. Think of all the server boards and motherboards and everything in your electronics. Globally, there's over 50 million tons of electronic waste is produced every year, and that's forecast to double in the near future. And if you want to visualize that, think of 125,000 jumbo jets stacked side by side, more jumbo jets than have ever been created. It's an environmental emergency, and AI is going to be contributing to this problem. But the thing about e-waste is that it's actually very valuable, and it's worth the effort to recycle. There's even a term for it: urban mining, turning trash into treasure. The downside, though, is that we are very bad at recycling and dealing with the pollution from the digital world. In fact, only 17% is actually recycled. The rest is left to rot in landfill or sent to underdeveloped countries, where it eventually leaches into the environment, creating yet more pollution. So that means that not only are we creating pollution from not recycling, but we're also losing large amounts of metal that we need to dig up and process again. And this itself has a huge impact on the environment. Mining metals is responsible for 4 to 7% of annual global greenhouse gas emissions. Now, what are we doing with what we're actually recycling? Well, all those server boards and motherboards, they are recycled through a highly intensive process called smelting, which is just another way to describe burning metal at high temperatures, using a process that requires significant amounts of energy and produces emissions that lead to poor human health conditions. So why is this all important? Well, it's because we live on a planet with scarce resources. Those resources are only going to get scarcer as we increase their demand. The International Energy Agency estimates that the global economy is going to need 6 times the amount of metal in 2040 than it does today in order to reach the global goal of net zero by 2050. We should be recovering those resources in what we have already used and doing it in a way that is sustainable to meet this challenge. Because we have to ask ourselves, is it really smart to be relying on new sources of metal to meet our transition to net zero when we already have so much in what we're throwing away? Now, what if we wanted to create a new way of getting these metals out that wasn't so negative to the environment? Something that didn't rely on using extreme temperatures, didn't rely on lots of energy, or didn't produce CO2 or metal emissions. Wouldn't that be a great way to recover the metals? Something that is to create something that is actually sustainable. What would it need to look like? Well, you would want to use something that was non-toxic as your base. Maybe something where the chemicals were organic, biodegradable, readily available. It would also help if they were reusable. Now, I know that that might sound like science fiction, but just as I said at the beginning of my presentation, that we're always turning science fiction into science fact, we're doing the same here at DesCycle. We are implementing science fiction. We've taken over 20 years of scientific discovery and innovation in a new field of chemistry and created a catalyst for a profound change in the metals industry. Let me show you what we're doing. Our technology is based on a new class of chemistry known as deep eutectic solvents, or DES for short. DES are a unique class of chemistry that were invented right here in the UK in the early 2000s. And they are mixtures of organic, biodegradable, recyclable commodities. It's not a water-based system, which means it works very differently than current processes. Think of these as solids that, when combined together, create a liquid. Now, to visualize that, think of 2 slush puppies being mixed together at the cinema to make a favorite drink. So what are deep eutectic solvents? What does it mean? Let's break it down. We have the word deep, something that's intense. We have the word eutectic, which basically means something where a mixture that has a lower melting point than its constituent parts. And we have solvent, which is something that can dissolve other substances. And when you put it all together, you get DES. Powerful solvents with amazing superpowers. So to help me explain their superpowers, I'm actually going to lean on one of my all-time favorite books, The Alchemist by Paulo Coelho. And in this story, our hero's journey meanders through a series of events until he meets the alchemist, somebody who can help him turn lead into gold. Now, I'm not saying that DES is going to turn lead into gold, but its superpower is, just like in The Alchemist, one of transformation. DES can take a metal and transform it so that it's able to move into a liquid, just like a cube of sugar dissolves in a cup of coffee. So what's going on? As I said, DES are a combination of organic, biodegradable bulk commodities. They're made of things like carbon, oxygen, nitrogen, and hydrogen. Think of things like urea, which is a common fertilizer, or vitamin B4, which is used as an additive. When you combine these chemicals together, really cool things happen. the lattice energy of the system, which is what's holding everything together, drops. And these solids become a liquid. And in this liquid that we've created, it loves metal ions. It loves them so much that when we put a metal into the solution, it dissolves like the sugar cube I talked about earlier. So let me show you what I mean. If you can play the video, please. So here we're taking our solids, combining them together, and they become a liquid. And in that liquid, we place what we want to dissolve. And the metals dissolve into the solution, and then we can recover those metals. But the beauty of DES is that it's not consumed during the reaction. It's a medium through which it happens. So we can use it over and over again. It's completely recyclable. So now that we've got a new way of recycling metals using mass-produced, biodegradable, organic solvents which aren't consumed in a chemical reaction, what can we do with them? Well, it turns out quite a lot. With DES, we can selectively recover metals, which means we can tailor a process to take something out or leave something behind. We can recover a range of different metals, but crucially, without the current associated environmental impact. And that's the key here. Using DES is a cleaner way to get hold of the metals that are going to be in demand as we move to net zero. The waste that's generally thrown away is an amazing opportunity to recycle metals from one generation to the next, creating a circular economy. And it also brings in elements like traceability, which are important for supply chains. If we know where something came from, if we know what's in it, we can create a chain of custody. And with DES, we can recover that metal in an environmentally sustainable way. So that means that we don't have to rely on pollutive processes like smelting. In fact, because DES is organic, biodegradable, and works at low temperatures, the cost of construction of a plant to process electronic waste and recover this metal is an order of magnitude cheaper than a smelter. And it's an order of magnitude smaller in its footprint, which means we can create local recycling, moving away from big aggregate smelters to something that can happen at the local scale within cities, transforming the way that we get our metal. Now, because DES works on e-waste, it also works on the rocks that hold the metals themselves. DES is a platform technology. We can use it in a range of industries, which opens up a whole new opportunity to make mining the metals we need to reach net zero cleaner, transparent, and more sustainable. If you want copper for electrification, we can get the copper out. If you want nickel, cobalt, manganese for electric vehicle batteries, we can get that out too. And if you want to remove toxic chemicals from contaminated sites, we can do that as well. And now looking longer term into the future, when the world doesn't want to rely on mining in the Earth, and we look to space to mine asteroids instead, we can use DES there too. Because if you're going to be using or going to be millions of miles from home, you don't want to be using something that's going to get vented into space like water, and you don't want to be using something that's going to be consumed. You need something recyclable. You're going to need something like DES. So I'll finish on that exciting thought of space exploration. Let's finish with a simple statement. For too long, we have relied on toxic chemicals and intensive consuming processes to recover the metals we need for centuries to power our industrial growth. We have now the opportunity to break that reliance and make a statement that the environment should not be paying the price for our economic development. The technology that we're developing at DEScycle using DeepTech solvents truly has the potential to change the way the world recovers the metal we desperately need to transition to net zero so that we can have a cleaner, healthier world alongside a prosperous one. We shouldn't accept that it's either or. Thank you.
Good stuff. I think one of the things that makes me so excited about this is that it's been this kind of a painful progression for us over the last, I don't know, decade or so as we started to recognize that recycling isn't really working in general. And we're all separating out our trash, we're getting our cans and bottles separated from the cardboard, and almost none of it is working. And we've, really over our lifetime tried to build out recycling for the cheapest crap on earth, cardboard and plastic bottles. And what's amazing here is you're going after the most valuable stuff. And it seems like the place to start. I think that's just amazing. When you talk about the way that DES works, I guess what I think maybe would be helpful to just pick apart is like, how does that compare? You talked about the smelters and the incineration, but are we going to be able to get all that metal back from data centers? Are we going to get it out of phones? I mean, how much of it do you think you can really get to?
Well, with electronic waste, we can get everything.
Yeah.
So the great thing about electronic waste is that it's all native metal. The metal's right there, ready to be recycled. What we need to do is do it more sustainably. Okay. So we already know it works by putting it in a smelter. What we're saying is you don't have to do that. You can get the same output with the chemistry that we've developed.
Because a smelter is just going to literally burn everything, send most of it up the smokestack, and then leave you with a little bit of the metal. And so with DES, you get rid of the smokestack.
Yeah.
What happens to the other stuff?
So if you take something and you incinerate it, you evaporate everything, and you put metals into the atmosphere, you burn plastics, you create toxic chemicals.
Yeah.
What we're doing with DES is we're using our chemistry to allow us to separate the parts of the electronic waste so that they can be recycled, and the bits that we're interested in, all of the metal components, they get separated out, and then they go into our solution, and then we can physically recover that metal without touching the plastics and everything else.
Wow. And what's the scale of the market? Do you have a sense of like how much metal we could recover? How much is going into electronics in the first place?
So it's the value of raw materials makes recycling electronic waste very, very economic. It's a $60 billion a year annual value of the contained metal. That's likely to double in the near future.
$60 billion a year of metal goes into electronics.
Yeah, exactly, and that's metal that we have to then take back out of the ground because we're putting 80% into landfill.
And how much of it's being recovered right now with the smelter?
That's 17% that I'm talking
17%.
about. Yeah.
Wow. Amazing. Folks have questions? I can keep asking questions, but if you guys have questions, they're probably better. So, over here.
Hi, thank you for the talk. Super interesting. What's the ratio of the liquid to metal you're able to pull out?
Mm-hmm. Yeah, I'm not going to say what the ratio is, but what I will say is that because it's not consumed in the reaction and it's a medium, it means that once you've put it in, you rarely have to replace it. So you constantly regenerate and reuse it, which is a complete change, 180 degrees to what normally happens. If you want to extract metals, you normally put acids. Those acids are consumed, creates carbon dioxide, and you don't have that acid anymore. With DES, it's the opposite. It's always there. It's like that cup of coffee I discussed.
Wow.
Hi. So obviously there's already a lot that's gone into landfill. Is it economic to fetch that out, or is there a plan to be able to find what's already there to recover it?
Sorry, for the electronic waste? Or? Yeah. So in landfill, I don't think we've really kind of taken a look. I think if you can get it back out of landfill and make it in a kind of environment that we're able to process, absolutely. In fact, it's probably even more valuable than what's being produced now, because back In the past, we'd use a lot more copper, a lot more gold in some of the circuit boards, so it's incredibly still valuable. We've just not looked at it from that perspective yet.
I've seen videos of like, I don't know, kids in Southeast Asia trying to scrape the gold off of circuit boards,
Yeah.
And I mean, it's a nasty business to be in. Wouldn't wish that on anyone, but it's amazing to think about being able to do it in a, non-toxic way. So, yeah, over here.
Hey, I want to ask if there'll be a process for detecting whether the e-waste that's going to be recycled is still operable, and if that is going to be reused, or if it'll also be recycled into raw materials.
Sorry, could you repeat that? I couldn't hear the question.
I wanted to ask if the e-waste that's going to be recycled will have a screening process before being recycled to detect whether or not it could still be reused by itself, or if it will...
There's I can answer that. We have a lot of problems with that right now. It's not going very well. But what's happened in some markets is they've sort of sprung up a sort of intermediary companies that are trying to intercept the e-waste, see if they can refurbish it, and then remarket it or take it to a market where it's still useful. So that's your old phones and computers and things. And I think that's starting to improve. It's not going to impress anyone, I think, at this point. It's not at a scale that's meaningful, but these guys are kind of downstream of that. So it wouldn't be what they would do, but right now you can see like cell carriers and stuff have these buyback programs and things like that, and they're trying to intercept that stuff and get it back into the market so it can live longer before it gets thrown out. But the truth is, I think there's very limited possible returns on that. By the time somebody wants to throw out a computer, there's a very small market that's going to find it useful in a lot of cases.
So this is linked a little bit to that first question, or the question that we just had. How much processing needs to be done? Let's say, just take your average PC, for example. How much processing needs to be done before it gets to your process where you're extracting the actual core minerals? Because obviously there's the plastic, there's the rubbers, there's a whole bunch of stuff that goes with that, which you're not interested because you're interested in the valuables. So how much processing needs to be done before it gets to your stage?
Yeah, look, that's a good question. I think it'd be useful just to explain how how our technology can be adopted, because all of that disassembly of electronic waste is already happening. Like there's the groups that we're working with. We've got a joint venture with a recycler in the UK to co-locate our first plant. It's really all about integration, because groups and companies taking our electronic waste have to separate it into the different waste streams, the plastics, the glass, the components. It's already being dismantled. What we're offering is, rather than the opportunity to send it to a smelter, where they don't get paid that much money, goes into high incineration, creates pollution, and transportation of hazardous waste, we're stepping into that point and co-locating our plants with existing recyclers, so that rather than putting it into a smelter, they're recycling it on their own site, having done all the dismantling that they would have done anyway.
Yeah. Awesome. Thanks for coming out, Leo.
Great. Pleasure.
Thank you, guys. Appreciate it.
Do you need this?
I don't need that. Thanks, you guys. I think there's a short break before someone else is coming on. I'm not sure what's happening next, but I really appreciate you spending time with us, and we can stick around, hopefully, and answer some questions if you guys have more. So thank you.
Thank you so much, Pavlos. Thanks to Pavlos, John, and Leo for a completely fascinating morning. I don't know about you, but I was taking pictures of all of their slides to investigate later. We're going to have a short break. At 11:30 is our next talk, so you can relax and refresh for a bit. We're going to be covering From Atoms to Materials with Digital Tools with Matthew Rosensky. So back in a few. See you then. Brain's calm, ready to go. We're going to be digesting some new materials. I hope you're ready. We're talking about from atoms to materials with digital tools. Please join me in welcoming onto the stage Matthew Rosinski.
Thank you. So, materials are all around us. And I'd like you to spend a few seconds thinking of the one material that has had the biggest influence on how our society is today. You might think of material, thank you, like silicon for solar PV or for compute. Or you might think of a molecule like penicillin for healthcare. So please just spend a few seconds thinking about that, and then I'll give you my candidate. So here's my candidate. It is zeolite Y, and is the basis of the petrochemical industry that has dominated modern society since the mid to late 20th century. Zeolite Y is the basis of the fluid catalytic cracking process, and every single molecule of petrol on the planet passes through zeolite Y. Now, of course, the petrochemical industry has been a decidedly mixed blessing. However, I think this illustrates the point that one material can make a transformative difference. Now, zeolite Y is an example of a class of materials called crystalline inorganic materials. So a crystalline material has a regular structure that repeats periodically in space. And an inorganic material is drawn from a chemistry that is not the chemistry of carbon with hydrogen and a small number of other elements. So imagine we're 100 or 1,000 years into the future, and the same audience is asked the same question: what is the material that made the biggest difference in showing society that we can move beyond fossil fuels? We could get our power in a different way. What would that material be? So again, my answer is that that material would be lithium cobalt oxide. This is the cathode of the lithium-ion battery, and it was shown to work by the very brilliant Professor John Goodenough. Lithium cobalt oxide gave us phones, gave us laptops, gave us electric vehicles, and it showed everyone in society we could really live our lives in a different way. Now, like zeolite Y, lithium cobalt oxide is also a crystalline inorganic material. And so perhaps, given their importance, we should consider how we can get better at finding these materials. And that's what my talk today is about. It's about accelerating the discovery of crystalline inorganic materials, materials like zeolite Y and lithium cobalt oxide. So these materials come from exploring the inorganic chemistry of the elements. And the elements are drawn from right across the periodic table. And this makes the challenge of finding those materials intense. So clearly, there is a huge scale of possible choices of elements to combine. And there is a huge range of possible interactions between those elements, possible types of chemical bonding. And if we consider the opportunity there, we can perhaps contrast with biology. Now, biology is fantastically powerful, but actually, it's based on a relatively small number of elements, operating in a rather narrow parameter space and using a quite narrow set of bonding interactions. So imagine if we could harness the full potential of the entire periodic table to create function. There's a lot of opportunity there, but of course the scale and the complexity of finding these materials makes it a daunting challenge. So let's imagine we didn't have zeolite Y and we wanted to invent it. What would we need to do? Well, we start from the whole space of chemistry that I've just shown you, and we have to start making some choices. And I'm going to come back to choices throughout the talk. So we have to start making some choices. So the first thing we do is we have to select the elements that we want. So in this case, we have to select hydrogen, silicon, aluminium, and oxygen from all of the different combinations we could choose. That's choosing our chemistry. But that's, of course, not enough. There are lots of possible combinations of those elements. We have to define the composition of zeolite Y. What exact ratios of those elements do we need? So that's a set of atoms. But even that's not enough either. We have to arrange them in space in the right way. So with the composition, we then need to generate the correct structure. And the composition and the structure together then give the function. So in the case of zeolite Y, you have a hydrogen atom in the composition, and it is arranged in space by the structure of zeolite Y to be a very strong acid. It's actually a stronger acid than sulfuric acid. And the structure also has holes or pores in it to allow the long-chain hydrocarbons in. The acid centers then crack them into the lighter hydrocarbons that we need to use. And it's that connection between composition, structure, and function that underpins the design of materials. So that is our challenge. So how do we tackle that challenge today? Well, here is an example from our own work. Here is a new materials structure: bismuth 4, oxygen 4, selenium, chlorine 2 is the composition, and the structure is shown on the left-hand side there. And this material has the lowest thermal conductivity of any inorganic material. Its thermal conductivity, and remember this is a sort of dense solid, is only 4 times higher than that of thin air. It's interesting if you think about it. So how does that arise? Why did we target that? Well, through our understanding of chemical bonding and of crystal structure, we selected those elements because our insight was that this would generate a unique arrangement of chemical environments that would interact in order to generate vibrations within the solid that moved particularly slowly. And it is the motion of vibrations that transmits heat, and it is that combination, that unique combination, previously unseen, of chemical bonding that drives the low thermal conductivity. Now, thermal conductivity is a very consequential thing. So first of all, understanding it demonstrates our understanding of bonding in solids and has been a challenge to scientists since Einstein and Debye. But also, if you came here on a jet aircraft, you might be interested to know that in your jet engine, that alloy in the blades is actually operating at above its melting point. Right? The gases are hotter than the melting point of the engine. This would be concerning if it wasn't for materials with extremely low thermal conductivity that form a thermal barrier coating over the blade and prevent it from melting. So understanding how to generate low thermal conductivity is a very consequential thing. And we can drive those thermal conductivities down by discovering new inorganic materials. So what decisions did we have to make in order to access that material? Well, many, but I'm going to focus on two. The first one is how to choose the chemistry that we studied, those 4 elements. How to choose them, how to select them from all the options that the periodic table offers. And the second one then is, having chosen that chemistry, where do you look within that chemical space? So even having made that decision of which 4 things to choose to study, there are myriad possible combinations to study in the laboratory. And that's perhaps the most important thing for you to take away from this talk. This is all about finding actual materials by chemical synthesis in the laboratory. And given the scale of the challenge, the scientific community, I think, has done respectably well to find all of the materials that we rely on today. But really, we're a bit up against it. So unlike biology, we have not had a compound generating machine running efficiently for billions of years exploring biological chemistry. The number of examples we have in our hands compared to the potential size of the space is pretty small. And so although our insight and our understanding can take us so far, there's now a tremendous opportunity to intensify the rate of progress by using digital tools, by working at the interface between physical science and computer science. And I'm going to show you an example of how we have done that with my colleagues at Liverpool, tackling the second part of the challenge, which is where to look within that compositional space, for example, of bismuth, oxygen, selenium, and chlorine, to target that composition for synthesis. To do that, we have to be able to compare the energy of that composition with all of the other compositions we could make by combining those elements, to identify that as a particularly stable one, and thus a good target for synthesis in the laboratory. And to do that, we have to tackle the problem of crystal structure prediction. If, for a composition, a combination of atoms, we can work out what the most favorable structure, the most favorable arrangement in space of those atoms is, we can compute its energy, the lowest energy for that composition, and compare that energy to all the other compositions, and work out which ones are the most favorable ones to target. So this is the crystal structure prediction problem. It's one of the foundational problems in condensed matter science. And here is how we have been tackling this up until this point. So if you imagine representing the energy of a particular composition as a function of the positions of the atoms. So this is a contour map with the contours representing the energy. So red is high, kind of blue is low, and purple is lowest. And the energy varies as you change how the atoms are positioned in space, and that's represented in 2 dimensions on the screen. In reality, it's more dimensions, of course, but we're projecting down into 2. And what we want to do is find the arrangement of atoms that has that lowest energy. So the way we do it, or have done it up until now, is we explore the space, which is called the potential energy surface of the composition. We explore that surface using a heuristic, which is a clever strategy of building trial structures. So a trial structure might be one of the diamonds that you see on the map. We build it. It has a certain energy. It's maybe not exactly the optimal one that we can get to from that structure. So we do a second step, which is the little black arrow that you see. It's called local optimization. We sort of shimmy the atoms around, and they kind of move into the best position they can get to from our existing structure, and we call that a potential structure of the composition. And then we do that again. We build another structure. That's the red arrow taking us to another diamond. We do the same shimmy, and we keep going with this heuristic model until we run out of compute time. And then we note the lowest energy that we've got and the structure that is associated with that, and we call that the best structure for that composition and the best energy. And these heuristics are tremendously powerful, but they will never fully explore all of the possibilities. What we have done, by combining discrete and continuous optimization methods, is to consider the entire space of possible structures all at once, and thereby guarantee that we have identified the lowest energy structure. So it's a complete exploration of the space of possible structures and possible energies for a material, rather than a partial exploration of the space, and it offers us guarantees. So we do that by splitting the problem into two parts. The first part considers the entire possible space, but it discretizes the space. So the atoms can't be anywhere in the space. The true space is continuous, of course. They can only sit on a grid of points. And with that assumption, we can guarantee, using a technique called integer programming, to find the lowest energy arrangement. And if we get the discretization right, and there are physical reasoning approaches to tell us how to do that, we can then take this guaranteed global optimum across the whole space, which has been discretized, and then transition to the true continuous space by doing just one local optimization, one shimmy. So the allocation of points in the discrete space takes us directly to that star. That's the lowest energy guaranteed allocation in the discrete space. Then with just one little shake of the atoms, we go right to that purple target, the lowest energy composition. To the lowest energy structure for that composition, giving us a guaranteed lowest energy based on this combination of optimization methods. Now, as with any computational chemistry calculation, eventually if your problem becomes too big, you have too many atoms, or grid points are too finely spaced, you will get a combinatorial explosion of possibilities. You won't be able to do the computation anymore. But because of the way we formulated this problem as a discrete optimization problem first, this is a type of problem called a cubo problem that is particularly well suited to the use of quantum annealers. And so we've shown that you can apply this method of predicting crystal structure prediction to quantum computing platforms, which offer a pathway to overcome this combinatorial explosion challenge. So, coming back to the overall problem, finding those crystalline inorganic materials from chemical space. I've shown you in some detail about one key part of the process. It's this identification of the best composition for synthesis by tackling the crystal structure prediction problem. And we do this with a tool that leverages exact physical law to calculate the energies and exact mathematical optimization algorithms in order to extract those guarantees. But of course, there are many other parts of the problem. We have to be able to choose the chemistry. And we can do that using a machine learning tool that we have built that takes all of the examples that are known of crystalline inorganic materials and allows us to rank candidate chemistries for selection, for investigation by the crystal structure prediction methods that identify the precise compositions for synthesis. And the key point is that those tools all focus on the main goal, which is the synthesis of materials within the laboratory. And so this combination of the variational autoencoder with crystal structure prediction led to a lithium battery material candidate realized in the laboratory. And that's the point I would like to leave you with. We have these digital tools at the interface between physical and computer science. They can exploit exact physical law, mathematical algorithms. They can use machine learning, data at scale, giving a statistical perspective. But they provide support to the decisions by the expert materials chemistry researchers who will synthesize those materials that we need in the laboratory. Thank you.
Thank you very much, Matthew. Do we have time or interest for one question from the audience? We've got a pretty tight schedule to get on to the next talk, but I wanted to open this up. If there's anyone here having heard this very thorough and interesting chat, this is your chance. We've got a lady over there.
Thank you for the great presentation. I'm curious if you have some examples of use cases and applications that you can share.
Yeah, so I've got, just slide's gone. But if I look at the entire workflow, so we have several examples. So we've got examples where we've used the machine learning tool to select chemistry for lithium solid electrolytes, that we then use the crystal structure prediction tools to target actual compositions for synthesis. We then realize those materials in the laboratory. We find new structures previously unseen in the databases, and we then show that those materials can act as solid electrolytes in solid-state batteries with lithium anodes. So that's one example, but I can show you ones from catalysis for net zero. I can show you ones in the space of thermal conductivity and in other spaces as well.
And with the link that you just made with quantum to discretely look at those things, can you articulate a bit more what does it mean actually in terms of arriving to the final goal? So how do you integrate the capability of quantum with your sliced process, and why is it important?
Well, so the discrete calculation that we do, the first step of the discrete then continuous, is encoded as a problem that is a quadratic unconstrained binary optimization or QUBO problem. And we run that on a classical computer. We solve, we get guaranteed outcomes, and we then pass those outcomes to the local optimizer. Now, because it's a QUBO problem, it's well suited to a hardware icing machine like a quantum annealer that can then solve the same problem, and we've demonstrated that on a quantum annealer. So, of course, we run into all the practical problems about noise and all of these things, but it's a proof of concept that it can be run on a quantum computer. Standing here today, you have a problem, you're better off running it on a classical computer, but we all hope and expect these quantum machines will get better and better, and this approach is ready for those improvements in the quantum hardware.
Any other further questions? Yeah, we've got As you can see, the ferns are out, which means we're going to have a fireside chat. This is about transformational science and technology at speed, and we have two absolutely wonderful guests that I cannot wait for you to hear from. The first is going to be Professor Jenny Reed. She's the Professor of Vision Science at Newcastle University, and she's one of the new program directors who's just been appointed to the Advanced Research and Invention Agency, also known as ARIA. Joining her, also on stage, is going to be the CEO of ARIA, which is Elon Gur. So please join me in welcoming both of them to the stage. Good luck.
All right. Can everyone hear us? All right, what a pleasure to be here. I'm Elon Gur, I'm the CEO of ARIA. ARIA is a startup. It's actually a startup R&D funding agency. And like any good startup, we started out in stealth mode because we really wanted to take some time to build our team and really be intentional about what it is we're doing. We came out of stealth mode this week, both with an updated website and a very exciting announcement of our first set of program directors. These are the individuals who are going to come into ARIA as a funding agency and shape the scope and the thesis behind the programs that we fund. We'll be funding essentially constellation of efforts across the R&D ecosystem towards really big breakthrough outcomes. And if you go on our new website, you'll essentially at the top of the page see two bold-faced things. One is a tagline that says ARIA is empowering scientists and engineers to reach for the limits of the possible. And then under that, another bold-faced statement which says we're an R&D funding agency built to unlock breakthroughs that can benefit everyone in society. Now, depending on your background, either those statements sound really exciting and inspiring, or they sound like something we put into ChatGPT, and then threw on the website. And actually, I'm here to say that we were really intentional about that messaging. And so what we'd love to do is share a little bit about why do we feel like we need a new R&D funding agency to think about science and technology breakthroughs, and what do we mean by empowering scientists, and what do we mean by unlocking these big breakthroughs. Rather than me just sharing that with you, I have the pleasure of having on stage with me one of our incoming program directors, so one of the people who's going to be shaping our funding programs, Jenny Reed. And we figured it might be best to just have a conversation. I think one of the things we'll want to do in ARIA is sort of learn in public and share a lot about what we're doing and how we're thinking about things. So we figured it would be more interesting and engaging for Jenny and I to just talk about what we think this is going to look like, and hopefully that'll be really compelling for you all. I want to get to Jenny's background and sort of what she's going to be doing in this program director job, but let me just first frame this question of why do we think the UK and actually the world really needs new ways to fund researchers to think about breakthrough science and technology. And actually the framing is very simple, which is if you look at the story of human progress, it's basically a story of humanity leveraging ingenuity and determination to overcome certain challenges and capture certain opportunities. And that's sort of what moves us forward. And you can think about that in every context, but certainly throughout history now and in the future, there will always be major challenges and enormous opportunities that can uniquely be addressed by science and technology. I would argue that right now, and maybe every generation thinks this, it feels like the stakes are as high as ever, right? The problems we're facing that relate to science and technology are at a scale and complexity beyond what we've ever dealt with, whether that's climate change, biodiversity loss, thinking about things like pandemics that we've obviously experienced, and also the power of technology, and a lot of what's been talked about at CogX, are thinking about these massively powerful technologies that are pushing us beyond scales again and scopes that we've thought of before, AI, bioengineering. And so on one hand, we've got this enormous demand for new approaches and new solutions and new breakthroughs from a science and technology standpoint. What excites us about ARIA is that's sort of the demand side. On the supply side, we've got an enormous kind of army of trained scientists and engineers across the world, but certainly in the UK, who are the people who have exactly the training, whether it's physics or chemistry, we heard from Matt recently, material science, to be able to develop these breakthroughs. And so the question for us is, at this moment, how can we get more out of that talent base to try and address the biggest challenges and capture the biggest opportunities at our time? And we have a lot of reasons to think that there are opportunities to sort of activate that pool of talent. For me, ARIA is really special because there are only a few places in the world that have the concentration and depth of scientific talent to be able to develop breakthroughs in technologies that can change how the world works. And the UK is certainly one of those. And so that's why we're really excited to be launching ARIA right now in the UK. We're going to have sort of a global mindset and scope, but most of the activity is going to be here, and we're going to be thinking about programs that can really benefit the UK in the future. Our approach on empowering scientists and engineers is basically starting with this call we did for program directors. And we launched a wide open call globally, and the application started with one question, which is, if you had the opportunity to direct 50 million pounds of government funding to activate the research community in new ways and unlock breakthroughs, what would you do? And we had almost 400 people apply. We've selected 8 program directors. And so let me introduce Jenny, or I'll let her introduce herself. I'd love for everyone to just be able to hear about your background and why the heck you applied for this job.
Yeah, absolutely. So I'm a vision scientist. I started out in physics. I actually did a doctorate in theoretical astrophysics, and then I moved into neuroscience. I think what fascinated me was the idea that there were mathematical laws and descriptors that would apply to us, to brains, to neurons. And that really fascinated me. And I spent the past 25 years working in visual neuroscience, particularly specializing in binocular and stereoscopic vision. So, we all look out on the world, or most of us look out on the world through 2 windows, our eyes, but you're not aware of that, right? You perceive one unified percept. So somehow your brain takes those 2 visual sources of information and fuses them together, while at the same time, detecting the tiny differences between the 2 eyes and using that to infer depth. So I've used that as a model system to what's going on in your brain when you do that. I've also been really interested in applications of that basic science, right? So that's very sort of basic and abstract and how do brains work. But I'm super interested in applications of the science. So how does vision get altered by particular pathologies or different visual experiences? So clinical applications of my science. One thing I've done is develop a binocular vision test for clinical use in children with strabismus and amblyopia. I'm also interested in the applications in industry, so like novel visual displays, user experience, that kind of thing. So that's my background, and ARIA is obviously a bit of a new direction and a new change for me. I think you asked what led me to get involved, and actually my program's going to be aimed at developing novel ideas in robotics, which may sound a bit like a left turn at this point, given what I've said about my background. But I come at that via my work in insect vision. So I think of insects as like tiny little robots, right? They're incredibly small. They have these very small brains that have about 1 million neurons, but they're able to solve incredible problems. And just the list of things that insects can do just keeps growing, right? It's amazing. They can count. They can make complex decisions based on trade-offs. How are they doing this? And if we could understand how, could we use that in robotics? And that's the angle that got me into this area.
Yeah, so one of the things that we found really compelling about Jenny wanting to do this job was, here's someone who is saying, I actually think ARIA should be doing a program in robotics and I should be the one to lead it, even though she's never worked in robotics. And then you sort of look at your background and you say, well, wait a second, you started in physics and then you went and built this really powerful career in neuroscience, and then you've now applied that in different areas. And so actually, we have a lot of confidence that you looking at robotics can bring something different. And I think it's one of the important things we want to do in ARIA is create opportunities for people to come in with sort of a beginner's mind and fresh perspectives and be able to sort of question the status quo around, like, why is the field going this direction? Well, what if you did this? Where anyone in the field would say, well, that's, of course we're not going to do that. That seems kind of ridiculous. And then you sort of ask why, as you were talking about your background, one of the things that I was wondering, as I think about our group of program directors, one of the things I find is that they seem to be people who are very creative in thinking about science, and that's something they're passionate about. But they're also sort of creators. They want to think about sort of the application. So as you think about when you talk about sort of studying praying mantises in their neural system, but then also applying it to, looking at healthcare and really sort of new diagnostics, what motivates you more, the creativity or the application and creation?
Well, I think it's both, isn't it, right? It's about finding creative new applications. I'm not sure you can make a division between the two of them. I've always been very stimulated by taking ideas from one context and applying them in another. And I think that's what ARIA is going to be all about. That part of the role of the program director is going to be forging connections between communities that maybe don't meet usually, and let's see what we can do when they come together. And we, with the £50 million budget for each program, we have the convening power to really bring people together and fund the ideas that they come up with, right? So it's not just about introducing them, but then potentially empowering them to do something amazing.
When you think about, the approach we're taking as program directors are starting very much like you, saying, let me look freshly in a space, and over the coming months, program directors will be going through from kind of developing a thesis of where there are new opportunities in a broad opportunity space, and then from that saying, here's a very specific funding opportunity. So you're just starting this process. As you come from sort of insect vision and neural systems and you start thinking about robotics, what are some of the things you're thinking about?
Yeah, so I mean, part of me, I'm interested in bio-inspired robotics, so I guess that's most closely related to my immediate background, so that's certainly something I'm interested in. So ideas from robotics maybe in terms of like flight control in drones, what can we learn from flying insects? So that would be one thing. There are really interesting applications. So, for example, we don't always think of robots in biodiversity, but there's some fascinating work being done, and I've just read recently on robots helping human divers rejuvenate coral reefs by actually planting, seeding the new coral, right? And that's something repetitive, and you need a huge amount of it. So can robots help us there? So I'm really interested in these unexpected applications, perhaps, of robots. I'm also interested in, could you make a robot biodegradable? So again, insect-inspired robotics, you think of small swarming robots, and the whole point of insects, I think, is that they fail a lot, right? They're sort of, you generate large numbers, they're not very robust, they fail, they die, but that's fine because there are lots of them. But obviously you don't want to be like leaving large amounts of robotic litter around. So could we have a biodegradable robot? How complex could it be?
Yeah. I love this. I'm gonna pause because for me, I think a lot of the programs that we develop, the successful ones, will have some insight. It'll be one thing where you say, well, here's something interesting and different. And just as you were talking, saying, well, the cool thing about insects is they're born and they die and there are lots of them. And actually, I don't know many people in the robotics community are saying, like, the whole thesis of what we're doing is like the insects, there are going to be lots of them. And, those sort of, yeah, I think that's a great example. One of the things that I'll share with sort of the audience here that is both, I think, exciting and terrifying for us, for ARIA, is the idea that, we're built to not try and develop things that could lead to sort of a marginal improvement. I like to say, if an ARIA program leads to sort of a new product that one of the people that we fund develops, or even sort of a new company, that's great, and we'll sort of take the win, but that's not what we're here for. We're here to really create sort of transformations, entire new industries, entire new capabilities. And we have the benefit of the sort of inspiration from a policy perspective. ARIA was built inspired by DARPA, the funding organization in the US that really catalyzed entire new areas like, frankly, computing and the internet and GPS technology, more recently mRNA, arguably. And when we got our program directors together for the first time, there was a conversation around what is the job of the program director, and this line came out, civilization scale, catalyzing civilization scale transformation. So as you think about developing a program, how do you know, how are you going to know if it's big enough, the vision?
Yeah, that's a great question. I think maybe backing off slightly from the idea of changing entire civilizations at this point. And one of the things that's definitely very attractive is the idea of doing joined-up research. So over the scale of a program that maybe is initially 5 years, I mean, that's a long time, and £50 million is a large amount of money. So you can really afford to think big in a way that researchers typically can't. So I'd really want to encourage people to reach out. And I think, again, talking about the convening power, so maybe you've got an idea, but it would depend on all these other things that you can't do or don't know where to start. But maybe as a program, at a program level, we can solve with that. We can help that. And I think DARPA, again, has got a great track record of really thinking for the long term. So even though its program directors have worked over 5 years, they've had a trajectory that has kept going over 10 or 20 years to really push forward into, say, the personal computer.
Yeah.
And that's something I really hope we can do.
I think it's a really good point, right? So ARIA was created by Parliament, and specifically there's a directive to think about, sort of a decadal time frame of impact, but also to recognize that, if we're going to make these big, bold, kind of speculative bets on transformative technology, you don't know, when you start sort of a bold expedition, if it's bold enough, you don't know whether it's going to succeed or fail in the early days. And so it's really important, as we've talked about this internally, to think, we should be much more scared that we don't set our ambitions high enough than that we set our ambitions high and we don't make it. One of our advisors for ARIA is Özlem Türeci, one of the founders of BioNTech, sort of, the other big, success story in terms of mRNA. And when you hear her talk about their story of mRNA vaccines, it's sort of a decade-long journey, and actually really inspiring for ARIA, because it went from basic science to thinking about understanding clinicians and regulatory, and they were focused obviously on cancer. And the pandemic actually shifted the trajectory of the viability of that technology. And one of the things in the story that you hear is, if you pause somewhere in the middle of the story before it was successful, it's actually hard to differentiate between that versus an attempt that was just as bold but didn't succeed. And so I think it's one of the reasons it's so powerful for us to have a portfolio. We talked about getting the program directors together. And so how do you think having the other program directors, so we have folks, with expertise in electrochemistry and computer science, electrical engineering, how does that dynamic play in?
Yeah, that's one of the things I'm most excited about, actually, because the program directors are a really great team, and I'm so looking forward to working with them. And I think it's going to be really exciting to try and build synergy between the programs. And talk to each other about what we're doing. Oh, that's amazing, because that would actually plug in really well. So, for example, Suraj, another one of the program directors, is looking at novel compute technology beyond the transistor, maybe thinking about organic computing, for example. So, well, if I'm thinking about bio-inspired robotics, there's room for some synergy there. And I think those kind of connections are what's really going to make the whole be more than the sum of the parts.
Yeah. I'm probably going to date myself, but I think about that TV show Voltron from back in the day, my childhood, where you had all the different sort of robots coming together. I think about that when the program directors are interacting. Maybe one last thing that's worth chatting about, and I don't think we've had many opportunities to talk about this, but you and I, so Jenny, you're, in addition to your research, you've kind of served some administrative capacities in the university, including being a co-chair of, I guess, the ethical review, or a deputy chair of the ethical review board for, I guess,
Faculty of Medical Sciences at Newcastle.
Medical Sciences. Obviously, so many of the opportunities and problems right now in technology are socio-technological. And if you actually look at our website and some of the bold ideas people are thinking about, whether it's in robotics, or climate interventions, or neurotechnology, there's a really big obligation for us to think about sort of what's our role as responsible sort of stewards of shaping these technologies. And I'm just wondering, from your experience doing the ethical review work, what have you learned going from being a scientist to doing that work that might help us there?
Well, I think 100% committed to the importance of patient involvement and engagement, and talking to end users, who are you doing this for? Is it what they want? What concerns do they have that maybe you haven't thought of? What ideas can they give you, right? So I guess that ties into ethics, but it's more than that. It's about involving people really early on at every stage. And that's something I think medical research has got quite good at doing. And I think that's something, part of the culture we want to embed into ARIA. And certainly ethics good practice as well, of course.
Yeah. How are you thinking about this for, as you think about robotics? How do you think about sort of engaging people there? And maybe because we have a chance to be in sort of a conference, what are the types of people you want to hear from?
So you just mentioned the ethics point of view. So there, I guess we'd be talking to people on the street, right? What would you like robots to do? How do you feel about robots? What concerns do you have? From the scientific and technical point of view, I am completely in discovery mode at this point. So I want to hear from basically everyone. If you're working in robotics or if you're not working in robotics, but you're working on a technology that you think might have potential applications, get in touch, absolutely. I want to hear from everyone, I think.
It's so funny. It feels like you both need to hear from people to imagine where robotics might go and say, what do you want, what do you want and what do you not want based on how you can imagine. And it sounds like you also want to hear from people to say, well, forget about what people want. Tell me what you could imagine at the same time. And I guess that's part of your job is to assimilate all that information and think about what's something that's bold and new and pushes the boundaries but does it responsibly.
Exactly, I think that's it. And at this point, we're very much in the information assimilation stage, and then later on, we'll focus down more narrowly.
Yeah. Jenny and I talked about the biggest risk of this panel was not that we didn't really do a lot of coordination on the questions, but more that we're going to run out of time, which I think we're getting close to. I will say we have on our website at ARIA a list of all the program directors, the questions that they're exploring, kind of these broad areas. And then as they move forward and do this sort of engagement and really think about the opportunities, we're going to be putting out documents that really more clearly say, well, here's sort of an emerging thesis. We have one of them for one of Jenny's colleagues, Suraj, on the website now around alternative computing. So if you're interested in this area, go to the website, follow along with Jenny, and see when she puts out that next thing. And there will be opportunities to respond to that and sort of inform the funding program that gets shaped from that, which is really exciting. I feel like I've been asking all the questions, so maybe as we close, anything else to say or anything questions for me?
Yeah, what would you like people to be saying about ARIA in 20 years' time?
Well, first of all, I think it's the right time scale. I think in 20 years' time, and we have this paragraph on a website which resonates with me, which is, something should have emerged that is globally significant and really centered in the UK, a new technology that's out there in people's lives or a new industry that is just massively important to society, and that there's not sort of a study that says, here's how this was linked. It's sort of causally obvious that it came from ARIA. And so that's the generic goal. I mean, now that we have you and the other program directors, I want people to say, wow, remember that early conversation that Jenny had about thinking about robotics? The UK right now, biodiversity in the UK right now, just because you brought up biodiversity. So this is one example. Biodiversity in the UK right now is, I think, 40%. I learned this at the Natural History Museum. I think it's 40% of what it was pre-industrial revolution. It's going up because we're working on it. Wouldn't it be amazing if in 20 years someone could look back and say, actually, it turns out through vision science and robotics, there was a technology that helped increase biodiversity back up to 80% of what it was. And that actually pushed the frontiers of robotics to create a whole new industry that's being applied, in manufacturing and other spaces. Maybe that's the narrative. Maybe it's, Jacques who's thinking about neural interfaces and there's something similar or something around electrochemistry and climate. But I hope that's where we end up.
Yeah, me too. Sounds amazing.
Okay, I think they're going to kick us off stage. Thank you all. I'm sorry we didn't have time for Q&A, but we'll be around and very happy to chat with anyone here.
Thank you very much, Elon and Jenny. That's amazing. Thank you both. Yeah. So nice to hear some positive news, right? Particularly in science and innovation. It's not always the way, but it is today. We've got a few minutes. We're just going to clear the stage. So we'll be back on at 12:35 if you'd like to consult your watches, take a break, have a stretch, etc. Have some water. We've got Miles Kirby coming on stage to lead a conversation about how to bring deep tech to the world. Cover that in 20 minutes, right? Good luck. It's going to be pretty exciting. So hang tight. We'll be back in a flash. Still 2 ferns, but now 3 chairs. That's innovation for you. Okay, so we are on for our next panel this afternoon, how to bring deep tech to the world. Joining me on stage are going to be Elaine Lukes, coming on out, followed by Miles Kirby, who's going to be chairing this event, and Ian Lane. Please join me in welcoming them all. Come on. Good luck.
Well, good afternoon, everyone. It is wonderful to be here at CogX, and we are going to be talking this afternoon about how to bring deep tech to the world. And deep technology is often coming from deep research, from academic founders, from engineers. And so we've got a fantastic setup here in Europe. So we often sort of look at sort of the US and other geographies. And, but here in Europe, we have 5 of the 10 top universities in the world. As far as STEM subjects, 28% of students cover STEM subjects here in Europe versus around 18% in the US. So we've got a sort of great raw materials there. 43% of the world's top cited research comes from Europe. And between 2015 and 2020, 6,600 companies were spun out of universities. So fantastic raw material. However, there is still a very high failure rate. So over 70% of companies between seed and Series A typically fail. And this often isn't because the technology doesn't work. It may be because the business model doesn't work, they can't get funding, etc. So there's actually quite a lot of waste in there, and the process is still effectively being worked through, if you like, on how do we best commercialize technologies. And that's what we'll spend some time talking about this afternoon. But however, if you can get this right, there is huge value here. So last year, PitchBook did a report, and there was 189 deep tech unicorns with a value of around $670 billion. So if you can do this right, there's real value here. So I'm delighted to be able to have a couple of wonderful speakers, which will have introduced themselves in just a moment. But Cambridge, where we are all sort of based, is a fantastic hub for deep tech innovation. And so for the last sort of 30, 50 years, deep tech companies have been spinning out from ARM to a number of the sort of big sort of biotech companies as well. So it's a real hub for deep tech. And so we think that it's a great exemplar of how to sort of bring deep tech to market. So with that, I will ask Elaine to do a quick intro.
Certainly. Hi, good afternoon. I'm Elaine Lukes, and I'm an investment director at Cambridge Enterprise Ventures. I lead on the deep tech investment side, and I started my career in early stage tech venturing actually back in 2001, interesting time, just after the dot-com crash, which probably most of you weren't born then. But I focused then on A's and beyond, but when I joined Cambridge Enterprise in 2015, I started focusing earlier on seed and pre-seed, which it's enormous fun. My background, I'm a PhD in physics, and then I trained as a chartered accountant, which is actually quite a good background for going into venture. And it is great being back, speaking to academics at the first stage, capturing that enthusiasm and looking at what can be done from their technology.
Excellent, thank you. And then on my right, we have Ian.
Afternoon, nice to meet you all. So my name's Ian, I'm a partner of Cambridge Innovation Capital, a deep tech and venture fund investing in deep tech companies focused in and connected with the Cambridge ecosystem in the UK. Currently investing out of our £225 million fund. We write checks ranging from sort of £1 to £10 million and longer over the lifetime of a company. I've obviously been working in technology and investing over the last 20 years, which means I guess I've been in a privileged position to see how the UK venture ecosystem has evolved, and it really has changed a hell of a lot over the last 10 to 20 years. So I'm looking forward to the discussion today.
Good, thank you. And then I'm Miles Kirby, I'm the CEO of DeepTech Labs, and I'm sort of sat between these guys because, as you'll discover, we've got sort of Cambridge Enterprise spinning companies out of the university. We've DeepTech Labs is an accelerator helping companies go between seed and Series A, building sort of the ecosystem around those founders. And then we've got CIC, who's doing Series A and later. So we've got kind of an interesting sort of set of folks to sort of talk us through from sort of the very beginning through to hopefully the large expansion stage. So, so with that, maybe what I'll do is, if you could tell us a little bit around, right from the beginning. So you've got these great academics, and they're in a sort of a darkened lab doing something really interesting, and they think, I might like to do a startup. So what happens next?
Okay. Well, I think I probably need to give a bit of a background of Cambridge Enterprise and what Cambridge Enterprise does, because there's several strands to it. We're a wholly owned subsidiary of the University of Cambridge. And Cambridge Enterprise as a whole is there to help commercialize technology emerging from the university. Now, there's several business units, but the two that are most relevant are tech transfer, and everybody's heard of tech transfer offices. But there's also the investment arm, which is Cambridge Enterprise Ventures, and that's where I sit. So in terms of where do you start, often our deals come in through the tech transfer team. So academics might approach our tech transfer team and say, I've got this technology, I think I can patent it, I think it can do this. So the tech transfer team will spend some time looking at that, evaluating, actually, is it something unique? What stage is it at? What's its TRL level? How much? Is it really pretty early? And they'll also look at what is the commercialization opportunity? Is it a license or is it a spin-out? And they can't make the decision on it's a spin-out. They can strongly steer towards licensing, as a lot of stuff is licensing. But if it's something that the inventor really wants to push to a spin-out, they'll send them to our team. So what I get is usually my first meeting is with people with some technology, and sometimes, but not always, with a vision, because sometimes people will say, I've got this and I think it can do that. And because I focus on the physical sciences deep tech side, what you often get is technology that's an answer, but actually what's the question you're asking of that technology? So our team will spend time looking at the people, because you need drive to do this. It's a really, really hard process to take an idea. And I think it's often underestimated just how brutal the process can be. But we look at the people, and quite often we need to help bring in people. We look at the business plan. What is this a scalable business? Because what we're trying to achieve within the ventures team is we want to create spin-outs that are phenomenally successful, that will be generating great returns for the investors, which include us, because we do invest, but will also have a huge positive societal impact as well. So we've got the double bottom line of financial return and impact. So making sure that our companies, if we want to achieve that, we need to make sure we are only spinning out and investing. It's not just spinning out and hoping that Ian will come along or Miles will come along. We put our money where our mouth is. We invest the university's money. We have to make sure we're investing something that other investors are going to say, this looks great. And I think we do that pretty well, because our spin-outs have actually gone on to raise, to date, it's £3.1 billion, which is a huge amount to have raised. And I think in the context of this discussion, what's really important is that it's not just we create a spin it out, say, hey, market, have a look at this. You have to build, and you can't build alone. You have to build within an ecosystem, and I think Cambridge is a fantastic ecosystem. So I'm talking to Miles a lot, I'm talking to Ian a lot, I'm talking to the other investors, and that ecosystem is really, really critical. So I'm sorry, I've covered quite a bit there, but that's how it starts.
That's great. And so then when we sort of look at as you were kind of saying, this is a team sport, right? So sort of different players come in, the existing sort of early investors continue to support the company, new investors come in, and the needs of the company changes somewhat over time. So we, with me sitting in the middle here, so there's a number of companies that Cambridge Enterprise has funded, has got started. They've gone from a raw technology, and where we come in is we want to see the technology is starting to work, some existence proof. And then the game changes somewhat. So instead of at the early seed stage, you're saying, I've got this great technology. One example, quantum interconnect. We think this will be great. We want to see some early proof points that's going to work. And then we've got a little bit of a shift where it's like, okay, technology is working. The idea and the potential is there. How do we now actually build a business, right? So how do we work out which market do we go after? What business model should we use? And of course, with a lot of these new technologies, there isn't necessarily an established model. You may be displacing someone else. There's also, you can leave massive amounts of money on the table if you're just doing a software license, but yet you're discovering a brand new material with billions of revenue behind it. So what we do is we invest in companies at DeepTech Labs, and we bring them through a 10-week accelerator program. And so we bring this ecosystem together. So experts from around the world who have already built deep tech companies, who've got the scars, who've got the experience, who've got the network, to be able to help these companies to work that out. And often the academics and engineers are brilliant in their field, but they may not have run a company before. Most likely they haven't. We do have some repeat entrepreneurs, but most of them are first-time entrepreneurs. So we think it's really important to bring this whole ecosystem around these companies to ensure they're successful. So we've got 400 experts that we bring in to talk to them and advise them, work one-to-one with them, and then we do a demo day at the end with, last time we had over 350 people came along, over 200 investors, to expose those companies to the larger ecosystem. So effectively we've got the academic founders of, I think I've got something interesting, get started, get funded, then sort of come through our program, so going between sort of pre-seed, seed, getting ready for Series A, and then Ian comes in. So maybe Ian, you can talk about what you guys do.
Yeah, thank you, Miles. So it's no surprise that for a deep tech company, a Series A round looks completely different compared to an enterprise SaaS company or consumer internet startup. I mean, I think that's a given. But how do you define that? What is so different? And for me, it really is the transition from sort of a technology through to a product. And exactly, it's not even the case of that product being purchased by multiple customers. Like I say, that's probably coming a bit further down the line. But it's how that transition from a technology to a product has been made. Because if it's just been done by a group of very smart technology-based founders in a room locked in a basement somewhere, that it really isn't the transition from a technology to a product. That's just that's something else. What really we're looking for is that the team have really engaged with, spoke to, and listened to customers to make that transition, and hopefully iterated on that such that the technology can move to a product. Because all too often, the sort of that productization step is either lost or just done sort of in a sort of academic way without, as early as possible, getting out there and speaking to customers and being very open that this thing, the product maybe even not be built yet, but that's the direction. So that's really the key thing for us that we're looking for. And there's obviously everything else that we're looking for across the team, but that transition from technology to product done in a way, listening to customers is really, really key.
And I think there's some great examples there of one company that we've worked with together who said, we're going to go here, and we start talking to customers, and there's kind of a product halfway to that end product, and customers say they want that now, and they're going to pay for it, and it's a simple, okay, great, that's fantastic feedback, let's go after that, right? I mean, it's not quite as straightforward. There's a lot of considerations around that. But I think that feedback from the market is really critical. And I think that actually is where a huge number of companies fail is, again, it's not the technology, it's about finding the right market. And then maybe, when we talk about, moving from this kind of, academic and engineering building the best widget to sort of, if we build it, they will come to, well, actually, that's not going to be the case. We need to figure out, what are the right markets. So So interesting talk. We were talking sort of, in the back there just a little bit about this. Is how do you get the right talent in? And I think, when you look at the US, which is often sort of taken as a poster child for innovation, the very best and the brightest coming out of universities are going into sort of the entrepreneurial space. Historically, folks in Europe were maybe more on the finance side or consulting side. I think that's starting to change. But would love to kind of get your opinion. How do we bring the right people in? Are the people out there? Is this building the ecosystem? I mean, how do you think about this?
I think absolutely people are critical. And as you say, you've got, maybe the academic, more technical inventors and the founders. And yes, maybe they don't have the business side, but they've got the passion. And I think it's actually, you've got to bring in somebody who can work with that passion. You've got to understand what it takes to spin a company out. So I think where we are behind in the US is having, if you go and take a job in the Valley, you're probably going to be reasonably relaxed if you shift your entire family over there, that if that job doesn't work out, there are plenty other ones. It's not the situation, it's not the same situation in the UK. So Cambridge, I think, is probably the leading place. I know that others will maybe dispute that. But we have, obviously you've got the university as the base. We've got several major companies that are there now. You need these companies, you need all the startups, so you've got access to the talent, but you need to encourage people that have been there and done that, ideally with a startup, because going from a successful massive company to a startup is a very much underestimated how difficult that is. So I think if you have an ecosystem where people, there's a buzz about the place, there's lots of opportunities, there's lots of talking. I mean, Cambridge is just all about network of networks. You go and you have a chat with someone and say, oh, you should chat to someone else. So I think building that out, now logistically, Cambridge has a huge issue with traffic and housing, etc. But I think if nowhere is going to be the next Silicon Valley, but I think we can have somewhere that emulates it to a large extent and really encourages, just attracts people in, because it's that experience that is really, really needed.
Yeah, absolutely. And again, that whole ecosystem of sort of startups, funding, advisors, space, housing, roads, etc., bicycles. So what's interesting, though, I mean, obviously in the early stages, I mean, often I think sort of, a CEO may be good for a certain period, and then sometimes, for the next phase, a different CEO might be the right person. Maybe the academic becomes the CTO or chief scientific officer. And probably this is sort of, more of a crux, of where you are, because you are very much looking for sort of, the company has found those commercial opportunities. So is that something that, how do you think about that and bringing the right talent around, these companies? And do you feel that there's a different kind of CEO required at Series A than at kind of pre-seed and seed?
I think, look, we'll back and work with founders, and if they're capable of going all the way through, some can, some can't, some don't want to, some do. So I think, if founders are willing to learn, and it's clearly a very, very different job being a pre-seed or a seed founder to a sort of Series B, Series C founder, raising hundreds of millions of dollars and deploying that capital. So if founders are capable of doing that, we'll work with them to do that. Key for us, though, is that first CEO, changing a CEO between sort of seed and Series A is very, very, very hard. And so ideally, the same CEO will take the business up through that startup phase, and then if it's the right time to change for the scale-up phase, I think that's fine. But yeah, changing the CEO at that early stage is a challenging. So that initial evangelist needs to be the person who can take it through and have that. I mean, we tend to call it sort of entrepreneurial muscle. Just as you said, Elaine, it's a challenging process through those early years, trying to make the evolution from technology to product and speaking to customers, and so having that muscle. So that's the most important thing. I mean, I think. When it comes to, talent in the UK ecosystem, and so like I said, we look at startups and we look at scale-ups, and I think we've got plenty of examples now for scale-ups where we've got phenomenal talent from all the way around the world coming to join our businesses that are, like I say, well capitalized, and so I'm not saying there's not more to be done, but I think our companies in the UK with phenomenal technology can attract phenomenal talent at the later stage to help them scale and quite frankly, be massive companies. Where there clearly is still a challenge is at that earlier stage. And I think, as you said, the ecosystem, the network, and ways of doing that. I think one aspect for me that I think has changed a lot in the last 10 years is the prevalence of repeat entrepreneurs in the UK. So I think 10 years ago, I think founders often used to start a business and they were sort of one and done and then moved on, whereas now we're seeing them coming back and starting multiple businesses. I think one of our founders in our companies, I think it's fifth or sixth startup. And so, and that kind of experience is really, it's hugely attractive to get other people and amazing talent join some of these early companies. So I think that for me is not only are those people experienced, but also it's a really attractive for people then to try and join those companies when they see that experience and see that as success, quite frankly.
And I think on this ecosystem and these kind of repeat entrepreneurs, I spent 20 years in California. I came back in 2012 to the UK, and it was really quite interesting to kind of see the ecosystem in the UK versus the US. And I think in the last now 11 years, there's been a dramatic sort of uptick in the activity of the ecosystem, on the sophistication. I think seeing serial entrepreneurs come back, and also this really collaborative environment. And I think that's what you need. And often, we talk about the CEO, but also having sort of the right board, having the right chairman as well. And a really good chairman can be game-changing as well, to be able to help to sort of coach that entrepreneur as they come through. So, I think as a larger ecosystem, it's something you really need to focus on, is how do we draw more of these great people back in to help serve the next generation of entrepreneurs. And I think one thing that we found at DeepTech Labs is, because we're asking people to volunteer to come talk to our companies, and when we got started, I was quite worried. Are people just going to say, hey, look, I'm running a huge business, I'm too busy, I'm sorry, I'm not interested. But actually what we found is a huge number of people are saying, I wish I'd got this support when I was doing my startup. I've made so many mistakes, I've learned so much, and I would love to be able to give back and help. And plus also, actually, what we find is sometimes the folks that are running these big businesses that are more mature, they really miss that early stage, that excitement of, okay, we've got a new technology, how might we take it to market, versus how do we kind of turn the handle on this really big business.
If I could just add, because I think this is where the University of Cambridge really does it differently, is you're absolutely right. It is an enormous challenge to go from, hey, I've got an idea, to a successfully funded spin out, that Ian says this is great. And what effectively we're doing is we're working, I will talk to investors, for the founders for 2 or 3 years before we actually say, right, okay, you've been developing, you've got more grant funding, your TRL level is higher, you've got a better idea of what you're doing. And that time is so important. And some people come in and say, yes, we'll work with you, we'll take some sweat equity and we'll build this together. And immediately you've got dilution, you've got somebody who's basically there for the money. So I think that part of it, I would like to say, I think that part is so important, because it takes time, and not rushing in and maybe going down the wrong direction. Being able to see with the market.
Very iterative process, right? It's a learning process.
It is.
Yeah. Good. So we're down to the last couple of minutes. So I thought what I would do as we start to kind of get towards wrapping up the session is, this is an interesting area, because there is no one solution that magically works. We're still sort of evolving this ecosystem and this whole model of spinning technology out. So I'd love to hear maybe Ian first on this one. Is there one thing, or is there, what would you do to be able to sort of ensure much higher success rate for this kind of conversion of sort of raw ideas into real businesses that can have some major societal change?
So I think for us, it would be getting really strong commercial product and sales expertise into the business early enough, because that, like I say, that really helps with those customer conversations. It's sort of listening to. A lot of people can talk to customers. It's that rare breed that can then listen to actually say what the customer wants and then go back and put an extra wheel on or whatever.
And even then synthesize it into something that actually works, that they would buy, yeah.
So that listening skill set is so valuable. And so if we could work out how to get more of that talent into our companies earlier, it would be a lot better than sort of maybe going down a route and then finding out further down the line that it's not the right commercial approach.
Elaine, what about you? What do you think?
Well, I think you need to find more sources of non-dilutive funding in the early stages so that you could, companies very rarely go from A to B. They are in a straight line. They'll go in a zigzag, and that costs a lot more money. And it's right they go in the zigzag because that's you finding out what the market wants. So I would say getting that funded is from grant funding as much as possible, because that will then allow you to have a technology that will then, and to a stage of development, which will allow you to draw in that talent, because that's quite hard, bringing in the talent before you've got the product ready or you can really see what the visibility out to market is. So it's sort of bottom up to attract the talent that's going to then take it.
Thank you. And then I think from my side, I think it's really around building this ecosystem and making sure that you've got the capital, you've got the entrepreneurs, you've got the whole team that can go around them, this support community, and also these clusters, as you were saying, where an entrepreneur can take that risk and get started. And I think what's hugely exciting here, I think that as you heard me say at the beginning, I think Europe is incredibly well positioned to be sort of the deep tech sort of center of the world, the engine room, if you like, of deep tech. And I think we're really starting to ramp up. I think the model isn't proven yet, and we're still sort of tweaking and improving it, but there's just a huge, huge opportunity here. I think together we can really sort of drive massive societal change, value to our ecosystem. So a really exciting time. So with that, I'll draw this session to a close. I would like to say a huge thanks to our speakers. Thank you for joining us today. Thank you to the audience for listening. And we will let you move on to the rest of your day. Thank you so much for joining us.
Many thanks for that wonderful chat. We have our next talk in 9.5 minutes precisely. It's the future of supercomputing, what lies ahead. And that is with two absolute powerhouse speakers. You might have heard screaming actually a couple of hours ago because I ran into one of them in the hall. I haven't seen her since the pandemic, and it was such a rock star moment that we both screamed. That is Sue Daly. She's a very, very powerful, influential person in the world of AI here in the UK because she brings things together and really helps take action forward. She's the opposite of all talk and no action. She is all action. She's swum the English Channel and just mentioned that she's getting ready to swim around Manhattan. So we could potentially talk about that. She's being joined by Professor Catherine Royce. She's the director of the Hartree Centre, which is part of the UK Science and Technology Facilities Council here in the UK. These two women are going to be exploring where we are now in the evolution of computing power. Really, really interesting. So we'll be back on in just a moment. Meanwhile, enjoy and relax. Having such a fun chat back there, and I thought I should probably bring them out for all of you, so you too can enjoy the brilliant, scintillating wit of our two speakers. We've got Professor Kate Royce and Sue Daly coming onto the stage now to discuss the future of supercomputing and what lies ahead. Please join me in welcoming them. Join.
Well, thank you, Stephanie, for that great introduction. And it's an absolute honor to be here today. I already see some familiar faces in the audience. So it's really great to be here at CogX and to be sitting alongside our brilliant speaker today, Kate Royce. I'm going to ask Kate to introduce herself and talk a little bit about your role, really, Kate, because obviously I know you and I know you really well. But perhaps let's kick off there before we talk about what lies ahead for supercomputing in the UK. Let's start with, tell everybody your role and Hartree's role and where you fit in the ecosystem.
So I'm the Centre Director for Hartree. Hartree is a special research institute, part of UKRI and part of one of the 7 councils, which is the Science, Technology and Facilities Councils, that runs the national labs, and we're part of the national labs ecosystem. The Hartree Centre's vision and mission is to put technology into the heart of UK businesses, whether you're private or public sector. We're here to help you. And that can be with any of the emerging technology that we hear in the news today. So we've had a lot of press releases about AI. It's been very exciting recently. We also look at exascale compute and what that means for industry. And we also look at quantum computing and other emerging techs like neuromorphics, chips, and all that sort of stuff.
So we're talking today about the future of supercomputing and what lies ahead. And I was really, really keen to have this conversation, particularly on this stage, because we're talking AI and deep tech. And we'll probably talk about this as well in terms of why we're having this conversation here, because computing power, computing infrastructure, access to compute infrastructure is already key, but it's going to be even more important for our AI future and deep tech going forward. So we wanted to talk a little bit about where we are right now, the evolution of compute power, and then obviously looking to the future of what's the supercomputing, what's the direction of travel in the near and long term, as well as explore what that could mean for developments in AI, we were just talking about stage in quantum, as well as in other deep tech areas. And then perhaps talk a little bit about, well, what do we need to do to get this right? What do we need to do to realize this opportunity? I was really, really honored to be part of the government's independent Future of Compute review recently, which number of recommendations have been taken forward, and perhaps we can talk about that as well. But this is just emphasized in my mind how important compute and supercomputing is to us right now, but how it's going to be important going forward. So perhaps before we look forward, let's look at where we are right now. I don't want to get ahead of myself. So Kate, let's think about, where do you think we are right now with compute in the UK, with supercomputing in the UK, and what do you think is on the near and perhaps the long-term horizon?
It's a really exciting time, and just hearing you just try and summarize what's going on is hard at the moment. So at the moment in compute, we are at a real sort of emergent period of time where a couple of new technologies are coming out and coming together. One of those is what we've talked about, exascale compute. Yeah. So the exciting thing about that is the speed of processing, the fact that we'll start to be able to do huge large language processing. So this is natural language models that you've heard about in the press. And the other really exciting thing is the emergence of quantum computing and the relationship, which is where people like me are getting really excited, between the classical compute and this new technology of quantum computing. And we're starting to see some really exciting convergences between those two technologies, particularly around the machine learning, AI area, of what we can do with those two emerging tech. So this is the time to be in this world, and it is really taking off fast.
Yeah, I agree. It feels like we're really at the kind of step change of what's possible, but what's going to be possible in the years to come. And I think the Future of Compute review was looking at, well, how do we get this right? So 2 of the key recommendations that came out of the review was one around ensuring we have access to compute power for AI research. We know how key that is to the UK, and not just the UK, but here looking. And we had the announcement yesterday of the new compute resource. I don't know. Do you
Isambard AI is what the new resource will be. So the government's pledged, I believe, 150 million to help with AI research in the UK. And the reason this is so important is because we need a different type of supercomputer. We need one that uses graphical processors rather than CPUs. So this is why we're really excited. I'm going because I'm thinking accelerated GPUs, so I'm starting to say accelerate. It also means that we've got to change how we do our programming. So the next big thing is going to be software development and programming for scalable AI applications. At the moment, traditional way of doing most of our big compute is using CPUs. So the weather modeling particularly, community tend to use CPU-based compute. We're going to need to move that and transform that into GPU compute going forward.
Yeah, so it's not just the hardware and the infrastructure, it's the software and the programming and the engineering that we need to make sure that we get this right as well, and the two need to work together. Yeah. It's a really great, the supercomputing for AI research that was announced yesterday, going to be based in Bristol.
Yes.
Hence the name.
Hence Isambard.
Hence the name. So really, really great to see that recommendation moving forward. The other kind of key, well, there were a number of recommendations in the Future Compute Review. Go and check it out. Obviously not right now, but as your homework. The other one was around making sure we have a path on the road to exascale. So you touched on it a little bit, but why do you think that's so important?
So exascale compute is incredibly important. One, we've talked about AI and particularly large language modeling. We also need it for digital twins, so providing and producing realistic digital twins of the natural environment particularly. And then there's the work within the astronomical and particle physics community where we are starting to produce so much data that the only way we're going to be able to process that in manageable timescales is going to be with exascale compute.
Yeah, 'cause we could really seriously unlock the secrets of the universe in a way that we've never been able to do before. Help with climate modeling, as well as there are industry applications and commercial applications of these technologies.
And one of the biggest, I think, industries is a really good point, is when we talk about net zero and decarbonising our economy, one of the biggest uses at the moment that we have put together for exascale compute is around the chemical and materials industry. They are desperate to find new chemicals, new materials that do not rely on carbon quite as much as we do today.
Yeah. So a question I get asked quite a bit, and you touched on it a little bit with the mention of quantum, which is a super exciting area as well. Kind of makes my brain slightly ache when I work on quantum, but in a good way, folks. I would highly recommend it. Is around, a question I get is around, well, if quantum is the future, then why do we need to be investing? Why do we need supercomputing? Why do we need exascale? And the answer I always give is that these are going to be working together, right? We've got classical computing and quantum are going to have to sit together. But the supercomputing, the exascale compute and quantum together, when they work together, it's like convergence piece again. That's where the real power comes.
Absolutely. And it's, I'm really excited because I was at a meeting yesterday when colleagues within Hartree Centre were talking to industry experts around the value of quantum and quantum classical approaches. And we were showing just that there are certain things that quantum computing will be great at. Machine learning and optimization problems particularly, it will be excellent at. But at the moment where we are, we do need classical compute to check its homework, if you like. And one of the things I saw a really fabulous bit of work on was using a workflow for drug discovery for COVID. Because when we were in COVID, some of you may or may not know, we ran a lot of simulations in Hartree and a lot of the other supercompute centres to see what drugs were out there that would have properties that could perhaps provide medical support for the COVID. And what we found is when we reran that with a quantum kernel for the machine learning part, it was much better at selecting chemicals that were medicines, basically, that were useful, that could be used. So there is definitely, we've got to scale it up. We're still a long way from industry ready.
Yeah.
But we are showing time and time again that we are able to show benefits with quantum.
Yeah.
I mean, we were doing this with looking at cancer screening as well. Quantum computers, again, are very, very good at that sort of image recognition analysis. Again, you wouldn't rely on it completely, but again, we have shown on small data sets that it can pick better than an AI algorithm run just through a classic workflow. So it's very, very exciting.
Yeah. If I could get a quantum computer to swim around Manhattan for me, that would be good as well. So if you could work on that so that I can just sit at home, that'd be great. Really, it does feel like a super exciting time. And we were talking on the main stage yesterday about how a lot of these technologies we've been talking about for some time, right? AI we've been talking about since the 1950s. Quantum has been, a lot of people always said to me, even 8-9 years ago, well, it's a long, long way off. But it now seems to be, and I'm sure a lot of the deep tech we're talking about here, seems to be more of a reality because we're in a different place, because we've got the compute resource, because the infrastructure is here, the compute power is here. Compute power seems to be the key to a lot of moving forward with these really exciting innovations in a way that we've never seen before.
Yeah. Absolutely, and also we've got the data.
Yeah.
And that's the other thing. We've got to have big data, and we've got to have the compute power to process it.
Yeah.
And at this moment in time, those two things have come together, and that's why we're seeing this rapid transformation, particularly in the AI field, where AI is working really well. So ChatGPT and all of that is because it's feeding off huge amounts of structured data on the World Wide Web.
Yeah. Do you see this slowing down, the pace of this evolution slowing down anytime soon?
I can't see it. Once we have exascale compute, of course, we then start producing exascale amounts of data. So then we've got to look at how do we process that, how do we store it. All of these things around this exascale transformation that we're just at the edge of.
Yeah.
It's going to show us whole new insights in how we look at data, play with data, process data.
Yeah.
It's a truly exciting time to be in.
It really is. It really is. If you don't come away from CogX feeling really excited about the next stage and next step, then where have you been for the last 3 days? So the theme of CogX is really, how do we get the next 10 years right? I'm going to ask you that as our kind of end question. I think that's a really good one to pose. But before we get there, I can't not have you here and ask you your views on the announcement last week that we've finalised the association with Horizon Europe.
I was just so pleased.
It was such a brilliant way to start the day. I was like, oh my God, it's over the line. It's great. It's here because it's so important. We know why it's so important, but why do you think it's so important?
For me personally, big science, and what we're talking about now in big compute as well, I would include that as part of the big global science agenda, is a collaborative field, and we have to be part of it.
And it's a global conversation, right?
Exactly. It's global. We need to be part of Europe. The UK really did very well out of the previous European Horizon programs.
Was that Horizon 2020?
Yeah. And we were seen as real trusted partners and valued partners in a lot of very big proposals. CERN is another one which we are a big partner in. We do a lot of big science in the UK, and we're globally leading. So we need to keep up there. So really excited. And now we've got access to the European ecosystem on compute as well, with their new supercompute and exascale compute that they're developing at the moment.
Yeah. Yeah. So if you're now wondering, well, what's this Horizon Europe? Or you're like, this is great, now how do I get involved? Because there's research money, there is funding, there's opportunities. I saw yesterday, I think Innovate UK are doing a webinar. Forgive me, I can't remember the date, but it's either next week or the week after, where all your questions on Horizon Europe can be answered. Tech UK, we're going to look to do something similar as well, so we can spread the word, because it's great that we've now, the association has been confirmed and that we can move forward, but we need to get researchers, we need to get businesses, we need to get industry using it, right? And
so
working
it's not
together.
just about researchers. There's a lot of research going on in industry, and it is very much open to you guys as well as to those that work in the academic fields too.
Yeah, and the great thing about it is it's also consortiums can bid together, so it brings people together, and it's a great way of building relationships, building networks, building your contacts, building projects that you want to work with others on as well. So absolutely. I think we've done our Horizon Europe plug, tick. So let's, we've only got a few minutes left. So let's focus a little bit on that final question of how do we get the next 10 years right? I want to ask you, Kate Royce, what's on the top of your list or top of your, you know, what do we need to make sure we get right for compute in the next 10 years?
So for me, sitting where I do, the ecosystem of computing access needs to be right in the UK. So we've talked about Isambard AI. We want to make sure that we have an easy point of access for industry, for academics to be using these national facilities.
Which includes Hartree.
Which includes Hartree. We've just launched our procurement for our next HPC as well, which will also be enabled for AI applications, actually. Very importantly, it's going to be a GPU-accelerated machine. So we're going to have lots of these state-of-the-art facilities. We need to have an ecosystem that makes it easy for you all to use. The other really big issue around AI uptake in compute is to understand and have that open conversation about the ethics around use of data and the security around use of data. We know the data out there, particularly publicly accessible data, is very biased because it was collected for a particular purpose. Reusing it for a different purpose means we've got to be very, very careful. So we need to be supporting the skill base around that, as well as having a lot of these big summits. We've got one coming up soon that the UK government is leading the way in, but we also need to be training everybody around it. And finally, for me, as well as the skills, we need to be developing software to run on these new machines. We've mentioned that exascale machines do not work the same as a classical HPC does. The AI algorithms need to be rewritten in a different way so that you can use them. So that requires training and investment in developing that software so people can move forward.
Yeah, absolutely. I think those are all brilliant points. I would add to that, from my perspective, thinking about it from an industry point of view, is how we also ensure that industry are thinking what supercomputing, what exascale, what quantum could mean for them as well. So how do we ensure that, of course, it's all of this computer infrastructure is vital for research and researchers, and that could be industry as well as in the public domain. But how do we get business leaders to also think about, well, what does supercomputing or what does compute infrastructure mean for me? How could it unlock my business, or how could it help me drive that innovation that I think is going to be transformative to my industry?
And that's partly what Tech UK and Hartree are here to do. Hartree's there to actually take you on that journey with that AI problem that you've got. What technology do I need to solve my digital problem? What's the best way? We've got government funding to help you do that. So get in touch through Sue at Tech UK or come directly to Hartree, and we'll help you on that journey, because at the moment, I think for a lot of industry, it's very difficult to know what technology you need, what's the best way to do it, and to develop a massively big, skilled AI data science team off the bat before you've even got anything running is very expensive. And that, again, is something that Hartree can help with.
Yeah, that's a good point. We need to make this easier for people to understand what it means for them or what it could mean for them. Because it's a very complex, busy conversation right now, right? And so it can sometimes feel overwhelming. So I think always think about value, always think about what it could mean, what it could unlock, what's the problem, what's the issue you're trying to solve.
And if you're not sure, come and talk to Tech UK and Hartree about what your problems are, because we've probably got, if we haven't got the experts ourselves, we probably know the expert.
We probably do. Well, Kate, absolutely amazing and great to have an opportunity to talk to you about the work of Hartree and what lies ahead. So thank you so much for being with us today, and thank you, everybody. We hope you found that useful. And
thank you.
Hand back to Stephanie.
Thank you very much, everyone.
Yeah.
Thank you so much, Kate and Sue. Not a dry eye in the house after such an interesting chat like that. Wonderful news. Time for food. Go and get some sunshine, fresh air. We've all been in here breathing this. God knows what will happen. We'll be back at 2:30. We're opening up the quantum section of the afternoon. So we're going to be talking about integrated phonics, the future of light-based technologies. It's going to be kind of cool, but be fueled and rested. We'll see you soon. Are you all sleepy and digesting like I am? What's great is you now have half an hour to listen to fascinating panels. You can just like relax and let the other brilliant people do the thinking, and you just absorb and then quote them at your next party. You can tell the kind of parties I'm going to. So without further ado, I'd like to invite onto the stage John Lincoln and friends. He's coming out with 3 panelists. They're going to be talking about integrated phonics, the future of light-based technologies. Enjoy.
Thank you. It's a huge pleasure to be at CogX in the first panel session that's ever talked about photonics. Lots of people say, what is photonics? Well, it's anything to do with light. Technologies, innovations, products, anything that involves this stuff, right? And it's one of the fundamental senses, 5 senses of the human brain. It's something that's fascinated innovators for a long time. The first treatise in optics is rumored to have been written by Euclid in about 300 BC. So we've had a little innovation going on for a couple of years. It helps us along. Somewhere Galileo thought about telescopes. James Clerk Maxwell theorized it. And then you note the subtle shift to geography there, back to Scotland. So photonics has been around a long time, but it's something that empowers us all every day in ways we don't realize. It's the technology that makes the internet work. I'm proud to have been involved in engineering things that transmit about 40% of all data traffic globally every single day. It's something that every time you go to hospital, the thing that says whether you're sick or not, the white blood cell count, that's driven by optics. It's the lasers that cut and weld your car. It comes to us everywhere. Globally, it's about a $700 billion industry. In the UK, it's about £15 billion, employs about 79,000 people, according to our latest studies in the UK, engineering those products. And they're increasingly getting to very interesting places, consumers, AR, VR. And that brings us around to this topic. How do you get photonics from the stage it is now, which is a bit like the early stages of electronics before you had integrated transistors, to the next stage where you can ubiquitously churn out innovations in a very short space of time? And that's where I'm going to pass over to Killian to explain the integrated photonics thing that is up on the stage. Killian.
Thank you, John. So my name is Killian. I'm a photonic technologist at Digital Catapult. So at DC, Digital Catapult, we accelerate the adoption of technology via collaboration and innovation. So I focus on light-based tech, photonics. So as John was saying, photonics, massive industry, but when we think of photonic components, we think of lasers, fiber optics, detectors. Integrated photonics essentially is all about shrinking those down, integrating them onto a substrate and onto a chip that allows, say, for better performance, greater reliability, lower energy consumption. So creating essentially on-chip photonics is our goal. So in a similar respect to integrated electronic circuits, we can develop integrated photonic circuits, also called photonic chips, which, due to their very nature, they're incredibly compact. You could say put them on wearables, as well as increased functionality and greater performance. So, because these can be developed, say, silicon-based chips, they can be produced using similar manufacturing techniques to the semiconductor industry for electronic chips on the silicon side of things. But there are also metal-based systems where we develop integrated components using nanoscale metal components, which are termed plasmonic components. And in plasmonic side of things, we can, say, confine light into an extremely small volume, for example, to increase data storage, as developed by Seagate and their HAMR technology, as well as for sensing, the biosensing as a causeway sensors for accelerating drug discovery. So we've got this raft of technologies in integrated photonics. The core market at the moment, so datacom, so it's transceivers in data centers. But with the ever-increasing production of data and need for faster networks, there need to be new photonic technologies to really avail of the bandwidth, avail of the low energy consumption. So integrated photonics exists on the communication side of things, but there are many opportunities for emerging applications. For example, in sensing, as I was saying, on biosensing, say for continuous health monitoring, lab on a chip. There's also work being done on-chip LiDAR for autonomous vehicles, inertial sensing for navigation, sensors for industrial automation, as well as monitoring the health of infrastructure. So sensing is a big core application for integrated photonics, but of course, computing, it's very fitting we're talking today. For photonics, massively parallel, massively fast, very suited towards, for example, new computing architectures, could be neuromorphic computing, as we saw yesterday, there's a session, in terms of very low energy consumption for AI applications. So far, I've just been focusing on classical applications for integrated photonics, but of course, it underpins and has many opportunities on the quantum side on the 3 core pillars. That'll be sensing, communication, and computing. So here, the quantum technologies can avail of the scalability of integrated photonics, as well as the compactness and being incredibly robust. So there's many, many applications. We can think of integrated photonics cutting across, say, semiconductors, of course, AI, enabling, as well as optical commons, which is very well established, the medical side of things. It's very, very broad and a core pillar for the UK in photonics. Moreover, Digital Catapult and Yellow and Causeway, and John as well, taking part in the Smart Nano NI Consortium. So this consortium, based in NI, really has a wealth of expertise in integrated photonics and nanotechnology, as well as manufacturing and data analysis. So as part of this, we are developing new photonic technologies. The aim is to have 100 prototypes over the lifetime of the project, 6 products by the end. So it's a really core project building up the photonics cluster, and also at Digital Catapult, we're running programs to accelerate the adoption of photonics amongst other digital technologies, say for manufacturing. So we have a program running soon. I'm happy to talk about that more later. So there's a lot to get through today. I'm very happy to get through the opportunities and challenges for integrated photonics.
Thank you, Cillian. And I'm very pleased to be joined by 2 others who represent, between Kate and David, the yin and yang with Kate, a very established company. Yellow is one of the most important companies globally in enabling the integrated photonics. A small company in Carrickfergus, without which we wouldn't have the internet. And that's a fundamentally and very important point. Kate, talk to us a little about what Yellow do, what you do, and the issues of serving that manufacturing beast that is the global data center world.
So I'm Katie. I'm the optical physicist at Yellow. We design and build test equipment for a range of applications, including photonics. So I work mostly on the photonics side of things, helping with the design. I help doing some of the simulations and integrate with our engineers so that they know how we can make our systems as good as they can be. And that's why I've come on board to sort of facilitate improving that. And as time goes on, and the device densities on wafers they increase. That's really what we're looking at now. That's, I think, going to be that's our big challenge at the moment. Is the devices get smaller, testing gets harder.
Thank you. And that's a very important point. If we want to serve consumers, we have to make not tens of devices, not millions, billions of devices. You can't afford to make billions of devices unless you can make tens of thousands at a time. That's a massive parallelism. That if then somebody says, could you test each and every one, and the test cycle takes half an hour, you can't afford that much time, right? We would be long and grey, and the adoption cycles will be over. So how you do that and how you resolve that is one of these key things.
Yep.
At the opposite end of this spectrum, we have the people who make systems, products that deliver value to people. And Causeway Sensor is a great example of a company spinning out of university, trying to make a name for itself, trying to work out how to add value to customers and resolve the classic problems of, well, I really need to make some money this week and send an invoice this week, but actually I also want to grow a very large company long term. Those are challenges. David, talk to us about those challenges.
Great to be here, everybody. I'm David Kane, lead engineer at Causeway Sensors. And Causeway Sensors, as John was hinting at, what we do is produce protein sensors. And the importance of that is that a lot of the therapeutics that are coming down the line these days in medicine are being grown in bioreactors. And you need to understand what's going on in those bioreactors to actually put out something that's an effective product and put it out at an economical value. And what we're doing is allowing the user to understand what's going on in those bioreactors better than ever before. And at the heart of that is a photonic chip. So my role in Causeway really is kind of the glue. I basically provide the opportunity for the biologists and the chemists and the physicists to all work together to produce this thing. And as John was saying, we are a university spin-out, and I think I'll get an opportunity maybe a little later on to talk more about some of the advantages and disadvantages of that. But it really is a bit of a journey in Northern Ireland at the moment in the photonics sector, because we have so much support from UKRI and because we have such a rapidly growing ecosystem. It's really a great time to be involved in it.
Thank you, David. And that's a good illustration. People think, what's the direct market of, say, photonics innovation? And actually, the direct market is small relative to the impacted market. If we can do things that enable you to make drugs faster, innovate drugs faster, that secondary impact is phenomenal. The leverage is enormous. And indeed, globally, we think of photonics as a $700 billion industry, but the industry enabled by photonics is sized by my good friends at SPIE at some $2 trillion and growing rapidly, and that's because of the diversity of places we get to. And one of the key things as we innovate, even a technology that's been around a long time, and especially as we get to this new generation of integrated photonics, is how do we get products to market? How can we not spend 10 years innovating something, but do it in 1 year? And there are two aspects to that. There are how do we make things reliably, test them, produce them, and manufacture them? And then how can we accelerate innovation out of universities? And how do we support that? Cillian, talk to us about what Smart Nano is trying to do to help that ecosystem move faster.
It's to essentially lower the barriers. So if you want to get companies coming together, cooperating amongst themselves, it's really ensuring collaboration between different partners, and each of us has respective focus areas. So Causeway, the end applications, Yellow, in terms of testing, us in terms of developing programs that allow external companies to interface with the ecosystem that we're growing, and to essentially prototype solutions to internal challenges. So it's reaching out beyond the consortium, which is crucial. So not only are we building stronger links amongst ourselves, complementing each other in terms of our respective focus areas, it's also engaging more widely and getting companies in. And then that helps nurture the ecosystem, grows it over time, and yeah, we see real results.
And it's fascinating. I've been to a number of their meetings in Northern Ireland. And what's nice is when you have somebody coming from the AI machine learning community who has no knowledge of optics, linking up with somebody doing sensors technology and manufacturing technology with an end user who's going, I just want a box that works better. Right? And the end users don't really care, of course, what's inside the box. They just want benefits.
Exactly. Yeah.
David, talk about this journey of trying to take an innovation that comes out of a university and turn it into something that offers those black box benefits that the customer doesn't care how it works, and your engineers care passionately about how it works, so do the academics. What are the emerging and new challenges? Many of them are well known, bridging the gap and getting over the innovation gap. But what do you see are the newer challenges that are emerging in the most recent years?
Well, I suppose one of the big challenges, certainly that we faced, was we spun out the physics department at Queen's University Belfast, and originally, so we kind of joke that we were a physics company, and then we became a surface chemistry company, and then we became, and currently are, a biology company, and with the new round of development, we're going to be a physics company again. And what I mean by that is that it really is a multidisciplinary effort. You know, the innovation that we spun out with was very much physics. It was a nanophotonic sensor. It was the know-how on how to build this nanostructured array of rods, and it was very much focused on the physics. It was the materials deposition. It was the light interactions, very well understood, papers published, academics pleased. And then you sort of sit and you go, we have this thing that we can see is actually very useful. So we should probably, productize that. We should probably bring that out into the commercial market, see if there's a use for it. And there were a number of pathways that we could have taken. We ended up settling on biological sensors. Although, funnily enough, jewelry was actually one of the initial ideas, because these surfaces are beautifully iridescent. But once you've done that, well, now you're in the biology arena, and to get there first, as I said, you actually need to look at the surface chemistry. You need to look at how those assays are bound to the surface. So you need to bring chemists in. And then whenever you're actually looking at the bioreactors and you're trying to understand, how we can sense what is going on, that's the realm of the biologist. So it really is this sort of very multidisciplinary approach. And the disadvantage in some academic environments is that, you are literally sitting in a physics department. They're not really used to working with, some of the risks associated with biology, for example. We did a project recently, and I can't say exactly what it was for proprietary reasons, but there was a slightly enhanced risk profile that in a biology department, they wouldn't have blinked an eyelid. And in a physics department, they're sitting kind of going, we don't know how to deal with this. And it's the same over in biology. They get a little bit nervous about, class 4 lasers sitting out open on a workbench, even if it's in a shielded room and so on and so forth. So really, one of the things that we sort of need to concentrate on to help that innovation grow is being able to join those departments even better than they are already. And don't get me wrong, universities are quite good at working in an interdisciplinary fashion, but there are still those walls that are built up, even purely because these departments are literally in different buildings in different areas. And I think one of the key actors to kind of get that going is the University Innovation Services. And I have to say, I didn't think I would be singing the praises of a University Investment Service, because quite often you'll hear startups complain about them. But the one at Queen's is actually very good about trying to introduce people and trying to glue together one academic from one side and be able to sort of allow them to help with another. And of course, the consortium is a really, really major driver in our successes, because it allows us to unlock a lot more partnerships in industry as well. And if I can just add something that Killian was saying earlier, if you're looking at establishing a consortium, or you're sort of involved in the organization of one, really the key thing that's going to make it work, and that has happened with Smart Nano, I'm very glad to say, is your companies and your academic organizations should be complementary. They shouldn't have overlap if you can avoid it. If we were another photonics test company, for proprietary reasons, I probably wouldn't be able to be as open with Katie as I am, and vice versa. Whereas we're able to very much approach each other as colleagues, despite the fact that we're from different organizations and companies, and that is immensely helpful.
Thank you, David. Katie, interesting, because the contrast to Yellow, when was Yellow established? I can't remember.
40 years ago. So
40 years ago.
This year.
Richard, who's the CEO, I know, he's been there almost that entire time.
Yeah, he has, yeah.
He still writes most of the software code, I believe.
Yes, he's still very much, very hands-on.
What do you see, as a company that's been in the business a long time, has an extremely strong reputation, if you're in the niche that knows about it. What do you see the challenges from you of meeting the very rapid pace of change that you see in getting stuff out, manufacturing, and meeting that demand curve?
I think, certainly within Smart Nano, one of the things that we've really benefited from is utilizing simulation software. And that means we can now test our ideas, at least in simulation, and it guides our direction much more, and it's much cheaper and much faster than us having to physically try things and then see what happens. And as everything gets smaller, things become much more difficult to machine, much more difficult to integrate, much more difficult to make. So the ability to use that simulation and then speak to the other people in the consortium who've worked not on the same things, but on similar things at a similar scale, that sort of micro nanoscale, it becomes very difficult at those sort of levels. And so I think, certainly using the simulation has helped us, even in the year that I've been there. We've been able to accelerate how quickly we can come up with the solutions in-house, and I think that they're much better solutions maybe than they had previously been, or would have been, without that sort of direction from
it's
exploring
an interesting process of looking what is essentially digital twinning, right? In the manufacturing environment to speed the manufacturing process up and deliver faster solutions. I think we underestimate how much I think people are using digital twinning, even at small manufacturing companies, as part of their standard processes these days.
Yeah, and it allows me to sometimes I come up with some solutions and I take it back to some of the mechanical engineers, and they tell me it's never going to be feasible. So, you know, it's...
So I wanted to take a step up for a second and look at the slightly bigger view. Integrated photonics is this whole process, just like integrated electronics, of putting many things in a chip, chiplets, joining them together. I'm personally involved in helping support the government on the national semiconductor infrastructure strategy at the moment and trying to work out where we can add value. So one of the key questions there is, where do you think integrated photonics will be going in the next decade, and what are the parallels and differences to the magic world of semiconductors? David.
Yeah, so it's an interesting question, and actually, so one of the issues actually touches a little bit on what Katie just said. One of the issues that we have as a startup, for example, is that if you walk into an optics lab, if you walk into a photonics lab, you'll see pretty much all of the experiments are set up on optics tables. They're on breadboards. And these are kind of vibration-isolated tables that you can slot these kind of pre-made components into. And there's a few sort of major leaders, Thor Labs and so on. There's a lot of famous names. And you buy those optical components in, and you've got a very, very wide choice. And you put those all on the table and you can do your experiment. And whenever you want to actually shrink that into something that's more like a product, then it starts to become difficult. And I think one of the things that the semiconductor industry has not so much an issue with, but you go through simulating, an experiment in your case, a circuit, an integrated circuit in a semiconductor case, and you can get so far with that before you actually have to tape the design out, and you have to go into a fab and you have to spend really quite a lot of money. And one of the issues I think that photonics has going forwards and is going to, the solutions to which will change the landscape, is that we currently don't really have that same pathway where if you want to take your integrated circuit design, you can go to maybe an older process node running in a fab that's no longer really at huge capacity, and they'll kind of say, sure, we can do you a few thousand units, we can tape that out for you. We'll do a deal. It's not going to cost you too much. Whereas I think that to jump from the kind of the macro scale of the optical components on the breadboard down to an integrated device that's sitting at chip scale is still quite difficult in the photonics industry. That's one of the things that the Smart Nano Labs are helping to facilitate that process, because we're getting in a lot of equipment that is allowing us to do that chip scale prototyping. So that then we can take it out to some of the larger manufacturers and sort of, quite frankly, know what we're doing and have that design much better illustrated and kind of frozen before we have to take it out and spend major money. But I think bridging that gap and getting that kind of more incremental approach to manufacturing is going to be crucial for a lot of small photonics companies.
Gillian, you've interacted with a lot of companies who are fascinated to know how that they can work with Smart Nano, partly because Smart Nano is well-funded, so that attracts people to say you're a well-funded consortium. How can we work with you? In that sense, what would you say people are coming to you and seeing and saying that they see the benefits of integrated photonics as a preconception, and then after they've talked to you, where are they taking those preconceptions forward? What are they seeing change after they talk to you?
Well, for integrated photonics, so at the moment, very much data comms. This is where integrated photonics is. And just going back to also on David's side, like looking to the future, it's going to be more sensing. It's going to be more on the computing side. So it's getting towards those high volume markets that potentially help grow integrated photonics, just to target those. So that could be in sensing, it could be in AR, VR, it could be in on-chip LiDAR. So it's making people aware of what is the potential of integrated photonics. That's what coming to us, Smart Nano, says this is what you can do, this is what you can build, this is the potential new functionality you can develop as a result of combining all your components onto a chip. So they may not have the expertise, and it's often the case and across photonics generally, is you need expertise in terms of that integration piece. So you have an on-chip, like a benchtop system, translating that into an on-chip, that's a very different challenge. So coming to us, learning how you could potentially do that. A big key here, and comparing it to the electronic side of things, we need to have, again, closer collaboration along the value chain. So we start with design, you go to manufacturing, you go to verification, and then development into product, into an application. it's making that as smooth as possible. Say a company comes along, they want to develop a prototype product, but it may be difficult for them to navigate through that ecosystem. So it's important, I think, looking to the future to make that as seamless as possible. So they come to us, come to Smart Nano, and learn about how you can potentially create a prototype product. So it's really, again, as I was mentioning earlier, lowering those barriers and training, design. And so, because integrated photonics is very immature in the design space compared to integrated electronics, there's a need also for standardization. So there's a lot of work to be done to make it as more mature, to bring it up to the maturity of electronics. So there are many, many angles that come at this, but I think the key takeaway is that seamless interaction across the value chain.
So we're getting close to time, but I'm going to put some question that I love because I like the way that one can have influence and say, Katie, you're earlier in the process of getting through the career and engaging in yellow and doing things than many. What would you like to be your long-term impact from being involved in this new generation, this new revolution? If you look 25, 30 years out, what would you like to stand up and say, I'm proud to have achieved?
I think on-wafer testing really is what we're looking at, being able to test thousands of devices quickly, or hundreds of thousands of devices quickly on wafer. And that sounds very simple, but actually being able to do that is very, very difficult, very complicated. And as, like I say, as device sizes decrease and the volume of testing increases, it gets more and more challenging. And I think that's the trajectory of yellow over the next few decades, is to be able to do that.
David, what would you like your legacy to be?
Well, certainly in the Northern Irish context, I think that really we want Smart Nano to continue to grow the capabilities that are surrounding Belfast and Derry and the wider corridor in between. Because the more companies that you have, then the more companies that are directly involved in photonics, the more companies that you have supporting them, which means that it's much easier to start a small company involved in photonics and so on and so forth, and that can really grow and snowball. And I think that is going well at the moment. What I would say is that there does need to be the continued good political leadership and vision that has occurred at places like UKRI to notice that we have this capability and that it should be growing. And if that continues, then really the sky's the limit.
Yeah, and it's notable, there are about 1,200 companies involved in photonics in the UK, and we create about another 25 to 30 every single year in the UK. That's the birth rate. I tracked it for over 40 years. We've tracked that birth rate, and it's been extremely consistent over that time. I think one of the things to add, and I would like to do, is to add to that, we send all our data around the world with optical fiber. We will very soon be going to a world where we store all our data, again, back using optics, whether it's the long-term archive data storage that our friends at Microsoft are working in Project Silica, where they burn data into little glass disks, or whether it's the medium-term data storage that people like Seagate are working on through this new optically assisted HAMR process, heat-assisted magnetic recording. And so it won't be long before data moves around the world with optics. It's stored with optics. It's archived with optics. But very soon we will also see it AI-enabled through optics. Optics is incredibly good at the matrix problems that are behind AI, a big theme of this week, and it will not be long before we see optical engines performing some of the key AI matrix functions that are necessary in mass machine learning programs. So I look forward to AI optics being in the processor as well as everywhere else. So that's a fun thing. Killian, I'm going to turn to you just for some wrap-up comments.
Yep, I think it's been a great session. We've covered quite a lot from the startup journey, testing, a wider view of the photonics landscape. It's integrated photonics is a fascinating area with many, many applications. We've spoken quite a lot about the emerging applications, potential high-volume markets, AI, quantum, sensing. And as Smart Nano and I, we're helping to grow this technology, to grow the cluster. So if you have any questions, definitely reach out to us. If you want to talk about our work or how we could work together in the future, we're very open to dialogue and how we could collaborate beyond Smart Nano. in the wider integrated photonic space. So I'd like to thank everybody. It's been a great session, and
thank
very
you.
much.
And I'd say, yeah, if you need to know anything about the wider photonic space, I'm all ears. I'll be around, whether that's on a national basis or actually I do a great deal on the international space as well. So I'm very happy to field those questions, and we'll be wandering around in the next few minutes. Thank you all very much. Thank you for being here. Thank you.
Thank you.
Thank you.
Thank you so much, John and Killian and Katie and David, for that riveting discussion. The good news is that it's sunny outside. The even better news is that we've got half an hour until the next talk, which means if you want, you can go catch some rays, chats, make a call, make a new friend, flirt. But be back here, if you like, for 3:30. We're starting promptly at 3:35, but you might want to get your seat. We're doing Unveiling Semiconductor Frontiers, AI, Bio, and Mobility Insights. It's going to be a cool panel. So we will see you back around 3:30. Enjoy. you out into the sunshine, and looks like only 10 of you have come back. Fair enough. We are going to be having a wonderful conversation today. Super nerdy, so just get ready. If you like semiconductors, this one is for you. It's called Unveiling Semiconductor Frontiers, AI, Bio, and Mobility Insights. Please join me in welcoming Michael Dimelo and Dr. Simon Hsu onto the stage. Now, not everyone, and in fact, I'm almost going to bet that almost no one in this room knows as much about semiconductors as the two of you. So if you could do all of us a favor, by which I mean me, and explain what a semiconductor is in a way that a 6-year-old can understand, that would be a great start. Which one of you would like to take that challenge?
You go first. No, you do it, Simon. I'm not going to interrupt.
And tell us a bit, first of all, who you are and why you're qualified to describe a semiconductor to a 6-year-old.
Okay, everybody, I come from Taiwan National Laboratories. And one of our main job duties is we try to enhance Taiwan's semiconductors technology. We still keep on going. And we every day we co-work with Taiwan's leading company, semiconductor company like MediaTek or TSMC. And we also co-work with Taiwan's professors to make sure their project and the student they trained actually fulfills can satisfy Taiwan industrial their requirements. So that's our job. So that's why I thought semiconductor, maybe I can share a little bit about my experience and my viewpoint. Yes.
Thank you very much.
Yeah.
And if you had to describe what a semiconductor is to a child, really simply, what does it do? What's it look like?
Okay. Actually, you can imagine like semiconductor like a calculator. So he put everything to be 1 and 0, 1 and 0, to help you to do the calculate. And because technology we improved so much, so you can imagine that right now, once we can do the 1010, we call it the transistors. A virus right now, the size of virus is around 100 nanometer. And right now, the one transistor, in terms of TSMC's process, we can do 2 or 3 nanometer only. So you can imagine that a small size, maybe they cover more than 100 million. Yeah, of course, over 100 million transistors to become a very, very small but powerful calculator.
So these are tiny, tiny calculators that you're saying can be as small as the size of a virus? Really, really little?
Yes.
Like
really
you almost
little.
can't see them with the naked eye?
Okay. If this one is a transistors, actually, the chip like London. So we can imagine that. So London to become a small chip, and how small the transistor will become.
Right.
So
super small.
Yeah.
And they're everywhere. Can you talk us through the devices and many, many things in which transistors, in which semiconducting chips are in? Where do we find them? What would happen to our modern life if they were to all of a sudden disappear?
Yeah, I think there's plenty of evidence of what happens when you take transistors out of society. You know, we don't produce cars anymore. You know, we don't produce phones or digital TVs or set-top boxes, washing machines, everything that has a small brain, basically. So the way I describe a classic semiconductor is it's a little brain embedded in some silicon with some wires. And the intelligence that we bring to all these everyday devices that we use without thinking, there's brains in there, and there's transistors that are being switched on and off to make decisions, really, about, you press a screen, the screen responds, you put your foot on the brake, and the brakes of the car slow down. These have all got little brains, and therefore little microprocessors, and therefore semiconductors embedded within them, everyday devices. And if you think about a car's got thousands of semiconductor devices in it. I mean, from the console through braking systems, through electronic windows, through engine management systems, just everything.
So modern life as we know it
Everything.
can't function without them. They're almost like the sort of building blocks. And also, what would happen if the very complex, fragile, delicate global supply chain that is needed to make them were to ever have a problem? So we've got you here from Taiwan, which is super exciting because Taiwan is the absolute sort of beating heart of the semiconductor industry in terms of manufacturing. But where is design happening? Where are the raw materials coming from? What are the countries that you would say are the biggest countries that are important for making semiconductors?
Okay. So actually, if you want to design a chip or semiconductor, you can done this kinds of job everywhere. You just based on we call the EDA tool. That's the design environment. And you follow some guideline and to do that. Okay, as more importantly, in the future, if you want to design a chip or a semiconductor, will become easier due to artificial intelligence will help you. You just need to define the spec, and you didn't need to do the coding more than 1 million columns, and AI can do everything for you, and then you just double check the final versions. It makes sense. But at the same time, once we call the type out, you finalize your design, and the foundry, the factory, will help you to make sure then from language to become physical IP, and we do the layout to make sure it looks like a chip. And the foundry will do everything for you. But if you jump into foundry process, actually they have a very, very strong cluster efforts. That means it's better that we put everything in the city. Then once we do the manufacturing, you can think about it. Just one chip, but in TSMC, there are more than thousands process. And engineering, they have to co-work and communicate to each other to make sure every process, the yield rate is so high. Otherwise, the chip will become very expensive.
Right.
So the better way from material to do the cluster growing and to become the wafer and do the AP, and we do the everything on wafer to cut become a single chip. Our experience is we should put together in a small place, and the engineering we can communicate to each other.
Right.
That's our experience.
So, question for you both. Does that mean that as AI becomes more important both in the design and the manufacture of these chips, helping humans to make them, but also AI designing its own chips, starting to take humans out of the process, is that going to become something that could actually change the nature of the supply chain, where it's going to stop becoming so important about where things are physically located and could be done at that level, at least of design, much more globally, and then I guess it just becomes a question of again, production, of manufacturing.
Yeah, I think there's several aspects to where AI might impact the way in which we design chips, as well as the way in which we consume AI as everyday punters and consumers. So on the design side, we already use AI and machine learning already to pick libraries of software that describe how a chip's going to be, how it's got, its functionality. So it already occurs today. And obviously engineers then will sit behind picking these. Imagine when you design software or hardware, there's somebody's already designed. It's a bit like the Beatles who invented music, right? The music has already been written, the tunes have been written, the beats have been written. And if you think about the design process, quite often you're taking pre-existing, melodies and beats, and you're putting them together in different combinations to create a different music. But fundamentally, when you're designing chips or software, it's the same principle. You pick what are called libraries, which pre-describe a function. You put them together in a certain order, and you then call up PSMC or TSMC and say, I need you to make me some chips, please. But AI will touch all aspects of that design process, and increasingly so. We don't produce enough engineers, for example,
Not yet.
to design these things.
Yeah.
And that's an area where we could improve tremendously. You could even de-skill the roles. So you could make folks that probably aren't good enough engineers to be good enough if they're augmented by AI, for example. So you're allowing, maybe lowering the barriers to being able to design because designs are very rules-based.
Right.
So if you can learn the rules, then you can teach a machine to follow the rules. It's not sentiment-based. It's not like I think this should be, or I can imagine this looking like this. It's rules-based, right? So I think AI at the design phase will be codified in tools. The tools will be used by engineers to augment their role, and it'll either enable them to make decisions more quickly or to arrive at designs more quickly. So in theory, it should reduce the cost to get to a design.
So lower costs, potentially better design, more interesting or innovative design, ways of helping the workforce, including people who aren't necessarily trained or the best that they could be in certain other areas, can become augmented with AI as a sort of ideal colleague. What about investment opportunities? Like, how are you seeing the landscape of semiconductors going forward?
Okay. I try to separate these questions into three directions. The first one I thought is about applications. So we put so much attention on AI on chip, especially for edge AI, not a cloud service or an NVIDIA solution. No, right now we put so much attention on edge AI. So that means in the future, AI is everywhere. So semiconductor is everywhere. And then the second one is because we have to fulfill AI on chip, those kinds of applications. So design-wise, I just mentioned, AI also help designer to speed up their design, and we can increase the performance, right? Because in the past, when we do the computer or a cell phone, those kinds of IC design, actually we just follow our experience.
Right.
But once AI is everywhere, semiconductor is everywhere, that means the application is diversified. So that means you have to design different kinds of chip.
Yep.
But based on different kinds of chip, maybe you did have relative experience in the past, but you can rely on the AI to choose the right IP for you and to do the hardware language programming for you. So you just give the clear idea, market spec, and your expectation, then AI will help you to do the dirty job. And so those kinds of a tool, right, we are looking for, and we want to invest. And the third one is, because if AI is everywhere, that means your semiconductor structures will change a lot. So in the past, logic IC is logic calculator, and the memory is memory. Memory stores your data, and the logic to calculate your data. But because AI, they need to calculate real time. So that means you have to put memory and the logic IC together. So you need a new technology, new process we call 3D process. So that's manufacturing, that is totally new technology. So the third one right now we are looking for is we invest the process, new process or a new manufacturing skill that can fulfill the 3D packaging. That's it. It's a little bit complicated.
I love that it's a little bit complicated, though, because this is a really meaty topic. If you were having to look forward to the next sort of 10 to 15 years as somebody who does a lot of investing in this area and is looking at growth, but also understands constraints, what are the things that you think are most exciting and that we should all be paying attention to?
It's like predicting the future, isn't it?
Just a guess. Nobody will hold you.
Dangerous.
Unless you get it right, then we'll credit you.
Dangerous game. I think if you start with what society is likely to look like and work back, that's probably a good way of framing.
Cyborgs, all of us.
Who knows? I remember my old CTO at ARM once, talking about embedding Babel behind your ear so you can translate languages live, real time, right? And this he came out with this idea, 2014 or something, said, oh yeah, we'll just embed a chip, just be behind your ear. And at the time, I didn't really think about it as a prospect, but actually it's totally feasible, isn't it?
It's
really?
doable.
You know, why have Google Translate when you can have something translate in real time?
Yeah.
You know, and does anybody really mind about embedding something in the skin when piercing and tattoos and everything else are now? He even suggested you could even tattoo a chip into your body as well. But anyway, that's a complete subject. So it depends on what you think society will need from the technology world. So Simon's talking about really how do you bring efficiency to the way in which you manufacture chips. My philosophy is thinking about how society will use technology and then working back through what should we be investing in. So the things that we're naturally going to do more of is we're going to have more compute around us, you know, either prompting us or inferring things, you know, more sensors, unfortunately, in our homes and our vehicles and other parts of
You
our...
say unfortunately, why?
I think, you know, the more you instrument, you know, okay, let me take a more positive spin on that then. So I think as you instrument, I've got a personal philosophy about instrumenting the human. The more you instrument the human, the more the human knows about themselves. And we've seen this a lot with some very elementary instrumentation. You know, I'm not going to promote any particular brand, but where you can read blood sugar levels or ECG levels, and we're able to bring instrumentation and sensors to the human body in a non-invasive way that allows us as humans to understand the state of our health. That for me is a fabulous opportunity, and it's one where, you know, the clinicians, which there's a scarce resource there, if you could present the clinicians with basic data points, then why wouldn't you instrument the human? Why wouldn't you take responsibility for understanding your health? Mm-hmm. You might not understand what it means, but you hope that a clinician would be able to help you quickly because they could see the data. Mm-hmm. So I do think that instrumenting certain aspects of society will have a profound effect on access to scarce resources, particularly clinical. You instrument a car, and anybody that owns a car will know that those sensors often fail. So it's not the braking system that's failed, but the sensor that monitors the brake. It's the most annoying thing in the world. You put a $1 sensor to monitor a $50 braking system or a $500 braking system, and the thing that fails is the thing that's monitoring the mm-hmm. actual brake. So you can still brake, the car stops, but the sensor's got a warning light that says you need to take it in for a service. That's right. What I sometimes think we overstep a little bit.
Right.
And you know, it's important to know when something's not working, but actually that's a false positive, isn't it? That's not a good indication. But anyway, that's sometimes you over instrument, and because you do that, you get false positives. So I think society, we as individuals will take more responsibility for our health, and so we're going to want to present that clinical data to clinicians in a more consumable format. We're going to compute more as a consequence of that. As you add more sensors to the world, you need more compute to make sense of what's going on. Once you compute more, you need to connect more things together, so we're going to need more connectivity and moving more into the optical domain. And so all of these things have a cascade effect on infrastructure, communication systems, devices that are attached to us or embedded in our bodies, devices that are in our vehicles or in our transportation systems. So basically everything gets instrumented. You've got to compute a lot of stuff.
You're using a really interesting word, instrumented, that I don't know if everyone would necessarily use in everyday parlance. When I'm hearing you saying everything's going to be more connected, I'm also thinking everything's going to be more surveyed. And I just wonder what you think about all of this sensors everywhere, be they on our bodies, outside of our bodies, et cetera, means for things like privacy.
Yeah, I know this is one of the topics.
You know, there's the whole knowledge is power, but ignorance is bliss, you know, between these two poles. What if do you have to join this brave new world of the more connected AI? Is that where you see it going? Or do you yourselves as people in this space ever think there's a limit to this?
I'll take 30 seconds. So I think that we have to opt in to sharing that information to certain people, and therefore people producing devices that we buy and either use as, you know, to get around or to monitor our well-being, we've got to give people permission, proactive permission to see that data. I think that's something that we need to improve upon. So rather than when you sign up to Google Android saying you can take my information forever, we're going to have to do something about enabling optionality around that. So that's my take.
And as people who are involved in the making of the chips, do you think that policy side, society's views on this, that's not my jam, my job is just to make the hardware, or do you think about how it might get used? Question.
Actually, my point is we just try to use to leverage semiconductor, those kinds of technology to help human being more.
Mm-hmm.
So for example, like Mike mentioned about bio, right? Right now, the process, the technology we have, actually the size is smaller than virus. So why now we can use a biochip, use a semiconductor to mimic, to become a human on chip? Then we can use those kinds of a tool to make sure the medicine or the sickness you have actually is a perfect match. So that is the perfect tool. So once we can do that, actually we can solve so many health problems. So actually I'm very positive to things how we use the technology to improve our life.
That's wonderful.
Yeah.
Thank you. Thank you both. I have to end this session on time because I'm chairing it, so we could talk, I'm sure, for much longer, but all that remains is for me to thank both of you very much, and we will leave the stage, and I'll bring some new people on. So you all get to relax. Should we go?
Yeah.
Thank you very much.
Thank you. Thank you.
Our next session, continuing on the semiconductor, this is superconductors. Prefixes. From semiconducting to superconducting, we're going to Enabling Transformational Technologies for Net Zero with Professor Susie Speller. She's Professor of Materials Science at University of Oxford. She's leading research on superconducting materials for technological applications ranging from fusion reactors to quantum computers. So that's going to be at 4:05. So we've got a few minutes. We'll be back on shortly. Thanks again. Hello, hello. Having gone from semiconductors, we are now onto the superconductors. We're going to be talking with Professor Susie Speller about enabling transformational technologies for net zero. Just reminding you again that Susie is a professor of material science at the University of Oxford, and she's leading research on superconducting materials for technological applications ranging from fusion reactors to quantum computers. So, without further ado, please join me on the stage, Professor Speller. Good luck.
Imagine a world which is powered by mini versions of the sun that are man-made, where electricity can zip around the countryside in vast, vast quantities, using very, very little energy itself, so with very low loss. From the North Sea wind farms, from the southern European solar farms, to wherever we need it. Where machines that guzzle huge amounts of energy can be made much more efficient. Where our data centers can use a lot less power. Where we can zip around wherever we like in electrical aircraft that are clean, in levitating trains, and we don't have to worry about the environmental damage it's doing. These things sound like science fiction, but in fact, with superconductors, they can be a reality. This is what superconductors can offer. And this is why, earlier this summer, the world went a bit crazy about superconductors. Some of you may have heard about it. There was a big announcement by a group in Korea that they'd discovered a room temperature superconductor, the Holy Grail, a superconductor that works at room temperature, at room pressure, doesn't need any cooling, anything like that. And everybody went mad. Everybody who heard about it was excited about the possibilities that this would mean for our energy consumption in the world. Unfortunately, this material, they called LK99, isn't a room temperature superconductor. So that dream was rather short-lived. The scientific community did their job and researched this very carefully and quickly and discovered it didn't superconduct after all. But that might sound a bit negative, but actually we've got superconducting materials that work. We've got them right now, and they can deliver on these transformational technologies straight away, right now. So, let's just look a little bit into the details of what we're talking about. This is a very simple cartoon of how energy gets around at the moment. 12% of our greenhouse gas emissions come from transport, from the petrol and the diesel and the kerosene used in trains and cars and aeroplanes and boats. And about 80% of our homes are powered by gas, which is like we were burning a fossil fuel when we're heating our homes. One of the things that the government want to do is to switch us to more electric technologies, electric vehicles, use different methods to heat our homes, to ban the sale in future of gas boilers. And that's one of the ways in which they think we can make this more environmentally friendly. We could use hydrogen as a fuel instead, and that as well won't solve all of our problems. But if we do this, what's the consequence? So all of these things need electricity now that didn't before. That means we've got to produce it somewhere. And it's completely counterproductive if we produce that by burning more coal and gas and oil in our power stations. So at the moment, 12% of our energy or of our emissions come from burning these fossil fuels in power stations to make electricity. If we want to power other things like this with electricity as well, our global consumption is going to go up hugely. And so we're going to need to make a lot more electricity. And all of the predictions, even the most favorable ones, suggest that by increasing our renewable energy, wind farms, solar farms, those kinds of things, that's not going to be enough on its own to meet the growing demand that we have for electricity going forward. And by 2050, we'll still be reliant on fossil fuels. So what else could we do? We heard on this stage yesterday somebody talking about nuclear fission. So we could increase our capacity of nuclear fission. In fact, a lot of our fission power plants are coming to end of life or have come to end of life. And these aren't things that you can just build in a day. So building back up the capability will take decades, actually, unless we use novel technologies like the one she was talking about yesterday. What else could we do? Nuclear fusion is a promise that's been around for years. It's always talked about that it's 30 years away. Can we do something to bring that forward? So nuclear fusion is the bonding together of hydrogen nuclei, heavy hydrogen and even heavier hydrogen. You make helium nuclei and extremely fast, energetic neutrons, and that's where you get the energy from. So we need to consider these new technologies as well as renewables to meet the growing demand. What are the consequences? Well, if we're using more renewables, that's intermittent, it's variable. So we're going to need to store the energy until we need it. So when it's very windy in the North Sea, we can generate lots of energy there, but we may not need it all at once. We've got to store it on grid scale. Of course, there's energy storage in cars as well for electric vehicles and batteries and things like this, but this is grid scale energy storage I'm talking about here. So that's all about the sort of switching to electric, how we're going to generate the electricity we need and store it. But what else could we do? We could try to reduce the emissions from what we're using. So we could try to make our devices more energy efficient. 42% of our electricity is used in motors of one kind or another. So could we make them more efficient? 8% of our electricity is lost just getting it from A to B across the countryside. So what could we do about that? Improve efficiency. And of course, if we're going to make everything more electric, we're going to have to get more electricity around. We're going to have to increase capacity as well. Our grid can't cope with the demands for electricity that we're going to have in the future. So how can superconductors help? That's what I'm going to talk about for the next sort of 15 minutes or so. And I think we'll start by playing the video, please. So what you can see up here is some superconductors that we show to students who come round in our labs. These are our levitating demos, and you can watch those whilst I'm telling you about what superconductors are. These kinds of levitation, of course, could be used for maglev trains. That's what our demo is doing here. But it could also be used for things like frictionless bearings, where you've got rotating machines, flywheel energy storage, for example. You could make that a lot more energy efficient if you don't have friction at the rotating parts. But the fundamental part of superconductivity, or superconductors, that's going to make them useful for net zero is the fact that they can carry electricity without any resistance at all. They're not just good conductors, they're perfect conductors of electricity, provided we cool them down. We've got to make them cool with something like liquid nitrogen, like we're showing in these demos. So provided we get them cool, electrons can whiz around them, inside them, without encountering any resistance. What does that mean? Well, it means that if we, for example, it's like if we had a shopping trolley. If we just gave it a push across the floor here, it wouldn't travel very far before it stopped. But superconductivity is like frictionless electricity. So if we start a current going in a superconducting circuit, it will carry on going forever. We can take away the power supply. We don't need it anymore. Okay? And that's exactly how MRI machines work. If you have an MRI scan, you get wheeled inside a big superconducting magnet. It's operating at minus 269 degrees C. That's 4 degrees above absolute zero. It's cooled with something called liquid helium. And in that machine, in that MRI machine, when it's installed in the hospital, a power supply is taken. They start the current going in the magnet. They then close a special switch and take the power supply away. And it's no longer there. That current will go around forever and ever, and the field it produces will stay completely stable, which is what you need for MRI. So the material we use for those has been around for the best part of 100 years. It's called niobium titanium. And liquid helium is not easy stuff, and it won't be useful for power cables and things like that, cooling power cables. But in the late 1980s, a whole brand new kind of superconductors were discovered, ones that nobody could ever have predicted. And these are called the high-temperature superconductors. They work at a staggering temperature of minus 180 degrees C, which still sounds hugely cold to most people. But the really great thing about these is that they can work above the boiling point of liquid nitrogen. And liquid nitrogen, which is what we're using here in that cup, that is very cheap. It costs about the same amount as milk, whereas liquid helium costs about the same as whiskey. So you can see that it enables a whole new raft of technologies just because we can operate at this much higher temperature. All right, I think we'll go back to the slides, please. So the most obvious one of these applications that I showed where superconductors can make a difference is in transmission lines. So this is just electricity cables, the long-distance power cables that go across the countryside. So up here on the left, you can see the underground cables, they're just coming out of the ground there. They're superconducting cables. They carry as much electricity as all of those overhead cables you can see up there. This is a demonstrator project in Long Island, and it's been running for quite a number of years now. So not only do superconductors allow us to transmit electricity with no resistance, but they also allow us to transmit a lot more electricity. So the same diameter of wire can transmit probably 50 times as much power as a normal copper cable would do. So we need a lot less of it. And so for lots of applications, this fact that we can get a lot of current through a very small diameter of wire is very useful. And for cables, it's particularly useful because it means that even with all the cooling and things we need, we can retrofit underground cables and increase their capacity probably by about 5 times, just without having to do any new rights of way or anything like that. So I have to point out, this is a manufacturer of coated conductor who are obviously, which is the kind of material we're talking about here, who are obviously going to want to sell their material. They say that they can decrease the energy by 77%, and that is including cooling. Okay? It's not very difficult to make these cables. They look something like this. You have layers of this material wrapped around, and inside you've got a channel for the liquid nitrogen and another one around the outside for them to return. So it isn't too tricky to do it. So what else could we do? That's one type of demonstrator. We've got lots of other demonstrator projects that have used superconductors. This one's a fairly recent project, which is called the EcoSwing project, where they fitted a wind turbine, 3 megawatt wind turbine, with a superconducting coil instead of a normal conventional coil. And they operated, I think, for about 600 hours, so not terribly long. But it performed just as well as the conventional one, and it weighed 40% less. So that gives you some idea of the benefits here. One of the benefits for wind turbine generators is that superconductors mean that you can shrink everything. So we could make the same power out of a much smaller turbine if we use superconducting technology. And that's great, particularly for offshore, where you have a huge amount of expense goes into to all the platforms that have to support these enormous devices. Other things, well, there are various transport projects that have been going on. This is a fairly old one now, actually, the US Navy propulsion motor. A much more recent one is electric aircraft. So there are initiatives like Flight Path 2050, where we want all our aircraft to be fully electric by then. And actually, the sums don't really work out for normal sort of commercial passenger aircraft very well. And the problem is that if you're going to make them electric, the motors and generators you need are too heavy. If we could use superconducting ones, even with the cooling, then it becomes feasible. And so Airbus are looking at a project on that right now. Energy storage, I mentioned. There are superconducting versions of energy storage that can be grid scale. So just essentially, it's a big magnet that we can put supercurrent into, and it stays there until you want to get it out again. Because it's no resistance, it doesn't cost very much to do it, so they're a good technology. Flywheel energy storage is another I've mentioned. Last but not least, I want to talk about fusion, because fusion is quite important to high-temperature superconductors. It might seem a bit weird, because fusion reaction happens at 150 million degrees C. Superconductors operate at low temperature. And in these compact machines, like the ones being developed by Tokamak Energy, which is a private UK company, they're talking about distances between the plasma at 150 million degrees C and the magnets being something like this. Okay, so tight, really huge temperature gradients. The magnets are needed to do the job that gravity does in the sun. It pushes all those nuclei close enough together that they can fuse. This is a magnet demonstrator that Tokamak Energy are building right now. And this is close to my heart because my research group are working on the materials that will be used in this kind of reactor. It won't work without superconductors. Fusion won't work without superconductors commercially for power plants. And these are the small-scale power plants that are likely to be there in much shorter time scale than we're talking for the big conventional type of fusion reactor. They have to have high-temperature superconductor. So what's the problem? Why don't we see superconductors everywhere? Why aren't they all around us right now? We've had these high-temperature superconductors for 35 years. And the real problem comes down to the fact that they're very difficult and expensive to make. It's not that they have to be cooled with liquid nitrogen, it's because they're really difficult to make. And they're difficult to make because they're ceramics. That's number one reason they're difficult. So they've got the mechanical properties of a teacup. And if you imagine trying to make that kind of material into long lengths of wire that can be bent and made into cables and wound into magnets, you can see what the problem's going to be. They're also very chemically sensitive, so they don't like any atoms to be out of place. And they react with everything. It will even react with air, actually, or water in the air if given the chance. And lastly, they have to be made as a single crystal. So if you've got a kilometre-long wire of superconductor, it's all got to be one crystal. And that's because the boundaries between crystals in high-temperature superconductors act like dams to the current flow. So these things make it really hard. And material scientists have worked for 30 years on ways to do it. And this is the state-of-the-art material. You can be forgiven for thinking it looks like copper tape, because what you're seeing is copper on the outside. But you can see it bends. It's a flexible metal ribbon. And it's made by taking a metal substrate, metal ribbon, and multi-layer coating, deposition, of various different oxide layers, and eventually the superconductor. There is 1 micrometer of superconductor in that, which is a millionth of a meter, a thousandth of a millimeter thickness of superconductor, and that material will carry 200 amps. Okay, so it's remarkable, absolutely remarkable material, but it's expensive. Has to be made with vacuum technology. It's all very, very tricky. So our problem has been that the material has leveled out in cost, if you look at the blue line. And this is because nobody will order it, because it's too expensive. The only way to make it cheaper is by having larger volumes of orders for it. And that's where the fusion message comes in. Fusion, these small fusion reactors need high-temperature superconductor. They need that material. They can't do it with anything else. And even one of the small-scale magnets, half-scale magnets that was built in the US last year, just one out of something like 18 they need for a single reactor, that took 270 kilometers of that stuff. And we make 1,000 kilometers globally, annually, of it. So you can see we're going to have to scale up hugely. A single tokamak, like the one I showed you before, will need 10 to 20,000 kilometers of this material to make it work. So we've got this opportunity. The cost the scaling up will have to happen, and everything that's been done previously in manufacturing advanced materials says that if we scale up volume, we can bring down cost. Okay? The practical lower limit of the materials is somewhere here. This is a log scale. With the deposition, they think somewhere here. And the technological, we're about 100 times more expensive than the low-temperature superconductors, but if we can get it down by a factor of 10, then it's commercially viable. Okay? There are other things that need to happen. We need to be able to learn. We need to learn how these are going to work in long-term trials. We need to learn how to integrate them with conventional technologies. We need to have standards. We need to have trained workforce, all of those things. But these materials are ready. They're ready to be used in applications. And to get them there, we're going to need public and private investment if we want to capitalize on their promise. So I've come pretty much to the end of my time. This is my vision for the future, superconducting future. There's lots of things I haven't talked about in here. I've focused on net zero. Quantum computers, superconductors are crucial for that. The message I really wanted to get across was that we have these materials right now. We don't need to wait for a room temperature superconductor. We've got materials that can be used right now for these technologies. We've demonstrated them. The properties are fantastic. We've demonstrated them in these small scale. We need to demonstrate them on a larger scale. And just get on with it, I think. Thank you.
Thank you so much, Professor Speller. We've got some time for questions from the audience. We've got some mics that will be circulating, so put your hand up if you have a question. We've got some back here too.
Thanks very much. I'm David Wood from London Futurist. The chart you showed at the end, the cartoon you showed at the end had a date 2007 on it. So how much longer do you think it's going to take before this vision is realized?
The cartoon I just put up there, okay, that was taken from a publication probably in that. Well, some of the things are being done now. MRI is in hospitals. Every MRI machine has a superconducting magnet. It wouldn't work without it. So they've been around for a long time. Quantum computers are using superconductors. Of course, they're not large scale or anything yet. The LHC, the particle accelerators, they're already superconducting technologies. Superconducting fusion reactors are being built all over the world, actually, including ITER in the south of France. So quite a lot of these things exist already. The idea of having, for example, all our electricity being transmitted across the countryside with superconducting cables, I would hope that, in 10 years' time, we would be starting to make some progress with that. Given the economies of scale we're expecting with fusion. Fusion is moving at such a huge pace. There's a lot of private investment, 6 billion of private investment in fusion. And they're working in a different way than it's been done before. So if anybody's going to make it happen, I think these really inspiring young companies are going to do that.
And I thought there were some over here.
Hello. Yep. I'm Ben from Connected Curb. We're an electric charge point company. A fascinating talk. I really enjoyed it. I'm just curious about the civils and the supply chain to roll this technology out. Is this above ground, below ground? Can you just pull it through a trench? How would it roll out?
Do you mean cables?
Yes. Yeah.
Yeah. Well, there's lots of details in there that I've skipped over. Because at the moment, depending on what kind of cables we're talking about, we use AC cables usually. Superconductors are not ideally suited to AC. They're not actually zero loss under alternating current situations. So superconducting cables are most likely to be useful where you might be thinking of high voltage DC. So getting offshore wind power onshore, these very long distance cables that can connect Europe to, throughout Europe. So DC technology is where superconductors are best suited. But we've made AC versions, we've made DC versions. They have been retrofitted in places like Tokyo, where they've got such huge problems with population density that they need to increase their capacity, but they don't have anywhere to dig new conduits for it. So it can be done. There is a company in Ireland, based in Ireland, called Supernode, who are at the moment working on this, in particular for offshore to onshore. And then there's in Essen, for example, there's a project called Ampacity, which is going from one distribution center to another around the city, and that's a superconducting cable. And in fact, even with the cost of the materials at the moment, that came out to be pretty much equal economically for that application to using conventional methods, conventional cables. Yep.
Anybody else? We've got about a minute and a half. Don't be shy. This is your time. The man over there. It's coming.
Hi, it's Aidan from Cambridge Consultant. You mentioned that about 40% of electricity used for power electrical motor. Well, I used to be power electronic engineer, so I know there's some years ago there were larger scale electrical generator use a superconductor, particularly for renewable. You mentioned it. Yeah. But why not happening on smaller motor, which is the larger volume? Particularly now we're talking about the EV, with all permanent magnet motors. Imagine if all those are superconductor motors, that would be super. And then you got the volume as well. So why not happening?
Yeah, well, I mean, I think the reason is it only will work if we can cool with liquid nitrogen, or we can use mechanical cryocoolers to get to these temperatures as well. And the materials are too expensive. It's not economically viable to do it. It's not that it's not technologically possible, it's that it's not economically viable. So I think it's the materials cost that's been the real barrier. The second thing that I didn't mention that's really important is that power companies are really conservative. They've got to distribute this electricity, they've got to know it's reliable, and they're not going to switch to a brand new, rather scary technology that needs cryogenics if they don't have to. So we need to make a case for how much we can make a difference. You've got to make a big difference before they're going to start considering it as a technology.
Thank you very much. I'm afraid that's all we've got time for questions now. Please join me in thanking Professor Speller one last time. Thanks so much. We are somehow incredibly drawing to the end of our time together. We have a little bit of a break. We'll be starting at 4:35, so just a few minutes in case you need a comfort break. We're looking at how enterprise readiness will propel quantum solutions into the future. Now, if that was a bit of a word salad, we're going to have 5 people on stage who are doing some of the coolest work that I've been interrogating them about behind the scenes, and they're going to be talking to us, exploring how to take quantum technologies out of the lab and into the real world. So stay tuned. We'll be back in a moment. plants, 5 brains coming on the stage. We've saved the best for last, and that's saying a lot because we've had a fantastic group of people today. We're going to be talking about how to take quantum technologies out of the lab and into the real world. Joining me on the stage, there's 5 of them, so we'll take our time introducing them. There's 5 of them. The first is Andre Koenig. He is at Global Quantum Intelligence, so come on out, he's the CEO. We've got Dr. Ilana Wisby, we've got Siwi Tan, we've got Manjari Chandran Ramesh. It's going to be really, really interesting. There will be time for some questions maybe at the end, but the focus is going to be on hearing what they've got to say and debating amongst themselves. So over to hopefully there are a few more of you coming. Come on out, just come on out. Don't worry. Sorry. Carmen, Siwi, and Ilana are going to be coming out on the stage, fashionably late to their own party, love it, to talk about bringing quantum out of the lab and into the real world. Over to you. Enjoy.
Thank you so much, and I'm delighted to be spending the next 55 minutes in this beautiful companionship, but they are much more than that. Everybody here is a leading scientist in their respective fields, and all related to quantum. You studied robotics, I believe, right?
Yes, so I wouldn't call myself a leading scientist, an investor maybe, but not a scientist.
And we'll get into that, and we'll explore a little bit what quantum is, what everybody is doing, and why that's so exciting. And I'll start with you, Ilana. I'll go over to you, and because you finance everybody, we'll finish with you. So quantum is spooky, right? And we were just talking about that. That's what Einstein said almost 100 years ago. And it's still not really sure when you read the press or online what quantum can really do and why and when. Ilana is building a quantum computer with her team, Oxford Quantum Circuits. It is, I had the privilege of seeing it virtually, in my opinion, the leading quantum computer in Europe, and that is a lot to say. Lucy, tell us, why does she have a name? I don't know any other quantum computer with a name, at least not in market. But what is Lucy? What is her goal? What is her mission in life? What does she want to achieve?
So Lucy was Europe's first quantum compute as a service that was available via public access. So it's an end-to-end system. She's absolutely stunning. She looks like a beautiful chandelier. She's got an 8-qubit processor. And I'm going to be honest, she's really old now, and she's going to be taken offline in the next few months. And we're going to have a party to celebrate all the work that she's done. But yeah, we build these quantum systems. They're absolutely stunning. And then we make them available to customers so they can run algorithms on these end-to-end quantum computers. And that can be through public access. It can be through private cloud access. And Lucy is paving the way for our next generation systems, which are called Toshiko. And I'll come to the name in a moment. And Toshiko is a 32-qubit processor, and these systems are now deployed in co-location data centers around the world into the world's existing digital infrastructure so that customers can securely access quantum as if it's effectively on-prem without needing to physically buy these incredible systems themselves. So this is, first of all, like very much the future of compute. Why are they called Lucy? Why is it the next one, Toshiko? Each of our systems are named after pioneering women in STEM. So when we talk about Lucy, we're talking about Lucy Mensing, who was a pioneering German physicist, and this was, of course, representing the system going online in Europe, and that being a European first. And then Toshiko has been installed in the TY11 data center in central Tokyo in Japan, and is named after Toshiko Iwasa, who is a pioneering female physicist, actually the first one that was awarded a PhD formally in Japan.
And so you're the CEO and co-founder of Oxford Quantum Circuits. You have a PhD in physics from the University of London. I'd like to go a little higher up before we talk too much about product. If Lucy looks back at all her children in 20 years from now, what will she be seeing and saying? Why are you doing this? Like the big picture.
Why am I doing this?
Talking about use cases.
Yeah, of course. I mean, I want to build a brighter future for everyone that is enabled by quantum. That's very much our reason for being. That's why all of our team work for us, is they see this, the impact and the good in the world that quantum can bring, and we want to be part of that. And as a CEO, I take a huge amount of responsibility for that vision, for that mission of making sure we deliver this incredible, world-changing opportunity. There's so few opportunities that you get in life to do something that's genuinely going to have an impact. Like, I genuinely just feel privileged and humbled to be able to lead a company in this way, but also bear the responsibility of that, of want to make sure, number one, we may bear the technology to full fruition, but number two, we do so in a way which is ethical, which is sustainable, which is promoting diversity and inclusion and building that brighter future, not just from the tech, but from the business perspective as well in everything we do. And I know that, you know, we have many shared values, and if we look at the other leaders of this field that are pioneering this forward, it's phenomenal to see the alignment of that, of a brighter future for all through business. And I think that's very powerful. And it's through love, but we can touch on that later.
We will. And there's only a handful of companies in Europe building quantum computers. So these are in market, they are available. They don't do all that much yet. I'll let you correct me later. But you know, this is a real thing. Of course, this serves a computational purpose on a computer, and that bigger business problem, you have a lot of information. And that's where Carmen does some crazy things. You have a PhD in quantum information from Cambridge. You're the CEO and founder of New Quantum. Mm-hmm. Can you explain, because I didn't really know that for a long time, what quantum information is and why you're doing stuff to quantum information and why that is so crazy? And then we'll talk, then I'll ask about product and those, but stay high level for
let's get right into quantum information. Well, I think, you know, the concepts behind quantum information, quantum mechanics and quantum foundations, which are some of the, maybe the most successful theories that physics has ever made. And by successful, I mean they've been proven to be correct to very, very, very high degrees of accuracy. Basically give us a few concepts that make us think about information in a different way, think about information and use information in a different way. So specifically, the two main quantum concepts that we use in computing and in other areas of quantum are entanglement and superposition. So, you know, we're not using information in a binary way anymore, where bits can be 0 or 1, but you know, a combination of qubits or a qubit can be in multiple states at the same time, in a superposition of these states, and bits are not independent from each other anymore. They have this correlation called entanglement, and those concepts are what enable quantum computers to be so powerful. And it's this big departure in how we think about information, which is really, I think, is the significance behind this field that it's the first step change in information technology from, you know, since the birth of classical computing.
And explain a little bit why it is so difficult to work with quantum information.
It's very difficult to work with quantum information because quantum states and qubits are very fragile. They are very susceptible to anything that happens in their environment. And you know, we can only observe quantum mechanics when we are looking at very, very small scales, at things like individual atoms or individual ions, or things that don't interact with the environment very much, like photons, which don't have a mass, so they don't interact with the environment very much. When we try to scale up these systems, it's very hard for the world, not, you know, noise and, you know, electromagnetic waves not to interact with these qubits and make them do other different things that you didn't want them to do.
So what products, what does that mean for the end user? What is New Quantum trying to make out of all of this?
So what that means is essentially that because qubits are so hard to control and to isolate, and they make a lot of errors, the field has come up with this thing called quantum error correction, which means that we can use many, many physical qubits that are noisy to encode one logical qubit that is not susceptible to noise anymore and should be, you know, a perfect logical quantum entity. But what that means is that if we want to tackle commercially relevant problems and say we need 100 or 1,000 logical qubits, but we need about 1,000 physical qubits to encode one logical qubit. Then suddenly the requirement for physical qubits goes to millions. And at the moment, companies are able to more or less assemble and control maybe 100, maybe less. And there's no clear path to getting to millions of physical qubits in a single quantum computer. So that's where New Quantum, the company that I run, comes in. We're building quantum networking hardware technology so that we can interconnect many quantum computers together to enable distributed quantum processing and to get to those millions of physical qubits. So we can scale in a modular way. We can have smaller, more robust quantum computers that work together in a network.
So we have quantum computers. We have the improvement of those quantum computers and networking them. Horizon tries to enable people to use these quantum computers today and in the future, right? You're the chief science officer. You have a PhD in physics from MIT, another small school that I easily got into. Tell us a little bit about what this means for the end user today, and project yourself out, whatever timeline you think makes sense.
Right. So quantum computers rely on quantum bits that Carmen has just explained to us a little bit about, and why they're so difficult to operate on and to handle. And Ilana has a quantum computer, which we call an all-purpose quantum computer, where basically you can utilize the rules of quantum mechanics to operate on these qubits and perform computations on them, called quantum computations, using gates and stuff. So, but the problem with quantum computers is that not just, of course, there's like barriers to use of computers because of the need for a lot of qubits. And today we still do not have enough qubits. But there's also another barrier, which is the barrier to having algorithms that you could actually run on these fault-tolerant quantum computers. So even if we have a working quantum computer today, we still do not have the programming language, we don't have the abstraction like we do for classical computers to be able to deploy, like compile deploy to quantum processors, and that is a challenge. So what we do at Horizon is we believe that it is possible to have a unifying programming language and automated algorithm synthesis to be able to construct and identify places where speed up in computations, which is a key application of quantum computers, and why so many companies and organizations are pumping money into quantum computers to be able to speed up computations that are so important to us today. So we are building this compiler that will essentially automate this process and allow our users without quantum knowledge to be able to figure out what kind of domain-specific applications they might be able to speed up using quantum techniques, but without the PhD, or PhD optional, like we like to say. Yeah, but it's a really interesting time for quantum computers. So, yeah.
Good. We'll get more into the use cases, but and these are all world first, right? As I said, there's maybe a handful of credible competitors to Oxford Quantum Circuits. I don't think Carmen really has competitors. It's too difficult what she does.
No, there's a couple.
Yeah.
A couple quantum networks.
And using quantum computers is Einstein would definitely call it spooky. But then you have to finance all of this, and that's a lot of money. Well, actually, not that much, but more than I have in my bank account. And you understand this stuff. You have your PhD from Oxford, but venture capital is in itself a spooky thing, right? How do you make sense of this? And in the context of how venture capital works, you need to assess risk, you need to understand your return, your timelines. Tell us a little bit why you're in quantum today, and how you make sense of this.
Sure. So I'm Manjri Chandran Ramesh. I'm one of the partners in Amadeus Capital Partners, and we're a global technology investor. We've been investing for 26 years in what's now called deep tech, and it's really cool to sort of be investing in deep tech now. But Amadeus decided to invest in deep tech before it was cool. in the same way that Amadeus and I decided to invest in quantum before it was cool to invest in quantum. So I wasn't with Amadeus at that time. My first investment into quantum was actually in Oxford Quantum Circuits in, what was it, 2017, I think?
Yep.
Yes. And then I moved to Amadeus 2 years ago, and I work very closely with New Quantum. So I'm in this unique position that, I get to interact with fantastic founders like Ilana and Carmen, and I've been on many panels with Joe and you as well. So it's a really exciting time. But to answer your question, why does venture capital look at it? So as a deep tech fund, we are really focused on the next wave of technology. And when we are looking to deploy money, we are looking for opportunities that are going to literally change the way the world is. So it's going to be a super disruptive technology. It's going to have a huge market opportunity, but it is going to make some returns because obviously we are deploying money for returns. So the timing of it does matter immensely. So when both Amadeus and I decided to invest in quantum, one of the things that we were very aware of was that the right time to actually get involved? Because you can't really time any market. Any person who invests in the stock market will tell you that. Do not try to even time the market. And that's not what we're doing. But you can take a very educated guess on what are the technical risks that need to be overcome for this to become a product. So how long is it going to be before this is actually a product in the market? What is going to be the value proposition if such a product exists? And so that's where our expertise comes in, because we've been doing this for so many years to really look at when was the right time to invest, how much should we invest. It is hardware, it is capital intensive, much more than what you might invest into a B2B software play. But my goodness, the results are just so exciting. So, no regrets on getting into quantum.
How excited are you, and Amadeus Capital does DeepTech, as you mentioned, right? And we've worked with you, probably the most sophisticated VC in that field. How excited are you about quantum versus other deep tech technologies? Rank it.
Personally, I'm super excited, and I've got a huge bias on that because I did my PhD in machine learning, and I invest in sort of foundational AI and quantum. So I kind of believe that AI and quantum is the way forward. My colleagues keep me more grounded, so that's a good thing. So Amadeus itself invests in everything from sort of synthetic biology and med tech to novel materials and climate and photonics and quantum and AI and cybersecurity. But because I work so closely with the quantum startups, I think we're really at that sort of shift, right? So 7 years ago, it was definitely very exciting. It was the right time, I felt, for the technology to be funded to come out of the lab. But now, it's like it's got to a point where it's really exciting. A lot of companies are willing to engage with the startups, to look at the use cases, to work more collaboratively, to actually create a product. And I think that's a fantastic time for startups, for investors in these startups, but as well as the large corporates, because you're actually in that process of bringing something that was possibly science fiction, or at least definitely in the lab, out into the market.
And we are in the process of bringing these technologies to market, and users are starting to use them. And we're also in the process of figuring out business models, pricing models, all these kind of things. I'm sure you all have heard about IBM and their cloud offering. They now have 24 quantum computers available in the cloud. And I live in the US, that is the approach there. Lucy and her children have a different approach. Can you talk a little bit about that and why Oxford is taking a different perspective on how to bring that hardware to market and why you think that is better?
Yeah, absolutely. So first, I'd probably say that her sisters, and they're probably her bigger sisters rather than necessarily her children. But what we're doing is partnering. So we have the strategy of building the core and partnering with the best. Like we cannot expect to have to do everything ourselves. That's why we have partnerships with some key people here as well to make sure that we can provide the right service offering to customers. The way we see this market evolving is much more like, say, the high-performance compute market before it. So if you look at the standard McKinsey, 15-year projections, like 260 billion. And if you look at the high-performance compute market, that's segmented into two. So you had one area which was like exclusive, kind of very high performance but niche, like lab-based quantum. High performance compute analogy might be to say Lenovo. And then you've got more mass market, widely accessible quantum, which is, say, more like Dell. So for OQC, we're focused on that kind of Dell as a service type model of making sure we are providing quantum to customers in a mass market accessible way. Now, we cannot expect those customers to come to us, right? We cannot expect those customers to go, right, I want to engage in quantum. I've no idea what I'm doing. Hey, I'm going to have to go to my chief information officer and now say, that little startup over there, can I put all of my private, confidential client data across the public cloud and run a quantum algorithm in the middle of Oxford countryside? Like, it's probably not going to happen. It's a huge barrier to entry of access. So instead, what we focused on is how can we make sure that we are creating this vision for enterprise-ready quantum, which is focused on customers today and bringing quantum to their existing infrastructure. And that is enterprise-ready quantum in a nutshell, right? It's seamless, it's 24/7, it's integrated into their existing workflows, be it through plugins, be it through their existing data center models. We approached Equinix, which is the largest data center provider in the world, about this, and they completely got our vision, and it was with them that we thought, right, let's now physically deploy the quantum computers into these data center environments. That means that everybody that has either a rack in those data centers can direct connect into those systems, and literally you can log on to the platform and just search quantum, you find OQC, and you just add Toshiko to the system, right? That's not to say that QCAS, Quantum Compute as a Service, isn't the primary business model in terms of go-to-market strategy going forwards. What we're doing is then strategically positioning ourselves around the world in the locations where the customers are and bringing down their barrier to access as much as possible. The other thing I'm super excited about is, right, think about the different market verticals. What software applications already exist where quantum is going to be a huge enabler? For example, simulation software. Think about stuff like ANSYS or any type of modeling. The financial markets, what's their software that they're using? How can we integrate quantum as a plugin into the back end of that so it's seamlessly accessible? Ultimately, the customers, they don't care that it's quantum computing. We don't want them to care that it's quantum computing. We want them to be able to just solve their problems in ways that has never been possible before. And that's really what we're doing in that go-to-market strategy. I think, of course, it's nascent. Of course, it's early. About 4% of the market, I'd say, are advanced. They come to us, they're like, just give us access to the computer, give us the API. We've got a team of 25 plus engineers that already know and are analyzing. And this is primarily defense and security and financial institutions that sit in that kind of 4% of super quantum advanced that can just get on with it. About 70% are early movers, and they are engaging, but they need a little bit more support. They need a bit more hand-holding through it, and that's where we partner, and we have relationships with other consultancies or other quantum software companies to support customers on that journey. And the final area, of course, is then the people that just want business impact now. And that's a really interesting area. And actually, we do have customers that are like, I just want business impact now. And quantum is never going to be siloed, right? It's never going to be just you're running a quantum algorithm on its own. It's going to be integrated into the existing world. You're going to have QPUs, GPUs. Like it's going to be integrated with high-performance compute. So here, what we're able to do is partner with Fujitsu, partner with NVIDIA, and then find what subsets of algorithms can you run on quantum computers, and then how can we make sure we're still delivering business added value now through the high-performance compute aspect, so that you can get them on that journey, but also provide them the business added value, which demonstrates return on investment for their key stakeholders internally as well. So that's the market today and how we're navigating it, but the future is still quantum compute as a service. That's the value inflection point, and it's just how do we make sure that we support customers on that journey to get them through that pipeline, bring down the barriers to access, and then make sure as a company we're strategically located to service as many customers as possible around the world.
That's a bold statement, quantum as a service. I'd like your opinion on that. But before, you're absolutely right. People don't buy quantum, right? They don't really care. what is the mindset of a buyer? And I'm not yet talking about use cases. We'll get there next, hopefully. But what problem do they have? What's going on in their head that they say, hey, we need to call Oxford quantum circuits?
It really it kind of depends on, spoke about this kind of advanced versus early movers to what their mindset is. Generally, there's a huge amount of FOMO, right? There's people that recognize that quantum is going to happen. It is inevitable, right? There's enough technological development, there's enough money in the market, there's enough traction. Quantum is inevitable, genie's out of the bottle, it's going to happen. And quite a number of people have been ahead of the curve on that and have already started putting the teams together. So they've already identified specific use cases, say within their portfolio analysis or within their specific, not getting onto use cases, getting within their specific area, they've already identified, and they are of the mindset of, I just want to be able to prove this out, understand how to work with the system, and make sure that I can also assess and benchmark the systems that are out there today so that I can get there first. Super competitive. The second lot, usually there's one or two people in the organization who have been tasked with, we need a quantum strategy and we need it 3 years ago. And they've been tasked with that, and they've got to figure out the market on their own. They've often the first question I get is, I need a team. What team should I build? And I send them someone else. But it's often with them, it's more curious. It's more trying to understand the impact on their business, what sort of subsets of problems it can solve. And it's often quite like an educational journey for them to understand how to interact with it and what it's going to mean for them as a business. And usually they're kind of middle management on rapid career progressions that have got this opportunity to build out a quantum strategy and a quantum team and recognize the potential of that. So I'd say that's the two general kind of approaches.
And so Ilana made this bold, in my opinion, claim that the future is quantum as a service. There are many other models, right?
Yeah, they make us more money today. But
I'm not going to pick that fight. I learned my lesson. Don't argue with Ilana. But hopefully you can. IBM just offers a cloud, hands off, and they have a consulting team, right? Others just do on-premise. There are many different business models in quantum that are emerging, which I'm sure you look at with Amadeus. What's your opinion as you look at the ecosystem and they are starting to come to market?
So I think that is the beauty of a nascent landscape, right? You have this option of exploring various business models. I mean, even when SaaS came about, there's so many different business models, ranging from the freemium to the enterprise, licenses. So I think that is a really good thing, that there are so many different business models. I'm not going to predict where the market is absolutely going to land, because I think we're still in a stage where people are trying to work out where they're going to fit the whole quantum offering into their business processes, where exactly they're going to. They have certain ideas, which is great. They are testing those ideas, whether it's the financial institutions or indeed, sort of new materials, the pharma sector, they're all testing. But until there's a clear pathway that this is exactly where the value proposition is, we're not going to really know which business model is going to fit that value proposition. So I think it's great that each company is trying out different business models. That's exactly how it should be, but we're not going to call it right now.
Yep, too early to call. I can't really call you and order a pound of entangled photons. Your market is a little different. Your customer is very different. How do you view that maturity of the market in general, but your technology and your products specifically? Who's the buyer? Why are they buying it? And what?
Yeah, it's an interesting question. So just as background, quantum networks is at a much earlier stage than qubit technology, than quantum computing companies. So there's, as we were saying before, there's 70 or 80 qubit companies building quantum computers. There's fewer than 5 quantum networking companies in the world. And we're getting we're building the first prototypes, whereas, Ilana is already deploying, I don't know how many quantum computers all over the world. So, so it's a little bit more early stage. And the business model or how we get income will change over the next few years. So for us, we'll start to deploy the first systems to buyers that are government and some big industry that is interested in exploring what it means to have this capability, this networking capability, this distributed compute capability, and what needs to start to be built on top of that. That will be the next, several years, maybe 4 or 5 years. We will start to also kind of, collaborate with qubit companies as they come to their limits of scaling and they start to need to explore what comes after and start to build prototypes of distributed computers. So, hoping that will happen soon, for example, with OQC and others. And that, again, will be first prototypes that will be very, very high-value systems because they will be very unique and sold to government, big industry, maybe some deployment in data centers. The roadmap for qubit companies is all about, having more and more qubits in their systems and higher performance, lower and lower errors, and more availability, which is a big thing. It's a big challenge in the industry. For a quantum networking company, the roadmap is all about being able to interconnect more and more nodes, even if each node doesn't have that many qubits, but connecting a larger cluster with, again, higher performance, which in our world is all about rate and fidelity. At some point, these two will come together, and that's where I see the kind of as-a-service model really taking off, because we will be able to together offer much more compute capability and much more service quality. So things like uptime. If you have a modular system, if one of the nodes has a problem, you can keep using the other ones. Things like elasticity of service and robustness of service. Those are things that we can aim for when both networking and compute roadmap come together. When that will happen is the $1 billion question, but I should think that it's the kind of 5 to 10 year side of the decade.
And I don't think we have yet done justice at the scale of the impact that your solution could have when it's deployed. In very simple term, when I eat ice cream, I'm less sad. I drink wine, I'm more happy. What will governments, what is the scale of the impact when your solution is deployed? Why is that so meaningful?
It's meaningful because it tackles scaling in a different way. So not relying on more and more R&D breakthroughs inside our computing core. We already know there's very tough challenges to continue to scale the number of qubits that you can reliably control. So you have it's a tangential way of scaling that is modular and can provide that that path to commercial fault tolerance, really, where we could ideally stamp out robust, smaller quantum computing cores and interconnect them together in an interesting architecture. And then the other thing that is very recent for us, but I think really exciting and potentially really meaningful, is that, so we were talking about error correction before and the fact that you need many physical qubits to encode one logical qubit. So the reason you need so many physical qubits to encode a logical qubit is to do with how the qubits are arranged and how they are entangled together. If you have a single node, that pattern of qubits will be static. It will be what it is, usually nearest neighbor connectivity. If you have the ability to entangle cores with these photonic links, you can create a pattern of entanglement, a topology of entanglement that is not fixed. It's not nearest neighbors. Is something maybe more complex and more long range, more like a hypergraph rather than a 2D plane, and that could allow you to use better error correcting codes that need fewer physical qubits per logical qubit. And long story short, you might need fewer physical qubits to get to the same computing power that was predicted with just monolithic scaling. So a more efficient architecture could be achieved with a distributed system.
Yeah. Nobody wants to build more qubits. The fewer qubits we can do, the better, right?
We want more qubits. We want higher quality, higher performance qubits. But we do definitely need to scale, and interconnects is 100% one way of scaling.
So we're still not exactly sure what customers actually want to do with it, but you're selling it to them. So you do applications, and we'll talk about use cases, but help us understand what that looks like. Who comes to you? What do they ask for, and what do they get?
Yes, we are focused on not like specific applications for quantum computing. So what I mean by that, I have to step back. To explain that, I have to step back a little bit. So I mentioned that for applications, we rely on specific algorithms that have been discovered. And the types of algorithms that have been discovered revolves around, like creating crypto systems, search. There's a Grover search algorithm. Then there is factoring, which breaks RSA. If we have, one day a fully fault-tolerant quantum computer, and more recently, in the last 2 decades, we have HHL, which is a quantum machine learning algorithm, which also has an exponential speedup. So I mentioned exponential speedup, and the fact that quantum computers can do these things much faster than classical computers, or at least promises to, when it finally comes to fruition. If we one day have Lucy at 1 million qubits, it can do all these things. And that's the kind of applications that have been discovered. But what we believe is that because very few people in the world today could actually create these or find these algorithms, because they're siloed into domain-specific knowledge. So we think that we at Horizon think that there's a lot more applications out there that could lie dormant for us to discover, or at least something that nobody has thought of, right? And in fact, the 3 domains I talk about, it's like 3 large families of algorithms, quantum algorithms. And in fact, recently there was a result that says that these can be framed into one problem, which is the quantum singular value problem. But anyway, so what we do believe is that if we put a quantum computer in the hands of developers who are trying to find applications to speed up their calculations using quantum computers, they themselves, could actually discover more about what could be done. And we think that applications can be as wide-ranging, as high-performance computing, and that's how we think people should think about quantum computers. It's not, something completely crazy and new. It's like, actually, we have things today that analogously can be thought of as, like high-performance computers. And quantum computer, I think this also kind of rings similar to what Ilana said, it's like it should be sitting in the server. We shouldn't think about it as like something completely crazy, even though maybe quantum mechanics is, but it's something that could potentially speed up a lot of different calculations that is inside applications. And it's just that it's waiting for us to discover that. And we think that the way forward is not for, like a company to go to another company and say, hey, can we pay for a PhD student to look into this, take months and months to come up with a quantum algorithm or like a variant of a quantum algorithm to speed things up, but rather, do it automatically using known techniques, maybe in quantum techniques, but it could also be classical techniques. And I think that's interesting because like the emergence of quantum computing as a resource now, right? So you can deploy through AWS or Quantum or IBM. You find that like when someone runs something on a quantum computer and say, oh, I got this, and it's like kind of there's a speed up, and then like the classical quantum computer science is like, no, we can't be beat, and then they find something better. They find an algorithm that's better by like tiny little bit, and they're like, see, so it's actually pushing the frontier of computer science and not just among quantum computing scientists.
So what does a happy customer today look like? Do they go home with millions in cost savings on whatever process you worked on? Or in your experience, what is success today?
Right. I'm getting a lesson in MBA here. but so we are still pre-launch at Horizon. We are pushing early access soon. But we don't have customers yet, so we're still trying to get our system built and up and into the hands of customers. But I think we project potential customers, once we have the system built, to be people who are interested in high-performance computing, so probably things like aerospace industry, probably automobile, people interested in molecular simulation, so pharmaceutical companies, people interested in fast computations, so banks, and a few others probably like mining companies who might want to compute certain simulations quickly when they try to do, I guess, geomapping or stuff like that.
Yep. So Manjari, good news. I'm very excited. I just decided to build a quantum computer, and I'd love to accept you as an investor. How big a check do you need to write to me for me to be able to do that?
Before I go to that, I'm going to just cover one more point about the business models, right? So we spoke about business models for the quantum computer itself, but as Carmen said, as a quantum interconnect, the way they charge the customers is going to be quite different because their customers are going to be different, right? And if I look at, some of the other companies within the portfolio, so Riverlane is it's the operating system for error-corrected quantum computers. Their customers will be the end customer, but also, somebody who's going to be working in the landscape. So their business models is likely to be slightly different. And then if I look at yet another portfolio company called CryptoSense, which got acquired by Sandbox AQ, they're actually looking at post-quantum cryptography, how, if a quantum computer was there and able to crack your current encryption methods, what do you do? So again, their business model is going to be very different from what quantum computers' business model is going to be. So I think that's the excitement of such a nascent landscape, in that there are so many different ways you can actually approach it. Going to your question, I think this is like any other, sort of deep tech investments. It needs patient capital. And I always, sort of tell my founders, Carmen's probably going to go, yeah, I've heard this now. When you say patient capital, it's not the lack of progress. It's just, it takes longer to find that product market fit, right? In sort of the non-deep tech sectors, typically, you'll come to a minimum viable product 6 months, maybe a year, you're already deploying it. I mean, these founders have been working on these problems right through their PhD and as a company for several years. And it's only now that it's actually coming to the market. And it's, that kind of understanding as a deep tech investor that you need. So it's not, I wouldn't say it's necessarily amount on the check that is the thing that decides whether the right investor is in the right company. I think it's very much the investor who understands what it takes to get to product market fit, what it takes to actually scale the company, which business model is going to ultimately work for the company.
Yeah, and there are companies that have raised 40, 50 million and built a working quantum computer.
Companies that have raised several hundred million as well, right?
800 million, and they still don't have a working quantum computer.
Exactly.
So it's difficult to say. A company just sold 2 quantum computers for, I think, 21 million. To some people in Switzerland. Was it 21 million? So if you do the math,
I need to up my prices.
Yeah, right.
Yeah,
it's a good market.
I think that the point here, though, is more money doesn't necessarily mean a better product, right? I think it's a mistake for the market to think that, ooh, that company has raised 300 million. They must be the best quantum technology company out there. No, they've been very successful in convincing investors that their vision is something that the investors should buy into, which is a skill in itself, right? I'm not, sort of detracting it from the management team, But that doesn't necessarily make their tech the tech that's going to win, right? That they have a very good chance. It's a lot of money. You can do a lot of things. You can make some mistakes and get away with it, which you can't do if you don't have that much money. But it doesn't necessarily mean more money means the company's better.
Yep, there is still a real advantage in smart science, smart engineering in this space. So, and we have 10 minutes left. I think we promised backstage to have a positive, uplifting message on this panel. No doomsday AI or quantum. If we look at the future, and you decide what that future is, if it's 5 years, 10 years, 20 years. But I still don't feel we've really honed in what quantum can potentially do and how it can change the world. So I'd like to go down the round and give us your dream, the uplifting story.
Well, I think as we were saying right at the beginning, this is the first kind of step change we've seen in the processing of information since classical computers. So we're I think we're at the beginning of the next century or centuries of this really giving fruit. So there's the possibility that these technologies will end up delivering as much value, as much new use cases, and as much benefit to society as the first wave of classical computers and telecommunications have done. That's that could be a world in several decades. For me, one of the areas of application of quantum that I think is very interesting and has the most impact potentially is everything to do with climate change and the new materials and processes that we will need to really, really, really change the way we occupy the world.
For you, is it a dozen use cases in a dozen different industry, which is huge, of course, that would be transformative, or is there a bigger mission behind it, maybe as well when it comes to the application of?
Yeah, I think the ambition is high. I think we want to think of quantum computers as something that can change the way computing works now. I'd like to just point out the pattern in this. It's like quantum technologies is not an old thing. It's not magical. It's just that we got to the point where we have so much control over these tiny microscopic systems. It appears like magic, because we could actually do things with them that we couldn't do before. And when I started my PhD, it was like more like 2004. It's unimaginable that we would have an operating quantum computer sitting on AWS waiting to be deployed to. And I think the first quantum revolution came about some time ago was the transistors. That was like the previous topic here on the stage. And then the second revolution, I think, was things like GPS, lasers, which you can't live without a laser now, right? And that's essentially a quantum mechanical process that happens, but you don't think about it. And I think this is part of that pattern. It's like the third wave. And it's about information, which is exciting. Being here in England, Shannon, Turing, all the big ideas about computing and changing the world. So I think implore everybody to think big, and that this is something that we all can have a share in, and potentially be optimistic about what the technology can do for us. And we hope that we will do it for good and not for otherwise.
Version N of Lucy?
I think what's amazing about quantum is quantum enables us to solve the problem of problem solving itself. That's the machine. That's incredible. And you can imagine this future where in 10 years' time on Lucy to the N, you're able to truly simulate and create new drugs, right? Create new drugs that underpin the future of pharmaceuticals, because each and every molecular atomical interaction is quantum mechanical, and we cannot simulate that effectively with any accuracy or for a long period of time, because it's a quantum mechanical effect with a classical computer. With quantum, you can do that. So that's, huge impact on society as we know it. Take the drug discovery process down from 10 years to effectively simulating it on a processor in 10 minutes. You might imagine a future the same, like for molecular simulation. Photosynthesis happens every blade of grass around us, and we cannot simulate that process. That underpins the energy industry, right? Fertilizer solutions that are around the world use up like 14% of the world's energy. You have to do it in massively high energy-intensive, wasteful chambers under extreme pressures and extreme temperatures. Yet, Mother Nature has figured this stuff out on the grass around us. That's quantum mechanics. With a quantum computer, we can truly understand that and understand that problem and come up with better solutions. Same with batteries, right? Think about the band gap. How can we use that to create new battery technologies? And then, of course, data. There's so much data in the world, and yes, we know that we can utilize data incredibly powerfully today. We are burning up the data centers from an energy-intensive perspective, solving these complex algorithms, and we're still limited in terms of the multivariable problems that we can solve. With a quantum computer, you can solve these multivariable problems a lot more quickly, a lot less energy-intensively as well. So we can help build that brighter future. This is what we're talking about. This is a brighter future for all. And once you have a system that is truly powerful enough, and it's not simply an imagined future of 15 years, this is already happening today. We have customers today. I'm doing flood analysis, seismic analysis, Monte Carlo simulations, radiation transport modeling. We're doing all of this work with large corporates already today. We're working with financial institutes on understanding what algorithms they can do to, better understand their risk analysis. Yes, it's a little less like green and fancy, but these are applications that are happening today, and we're just at that tipping point where the next generation of systems that we're going to see deployed within the next few years, and I would say even probably potentially from some people's roadmaps at the end of this year, beginning of next year, we're going to see that space where you can no longer simulate the quantum computers with the existing, multi-core processors. So that will be truly the point where we've actually been able to achieve that transition point. Some people argue we've achieved it already. Some of our customers say they've got speed ups already. I'm like, because it pushes the algorithms to be better. So it's such a pivotal moment for the space, and I'm so excited about the field, and I hope that gives a snapshot as to why we should be optimistic for this brighter future for all.
Is there a quantum company out there that you haven't come across yet that you dream of? If Amadeus were to give you 100 million, 20 years, none of your partners asked for any accountability, carte blanche, I'll build it. Tell me.
I'm not sure that one company is going to be a winner takes all. That's not the quantum landscape, right? So, if you look at the market opportunity by whatever it is, McKinsey or BCG, even their report, the one that came out, I think it was in April, was the quantum computing market will be anywhere between 9 billion and 93 billion. Like, what kind of a range is that? Because it's just so difficult to actually say this is going to be, sort of exactly this market, and it's going to be this company that's going to capture all of it, or 90% of it, right? So if I had 100 million, I would definitely invest a lot of it in the quantum space, but it would definitely be across the landscape.
Good, smart portfolio approach. Love that. With that, quantum is coming, and we are all very optimistic about it. For me, the key message, what these 4 entrepreneurs, and VCs are entrepreneurs, in my book, are doing is something new. They are not working on improving an existing thing or making something a little bit better. Everything these 4 are building has never been done before, and they are the world best at it, which is really pretty fascinating. So thank you so much, Ilana, Manjari, Siwi, and Carmen. I think we have a couple minutes for questions. Can't really see in the light, but I do see a hand. I see 2 hands. We'll start in the back on the couch, if that's okay.
Oh. Do we have a mic?
I'm not sure if there's a mic. You can shout out if you want.
with the design space, and I saw, oh, with a quantum computing, you can put all the design space at once, and they will deliver the optimized design in terms of process, in terms of material. Is it a bad picture?
Yeah. So to summarize, and of course anybody, but Siwi, I think it's for you, it's a question about optimization, especially in product design, and you come out of machine learning. But is that something that's possible? We have a product, we want to design a new table, and then instead of bothering a supercomputer with it, a quantum computer can just give us the optimal table.
There are algorithms out there that basically tells you how to use the quantum computer to, or at least quantum processors to find the solution to your problem. Yes, but yeah, right. So the answer is yes, but it depends on what kind of optimization you're looking at, and whether or not there are promised speed-ups there.
Yeah.
From like a physical cost perspective, the current QCAS model that is available is broken. If you want to start doing actual like large-scale algorithms, it would cost you like £4 billion or something to do a useful algorithm at a large scale. It's been set by the incumbents at like 0.0035 pence per shot, but realistically, that doesn't make sense when you have algorithms with many multiple shots across a probabilistic space. So that is something that we're also pushing down, right? So how can we give discounts for large volume utilization? The business model does need to change. The future is QCAS, but the costs need to come down to make this viable for the long term.
All that remains is to thank our brilliant speakers. I'm afraid we don't have time for any more questions, so we have to end on time to let workers go home. Thank you so much. It was absolutely fascinating. I'm sure I speak for all of us when I say we learned a lot.
Thank you.
If you want to ask questions or anything, people will be coming off the stage later on, so you're very welcome to do that. All that remains for me is to thank all of you for coming and your patience and attending. We've had many wonderful speakers here talking about artificial intelligence and different sorts of chips, superconductors, and now quantum. And we've thanked all of our speakers, but what you maybe are not aware of is that there's an entire team of technicians and engineers who've been making this magic happen. There's about 20 people behind the stage who have not had any applause, and I would love if we could give the biggest round of applause to them. Who's sweating it out in the dark to make it all happen and make everyone else look good, and that's the hardest job of all. So thank you, and thanks to all of you. It's wonderful to have your patience and dedication. I've seen many of the same faces over the past 2 days. It's been such a pleasure. So thanks for your great questions, and I hope it's been fun. Enjoy the rest of the evening. Apparently there's still sun out there. See you.